Nou, we kunnen de limit invallen. Je had juist de expectations laag moeten stellen.
Ja, misschien.
Maar ja, in elk geval, daarom zijn er nog een paar mensen.
Je hebt wel een moeilijke vallen.
Thank you.
Ook een beetje dezelfde wereld, ook weer uit de wereld.
So one thing is they have the camera set up. I know you have a clicker, but it's about the size of this, so can't really walk around the whole stage if you want to stay in the frame.
Oh, I have to be stay
Not directly in this, but you know, like.
but not here.
Yeah, don't go too far, just because they have the camera in one place. I think I can't remember where it is, it's somewhere. And they don't have somebody moving it. They don't have somebody actively moving it, so. Can we switch to video? Alrighty, I think we'll go ahead and begin to get started here this morning, so we aren't too late on the schedule today. We have a pretty packed schedule, but fewer people than yesterday, so hopefully things go a bit more smoothly in terms of moving people around. Huge shout out to PyData for running yesterday's conference, and we're super glad to have them, so please give them a sort of huge shout out for us. So as always, welcome to the third day of JuliaCon 2024 here in Eindhoven. I'd first like to thank our sponsors, as we have the past couple days. I will thank them all more fully this evening so we can move on, but just wanted to call them out real quick. Here's our schedule for today. Opening remarks are already 10 minutes late. Next, we have a keynote by Dr. Bert de Vries, who will be introduced by Dimitri, one of our fantastic organizers. We then have parallel tracks for about 2.5 hours before lunch. After lunch, there are parallel tracks again, in addition to the HPC Mini and the Earth and Climate Science Mini. Please attend those minis if those are of any interest to you. Those organizers have done a fantastic job there. Finally, at the end of the day, we have a keynote by Dr. Catherine Hyatt, a good friend and also a key member of our community on quantum computing. At the end, we have a closing ceremony. We'll announce the Julia Community Prizes and a bunch of other logistics and shout-outs and that kind of stuff, so please attend that closing ceremony if you can. And then tomorrow, starting at 10 a.m. at the Café de Lictoren, close to the West Court Hotel, we have our annual hackathon. So please show up for that. We always have many people working on all sorts of projects. If you need help finding a project or somebody to work with, please let us know. We typically can find people who need some help or who have an interesting project they want to talk and work about. Hopefully the maps on the TVs have helped in the past yesterday, and hopefully they will continue to help today. I know it's a very confusing layout, but hopefully people also realize where they are now. I wanted to call out JuliaCon proceedings one more time. We'll talk about that more this evening. If you have a talk today, please be aware that you can submit to JuliaCon proceedings for a paper, and it will be peer-reviewed and published similar to the Journal of Open Source Science. We also have a call for hosts. I've had a bunch of people come to me talking about how they want to host meetups, JuliaCon locals, and potentially the annual JuliaCon Global. Please continue to talk to me in person, but you can also visit the link on that QR code on our website, and you can also email me directly. That way I can keep track of your names and locations and everything. We have the code of conduct that I've announced every day, the same logistics as every day, and I wanted to thank our organizers and volunteers again real fast. With that all being said, I will introduce Dimitri, who will introduce our fantastic morning keynote speaker.
So our next speaker is Bert de Vries, professor from Technical University of Eindhoven, and I was a student. I am a student of Bert de Vries, so I did my PhD with him. And yeah, so the journey started about 4 years ago, more than 4 years ago, and I joined the lab. And Bert was very passionate about Julia. I never touched Julia before, so I joined the lab. And yeah, I started to use this language because that was the only language that we use in our lab. I learned it. So in the beginning, I wrote a package, rocket.jl, and I submitted it to JuliaCon, to my first JuliaCon. And it was in Portugal, I guess. Well, it's supposed to be in Portugal. And I couldn't go because of the corona. So it was first conference, I couldn't go. OK, can happen. Next year also was online. Next year was online, okay, couldn't go. Then last year it was in US. And okay, I knew that I need to apply for a visa, so I applied really in advance. I applied like 8 months before, and I couldn't get the visa, so I couldn't go. So this year, we do it here in Eindhoven, so I don't have to go anywhere with Bert de Vries. So Bert de Vries, it's your stage. You are going to talk about the research that we do in our lab. Natural Artificial Intelligence. It's really a great talk. So listen carefully and prepare your questions. Round of applause.
Yeah, thank you very much. Thank you, Dimitri, for the introduction. Thank you for coming out. It's 9 a.m., it's raining, so you could have just opened your browser, so I really appreciate you being here. My enthusiasm for Julia is indeed about 10 years old, but it was really instigated by Joris Kraak, who is working for Julia Hub now. We were colleagues at the time, and working with MATLAB, and Joris said, forget MATLAB, even Julia 0.3 is better than MATLAB. So we've been we started to work on Julia, and yeah, haven't quit since then. I'm going to contrast what I'm going to talk about, natural artificial intelligence, with the current AI, well, I wouldn't say hype, but the current state of AI, which is generative AI. Generative AI, ChatGPT, I love it too. Everybody uses it. It's fantastic aid in productivity. But there are some shortcomings. And for instance, there's no real-time learning in ChatGPT, right? And in generative AI in general, you can't just go out with ChatGPT and ask it to learn how to ride a bike. It's just not designed for that. It tends to hallucinate. It's very hard to check if what the answer you get from ChatGPT is actually correct, right? It's very resource hungry. obviously, not just in data, also in computing power, in number of people that are involved. And it's a kind of a black box. If you get an answer, it has troubles explaining itself. And these shortcomings contrast quite heavily with how we behave, how we learn, right? If I learn how to ride a bike, I do that in real time. I don't read 1,000 books on learning how to ride a bike. I just go out and ride my bike, and I fall, and I learn on the fly by trial and error. Our hallucinations, at least when we open our eyes and our ears, are corrected in real time by sensory imprints, right? We hallucinate in our dreams, but when we open our eyes and our sensors are open, we get a real-time correction. The whole brain consumes about 20 watts. There is a computer, the biggest supercomputer in the world, I think is in Tennessee, and it does about the same computation as the brain, but it consumes 40 megawatts. So that's 1,000,000 times more computations for about, or 1,000,000 times more power consumption for about the same amount of computation. The cortex, where the real stuff is happening, consumes only 4 watts. That's the power of a bicycle light. And we tend to be able to explain our reasoning, right? We tend to be able, if you ask me, okay, why did you say that? Well, I usually have I can give a reason for that. So that's the kind of learning that we're interested in, at least in our lab. And what we try to do in our lab is to find out how is the brain able to do this? And then use that for agents like ourselves that go out in the world. Robots, drones, and other agents that go out in the world and learn in real time on a power budget, because they're usually battery driven, and that are explainable. And so then we need to learn, how does the brain do this, right? And so we need to go to the physics, because the brain is just a physical organ. It follows the laws of physics. So I'm going to do a little bit of physics. And so the question is, it's a very basic question, right? If I have a ball in the left upper corner, black ball, and I throw it at T0, and it ends up in T1 at the spot on the right, and let's say it takes the black path, and then I can ask you the question, why does it take the black path? Why doesn't it take the red path? And you will likely say, well, that's just Newton's law. I can compute that. And that's entirely correct, right? You can compute that path with Newton's law. It just turns out there is a sort of a higher principle in physics from which you can derive Newton's law. Newton's law is perhaps not the most fundamental thing we can say about that path. And this is Lagrangian mechanics, and in particular, the principle of least action. And the principle of least action says, in nature, energy differences of any kind are minimized as fast as possible. So for this ball, if I write down an energy difference, in particular, the difference between the kinetic energy and the potential energy, right here, and I minimize this over time by differentiating, then I actually derive Newton's law. Right? This function, this energy difference, is called a Lagrangian. And this is true for bigger things in the world, right? Big things that move around. And if we have very small things, we can also write down a Lagrangian for small things, differentiate and get the equations of motion of small things, or Schrödinger's wave equation. For charged particles, we can write down a Lagrangian, the difference between electrical and magnetic energy, minimize it over time, differentiate, and we get Maxwell's equations, and so forth. And physicists like to put on a mug the Lagrangian of the world, right? And they say, well, this is the Lagrangian, the standard model of physics. All that happens in the world is, well, this Lagrangian is composed of energy differences of any kinds, and this is minimized in least time, and that's what's happening, right? So then the question is, hey, well, the brain is a physical organ. It should follow the laws of physics. We have movements, information movement in the brain, thoughts, reasoning. Is there a Lagrangian for that? Can we describe how we think, how we learn, our behavior by minimizing energy differences? And so Carl Friston says, yes, we can. And Carl Friston is a very famous neuroscientist in London. And he wrote down the Lagrangian, and this is the Lagrangian. And this Lagrangian is a function of probability distributions over states. So what does this mean, right? On the right, this picture is from a very interesting article in Wired magazine that is really fun to read. What does it mean? What does the brain really do, minimizing this function? This function is called a variational free energy. Well, it means that the brain is also a generative model. It builds a model with which it tries to predict our sensory imprint, right? And by receiving, and then you get prediction errors, and from these prediction errors it learns to build this model and change it over time as the world changes. To see that, or to illustrate that, here is a picture. It's called The Gardener by an Italian painter in the 16th century. And what do you see? Well, you see a vegetable bowl, right? And if I turn it upside down, the first thing you see is probably a gardener's face. Why don't you first see an upside down vegetable bowl? Well, when we go around in the world, we see a lot of straight up faces, a lot of straight up vegetable bowls. So we build a model to predict straight up faces and straight up vegetable bowls with higher probability than upside down faces. The data, our sensorium, is consistent with both, with an upside down face on the left hand side. This is also an upside down face as well as a straight up vegetable bowl. But our expectations are much higher for straight up objects. So our perception is this Bayesian fusion of these two things, and so that's why you get to see a straight up vegetable and a straight up face. It's only possible because we actually have a generative model of the world in our brain. From here on, it's just going to be mathematics, right? I want to talk a little bit about this about this variational free energy functional, a little bit, and the actual math doesn't really matter. But this variational free energy functional, this Lagrangian, is the only thing that's going on. Minimizing this Lagrangian is the only thing. It accounts for learning, perception, our behavior, attention mechanisms, everything. In the machine learning community, it's also known as a negative elbow, which means evidence lower bound on Bayesian evidence. It's a way, minimizing free energy is a way of doing Bayesian inference in a computationally effective way. It turns out that I can decompose this free energy functional into two terms. On the one hand, of course, minimizing free energy leads to maximizing accuracy. We want to get accurate predictions. We want to predict the world well, because if I cannot predict the world, then I cannot cross the street, right? I will get driven over by a car. On the other hand, we have a limited computational budget, right? We have limited time to make our computations. We have limited computational resources, limited sugar. We have just 4 watts. And limited data. So, but minimizing free energy also takes that into account. It doesn't just keep building bigger and bigger models. It actually trades off. It wants to get the best accuracy for a very limited budget. It will not learn, it will not go on to do more accuracy than you need to solve your problems, because it will conserve the energy. We may need the energy in our brain to solve other problems. On the other hand, there is a second decomposition at the bottom that shows that brains learn at the same time a problem representation and a solution. Both the problem representation learning and learning the solutions are just implicit in minimizing variational free energy. The problem representation learning would be learning the model, and doing the inference would be the posterior, and that's going to be your solution. It means that a brain also, we will never learn, we weigh off problem representations and solution. It's useless to have a perfect problem representation that I cannot solve. It's also useless to have a poor problem representation and solving it exactly. I need to have an adequate problem representation and solve it adequately. And we will never spend energy on formulating problems more accurately than we need and solving problems more accurately than we need. There's always this force in conserving our power and just spending just enough computation that we need. That's why the brain is 1,000,000 times cheaper than regular computers. Now, this is not just some oddball idea. This free energy principle, as Carl Friston calls it, is actually, it follows from straight physics. It follows just from the same approach to statistical physics as physicists have done for centuries, and with the right assumptions, right? There's an assumption that Friston takes is, he says, well, you exist as a thing, you are separated from the world, and what kind of processes must there be in place inside you in order to preserve that, right? Because once you are dead, you get reabsorbed into nature, but being alive means we resist that reabsorption. What kind of processes must be in place there? The free energy principle is a straight consequence of that question, right? And these ideas, Friston is also not the first one to come up with these ideas. In the control theory, people have proven that in order to make a good controller, you must build a model. And he also hypothesized then that the living brain must be a generative model. And this goes 50 years back. There are other papers from information theory, and even recently from in vitro measurements, just the biology in vitro networks of rat cortical neurons that show very strong support that brains minimize variational free energy. That's what's going on. From whatever view you look at it, whether you look at it from the physics view or from an information processing view or even biological in vitro, free energy minimization is the information processing that goes on in the brain. That makes it very clear for us, let's say an engineering lab here at the university in Eindhoven, of what our agenda is. If we know the math and the physics of what goes on in the brain, well, we want to get that math in on our Raspberry Pi or on our iPhone and send that iPhone in the world and say, now learn purposeful behavior, just like we do. Because our brain, by minimizing free energy, is an algorithm designer, right? We go out and learn to recognize speech. We go out and learn object recognition and navigation. There isn't an engineer, it just follows from apparently just by minimizing variational free energy, we design all these algorithms, we recognize problems, represent them, and solve them in the field, and learn how to ride a bike just by trying and learning, right? So that's the kind of intelligence that I want in my iPhone, and we call that natural AI because it's really based on the physics of natural systems. So in the end, the computations that we need to do in order to build these natural AI agents is variational free energy minimization or variational Bayes, because it's the same thing as Bayesian inference, as they would call it in probabilistic modeling. Are there packages or toolboxes around that do Bayesian inference? Yeah, there's lots of them, right? Even in the Julia community, there's Turing. There will be a talk later today, I saw, on more advances in Turing. There's Gen, and they're also in other ecosystems like Python and Ruby for that matter. There's also toolboxes. but for Bayesian inference, but we want something special, right? Our toolbox must be low power. We want to go out in the field, battery driven, real time. If I learn how to ride a bike and I'm falling, I can't take a minute to think about what's action to take. It has to, I'm in a real time loop with the environment. I need to still get performance. Right? I must be doing variational free energy minimization in a productive way. Of course, it must be user-friendly to code this all up, because who's going to code these Lagrangians and do all this minimization in real time? We want to have big models, right? So all these desiderata that we need for natural AI systems to go out in the world, that's not currently the focus of the toolboxes that are out there. And it hasn't been over the last 10 years. So about 10 years ago then, I got a chance to start a lab at the university here. And these are a host of PhD students and former PhD students that have worked on a toolbox in Julia to do just what I talked about, to do variational free energy minimization, but to do it fast, efficiently, to make it user-friendly, all the things that we want to support natural AI. And so these guys have written lots of dissertations, because this is hard stuff. There's a lot of math and physics behind it. Also, the coding is certainly not simple. And in the end, we have built an ecosystem in Julia. The ecosystem is called RxInfer. And RxInfer consists of a set of packages. And the most important packages, I'm just going to project them on this picture here. So from the user's perspective, if you're an engineer and you want to build an agent that goes out in the world and learns how to ride a bike, we have a language for that, GraphPPL. And GraphPPL is a very high-level language, and we really took advantage of meta-programming in Julia. Wouter Nuiten actually has done a lot of work on this recently, and later today he will also have a presentation on this. It's very easy to build a model. You just write Julia code, and if you have random variables, you use this very common thing of a tilde to say, well, theta is actually a random variable drawn from a beta distribution, and so forth, and you just write your model. Technically, that's all you need to do. Then you just put that model in our agent, and you just tell the agent, now go out and you communicate with your environment, you have sensors and actuators, and all you do is minimize your variational free energy. And that's what we want to automate, because that's really very hard to write out in math and in code. And that's what the toolbox is about. We support that with two toolboxes. Reactive MP, reactive message passing, I will get back to that, is a package that will do the actual variational free energy minimization in the agent. And RX environments is a package that in which you can simulate an environment. Now, why does it say RX environment and RX infer? Because this is reactively coded. These are agents that go out in the world and spontaneously minimize their free energy while they are communicating with the world. Just like for us, there isn't an engineer that writes a program for our brain. We're just doing spontaneous free energy minimization depending on our interactions with the world. So this needs to be coded in a reactive way, and so there is a package underneath Rocket that Dimitri designed a few years ago that both reactive MP and RX environments use. And these are the four most important packages that constitute the RxInfer framework. As a designer, you really only need to worry about doing your model. This reactive MP and RX environment is just basically a a system simulation that that minimizes its free energy. So RxInfer is hosted at GitHub. It's open source at the GitHub organization Reactive Base. And I want to talk a little bit now about what's under the hood of RxInfer, because there is a specific way in how we minimize free energy that makes it actually effective. Here's an animation of what's going on. It's a graph, and in this graph, messages are being sent to other nodes. I want to talk a little bit about that because it shows, because it's no accident that the brain is a graph of neurons, and these neurons send messages to other neurons. So let's assume that I have a function. So this would be my Lagrangian function, but let's assume it's just a probability distribution, f of 6, or is it 7 variables x. And let's assume that not everything depends directly on everything. So there is a factorization possible. This function f, this joint probability distribution, can be written as f1 of x1 times fb of x2, fc of x1, x2, x3, and so forth. So it's a simplification. I can represent that simplification by a graph, where these functions fa, fb, fc are nodes, and the edges represent the variables, and a variable or an edge connects to a node if the variable on that edge is an argument of that function. So fc connects to x1, x2, x3. This graph just represents the factorization, nothing else. Now, the most common operation in Bayesian inference and also in variational free energy minimization is marginalization, which means I'm interested in the probability distribution over x3 and not over all the others. I need to sum over all the probabilities of all the other variables. In this case, I would need to sum over x1, x2, x4 until x7. So how many terms do I have in this sum if each variable x has 10 values? Well, it would be 10 times 10 times 10. 1,000,000 terms. But because of this factorization, I can use the distributive law. And some of these functions, like fc, doesn't depend on x4 and x5, so I can move that function basically over the summation sign. We're going to represent now a sum of products by a product of sums. How many additions do I have here? Well, 100, 100, 100. This thing is just a few hundred additions. It computes exactly the same thing. And it's only possible because the graph is sparse, because not every variable depends directly on every other variable. Now, just think of the brain. The brain has 100 billion neurons. And each neuron is, on average, connected to about 1,000 other neurons out of 100 billion neurons. So this is a hugely sparse graph, right? I mean, you cannot almost not imagine a sparser graph than a brain. If the brain wouldn't, or it turns out, let me just say one more thing. These auxiliary, these intermediate products in red, in blue, in green, you can think of that as messages on the graph. Everything that is in red is computed based on FA, FB, FC, which is just the left part of the graph. And this whole computation is just a matter of message passing on the graph. So in the case of a very, very sparse graph like a brain, it would be insane to not use message passing to do variational free energy minimization. Because even if a small graph like this, we go down from a sum of 1,000,000 terms to a few hundred. Now there's more. in message passing, and particularly in Bayesian message passing, what we do. Let's say we have a graph here, and I want to minimize my variational free energy. I want to do my reasoning on this graph. So all these nodes pass messages to each other. We implement this in a reactive way. These nodes are just autonomous systems. They're just by themselves trying to minimize their own free energy by listening to messages from the environment. And each of these nodes is doing the same thing, minimizing its free energy. Which means, yeah, it will send out a message only if it expects that the accuracy increment offsets the investment in computation. Each of these nodes are also energy preserving. Yes, they want to maximize accuracy, but only as much as needed, right? So in any particular time, maybe you just have these amount of messages. And this also goes on in the brain. The brain is a huge model, but it's extremely sparse. And even on this sparse model, at any time, very little computation is going on. Only computation is going on where we have large prediction errors. So in the end, not all of this is working currently in RxInfer yet. But in the end, my speculation is that if we want low power, scalable computations for AI, it's going to be because of the fact that we do Bayesian computations rather than in spite of. The thing about Bayesian computations and Bayesian approach to AI is people agree that on theory it's the right thing to do. But in practice they say, well, but we can't do it because it doesn't scale well. So what we're here to say is that we think that it is because of Bayesian inference that in the long run we can actually do AI computations that are accurate, real-time, and low power and scale. Now, does it work? And it does already, right? RxInfer works. So here is a warehouse navigation problem. There are agents. These agents start in the blue star and they have to carry a package to the red stars. And then there are the obstacles, the blue bars are fixed, and then there are obstacles that just move around. The agent doesn't know about them. So the agent particularly doesn't know about the moving obstacles. So it will just plan by inference where to go, and hey, if it moves an obstacle, it's going to avoid it, because we have built in the model that colliding with obstacles has very high free energy, and the agent is going to minimize its free energy. We will never code what the agent will do. It depends on what he encounters in the world. On the right-hand side is a drone, and this drone needs to follow a moving red star. What we do here is in real time, as you see in the bars below, we just change the world in real time. We change the gravity, the engine power, almost everything that we can change, we change. And the agent keeps following the dot, no matter what. There's real-time adaptation going on here. We didn't pre-program an algorithm. We just said, this is your model. These are the constraints that you have adhered to. Now go out in the world and minimize your free energy. And it works for warehouse navigation, drone control, and we have lots of other applications. The real interesting thing here is if you look at the code that a user has to write, right? What the user writes is basically write a model in GraphPPL, and then at the last line you see infer, do variational free energy minimization. This model is 15 lines. It's not so hard. You just write what are your variables in your system and what are the relations, probabilistic relations between these variables. And this will solve the warehouse navigation problem. We did not write an algorithm to do warehouse navigation. We just say, well, there is some agent dynamics on the top line or the third line. We put in some probabilities for collision, and we set these probabilities very low. We put some constraints on speed, and we say some probabilities on start and endpoint position, and then we just say, now go out in the world, you will receive inputs, and minimize your free energy, and it will do warehouse navigation, and it will change on the spot if the world behaves in unexpected ways. So we're very excited about this, because this shows that you can actually go in one page of code or half a page of code, you can actually set up a model. It's not so hard actually to specify a model. Put it in a drone and just let the drone learn its own behavior. So we started a spin-out from my lab about a year ago, and these are the guys that are involved. So you recognize Albert on the left and Dimitri. And yeah, our goal is to basically a bit what how Julia started. Julia started with this idea. There is this two-language problem. People would say you cannot have the user-friendliness of MATLAB and the speed of C. It's impossible. And what Lazy Dynamics wants to also kind of prove that this idea of you can't have Bayesian reasoning and Bayesian inference and do it fast and for low power. We want to show that that's actually possible. And so we're going to actually build a pro version of ArcGen to basically, well, to help other companies build natural AI systems, right? I'm going to zoom out now, the last two slides. There is this hype cycle that just came out. I mean, it's every year. Gartner is a market analysis firm that plots how they think that interesting technologies will develop. Basically, they say interesting technologies or some technologies, nobody knows about them, then it gets hyped, but the hype doesn't pay off. People will see, well, there are some limitations, so then it overshoots in pessimism, and then there is this return of investment curve that saturates. There are three interesting points on this graph, I think. There is the traditional engineering disciplines here, computer vision. All the way on top, or just a little bit over the top, generative AI, and all the way in the left is first principles AI or natural AI. We are all the way on the left. And how does this compare to the other two? Well, traditional engineering disciplines, control theory, signal processing, computer vision, that's basically from my time, from 20, 30 years ago when I studied, and still in universities, we have these different groups. I'm in the signal processing group. The floor above us is the control theory group. And for us to design systems, well, I have to study a couple of years, learn all the math of my field, and then I can design algorithms, right? It's very expertise driven. The great thing about generative AI is that in terms of investment, well, a lot of the expertise is replaced now by data, big data. And it's a lot easier to collect a big database for many applications than get complete experts in a field, right? So what natural AI will bring to the table is that rather than big data, we automate the reasoning. It's going to be completely automated, right? As a designer, you still have to write a probabilistic model, but it's half a page. You don't have to collect the data because these agents go out in the world and collect their own data. So this is, I think, going to be a step up on generative AI, where you still have this problem of collecting a big database and training on a big database. Finally, this is just an extract from a model of the brain. Somebody drew his model of the brain, and I took a small part of it. And what's interesting about this is, well, our brain is completely self-organized. Nobody wrote this, right? This is the result of evolution. We have about 10 million sensory inputs to our brain. We have 100 billion neurons, and we relay that processing to more than 50,000 muscle spindles, our actuators, right? It's a control system of size and complexity that we will never be able to engineer. Still, the brain doesn't know anything about all our traditional disciplines that we teach in university. The brain doesn't know Shannon's laws, at least not at cellular level, at the neuron level, right? Doesn't know about Bellman's recursive equations. It just does free energy minimization, nothing else. And so I think that in the long term, some of these disciplines are going to be replaced by natural AI. If you want to build really complex control systems, like ourselves, it's not going to be enough to study control theory or to study information theory. You have to build a model, go out in the world and do proper reasoning with the data. Proper reasoning means Bayesian reasoning, and you want to do it in real time, you want to do it fast, low power. That means you have to do variational inference, and to realize that you have to do it with message passing. That's the only way to make it ultimately affordable to do real-time proper reasoning. So, and that's where we want to go with natural AI, and we want to build or make RX Infer the toolbox to support this, this new field of AI, natural AI. Thank you very much.
Thanks, Bert. It was a great talk. Does anyone have a question? Yes, I have a first question.
Oh, can you hear me?
Yeah, sure.
I want to go back to the slide when you compare the kind of the expertise-driven design, then the big data design, and then now the kind of the natural reasoning part. Because I'm just wondering, like, how do you see like the role of the data and the role of the expertise, especially when reasoning is an expensive time given the context? So a very easy context I would like to give is, let's say if you're playing cricket or baseball, and there's only so much time that you can react when the ball comes to you. So in a very high performance environment, if somebody tells you a certain technique, certain expertise technique is going to be helpful, and then a data analyst is telling you what is the probability distribution of this particular pitch is going to give you, that is going to help me as an agent to minimize my free energy a lot. So how do you see all these three kind of things combined together, especially when reasoning is going to be slow, or convergence is going to be slow without the help of the other things?
Yeah, so it's a very good question. The answer is complex, right? In general, you can think of variational free energy minimization as reasoning, proper Bayesian reasoning, and for problems when you have very short time, it may not be enough. So you may not get the accuracy that you need. So then, well, basically you cannot solve the problem. But you can, of course, do what's called amortization. You can learn, learn, let's say, direct consequences of actions if they occur a lot, right? So in a way, and that will reduce the energy consumption. For instance, when you learn how to drive your car, in the beginning, all your predictions are off. Right, you turn your steering wheel, and it's not going to do what you want to do. So you generate a lot of prediction errors, and you need all your brain to process those and learn from it. You cannot even talk to your instructor. Once you know how to drive and your predictions are correct, so your generative model has become correct, I mean, you can drive home, you don't even know how you got home, right? I mean, it's completely almost unconscious. So over time, this approach leads to less and less energy consumption for the same accuracy, and that can be enhanced by amortization, where you actually learn direct mappings from, let's say, sensory inputs to the proper actions. Yes.
It's interesting you go for the driving instructor principle, but would you think that the expertise of driving instructor helps the convergence, or maybe actually leads to a stable convergence of your free energy principle? Or otherwise, in a random environment, if you don't have any guidance, you might converge into something that does not give you the best answer? Do you think that is
Well, it's hard. I mean, let's say we are all a local minima, right? None of us is a global minimum. We are all just minimizing our free energy with our computational budget, and our computational budget fluctuates because, well, if I walk downstairs here, I suddenly have to attend to my walking downstairs, and I have less energy for other things, right? So over time, whatever task you do, you have a completely fluctuating computational budget, and the brain is the brain is constantly busy to basically to control where goes my resources, right? It goes to where the highest priority is. There's no guarantee that you can resolve your task. There's no. I don't think it's the right approach here is to think of, well, do we get long-term convergence of this process? There's too many fluctuations in computational budget, in tasks to do, in interruptions. You do the best you can, and over time you get better because your predictions get better, your model gets better, you make fewer prediction errors, and that's why we well, it's good enough to survive, right?
If you could maybe go back to the slide with the actual model of the guys working running around in the warehouse.
Summers in the Netherlands are fantastic, right?
I wanted to ask, in what sense does the model that you showed the code, in what sense does it encode the movement of how the little stars, how the little arrows are running around? Because
in the first line, we code the movement. Let's say the dynamics of the agent, and the other code is there to the constraints that the agent has to observe, but they are also encoded as probability distributions, so it becomes a large probabilistic model. The idea is this, that variation of energy minimization in a generative model is the only thing going on. If we would just try to predict how the world works, then we would build a model of the world and nothing else. Our brain will be a proper scientist, but we have biases. We don't want to run into collision. We don't want to have collisions. We have speed constraints. All these constraints makes the brain an engineer. It's not, our model of the world is biased. We predict that I predict that my temperature is going to be 36.5 degrees. And by variation of free energy, all the possible processes are called upon to make that prediction come true, right? So we have a biased model. We predict sensory inputs that keep us alive, that are good for us, that are desired, and inference does everything else. But the actual dynamics here is very simple. The thing can only move as a simple, almost like a random walk. Yeah.
What I meant in this. Oh, sorry. I meant in the sense that if, let's say, I wanted to add acceleration to this thing, like how would I go about that? How does this normal with mean and covariance encode the movement?
Well, acceleration is encoded. I mean, x here is a vector of position, velocity, if you will, acceleration, and so forth. So we can encode in this linear equation the differences or let's say a difference of velocity. So it becomes a matrix multiplication.
Hi, nice talk. So thanks, very interesting. In my sector, we tend to use like reinforcement learning for some of these problems that you seem to be solving. So I was wondering, could you comment a bit on like how they are different, where you would go with the one or the other, or I don't know how familiar you are.
Well, there are philosophical differences. I mean, in a way, variational free energy minimization, or the free energy principle, is sort of an umbrella over, I mean, you can see reinforcement learning is a special case, but there are philosophical differences and realization differences. The most important is that in reinforcement learning, in order to determine planning and actions, we actually, it's not a reactive system. You actually write an algorithm for clever tree search. Here, we say, no, there is only variational free energy minimization going on, nothing else. And this variational free energy minimization is implemented in small parts, distributed variational free energy minimization by passing messages. Each message or collision of message carves a little bit of free energy minimization away, and it's completely autonomous and distributed, which means we can also just say, I'm not going to do this one, I'm not going to do this one. And so in the end, we think this approach will lead to a much easier way of online to be able to cope with these power budgets that we have. We don't have this problem of, hey, I'm in the middle of a loop and I get interrupted. There is a continuous process of variational free energy minimization that can be interrupted at any time. So this approach is better for environments where things are not as predictable, where the environment can be very complex. I drive a car and suddenly I'm in a very busy traffic, or very, we'll say very easy traffic. That has a different computational footprint, and this system naturally deals with that. It seeks the most accurate model or prediction for the budget, and it does it in a very smooth way. So I think the way of implementing is a big difference.
Okay, thanks.
Sure.
Here is. Do you want to?
Others.
Hi there, thanks so much for the talk. Yeah, really interesting topics. So I wanted to ask, with generative AI, which you seem to be making the comparison with throughout the talk, it's got this ability to generalize from data. So you feed it data, ChatGPT has a lot of data, it can make generalizations based on the data. From what I understand, and that might not be much, this seems to make generalizations based on the model, and someone has to program the model. So does this mean that you're kind of putting the responsibility of an AI system in the hands of a developer? Like, for example, you had a drone example. If I'm deploying a drone in a military situation, for example, is that drone being based on a model created by some programmer behind the drone?
Yeah. I mean, the Bayesian inference in general is pretty good at generalization, because it will not overemphasize on accuracy, which will be overfitting the complexity term. If I only do complexity, I do underfitting, and so it finds a good balance, that in general. But indeed, you have to program a model currently and say, well, these are the constraints, and you can do, you get data from the environment, you minimize free energy, but you must obey the rules of your model. Now, in biology, our model changes over time as well, under pressure of free energy minimization. Natural selection is free energy minimization over a very long period of time. So we also are interested in working on structural adaptation under the pressure of free energy minimization and adapt the model over time. Because, yeah, if the world changes, you might actually need a new model. But, yeah. Everything at the time, right? So currently not working yet. Yes.
Is it possible for these agents to memorize the wall locations? And if so, where is that information stored?
Yeah, so I mean, they have in the constraints. We basically encode the wall. But I mean, what we do is we give these these agents sensors, and we say, well, if you get close to an object, you're going to feel that object. And then there is this constraint built in. You want to avoid collisions. So then logical reasoning means I'm going to go the other way. That's how it works. So we just assume this is a simulation that it sees the wall when it gets close to the wall.
Okay, so that sounds like bug pathing then. Like, let's say as a programmer, I want to deploy these robots to a warehouse, and I don't know the warehouse floor plan. I don't want to deal with that, but I know that the pillars in the warehouse are going to stay in the same place, and these robots are going to be there for years. Is it possible for me to write 15 lines of code that then has the robots themselves will end up figuring out and remembering where the walls are, kind of like a Roomba would?
Yeah, in principle, yes. I mean, free energy minimization goes over not just over states, but also over parameters of the model. So in principle, you can just learn the model over time, and then it becomes hard-coded in the model, and so it would know this, right? Absolutely. There's nothing that would, and that would currently work. In RxInfer, we can do, let's say, state estimation, parameter estimation, just not yet the structural adaptation of models.
We have room for one more question there.
Yes, I have a follow-up question on that. So these robots, will they actually get better at warehouse work as time evolves? And is that state saved somehow so that they will do better also in a new warehouse?
I'm sorry, can you quickly repeat the question? I didn't see where the sound was coming from.
Sorry. Yeah, so the question is if these robots will get better over time. For example, bring the package more quickly, and if they will also be better than an untrained robot when they enter a new warehouse.
Yes. I mean, if your hardest constraints are bring the package, and you make everything adaptive, that it will get better and better over time. First at smaller timescales, just Kalman filtering. It will do Kalman filtering, although it's not aware it's doing Kalman filtering. Then parameter estimation, and then hopefully at some point structural adaptation. It's the same thing as like throwing water over a mountain, and it just, with all the rocks and whatever, it just goes zigzagging its way down. And if you come back 10,000 years later, is going straight down, because it will remove the obstacles if it has just one task. So if you just say you have one task, bring the package and no collisions, and everything else is adaptable, then yeah, it will learn the parameters and hopefully at some point learn the proper model. Yeah.
Thanks, Bert.
Sure.
It's a great talk, great discussion. Extra round of applause. So our next talk will be after a short break in 10 minutes. And I want to remind you that we have headphones, just in case if you want to reduce some noise. They are really great. So use headphones if you are bothered by the noise. Rassos. So hello everyone. So our next talk is from Morten, and the talk is going to be about emulating Julia code evaluation, and Morten is going to talk about package called code evaluation.jl.
Cool. Audio is working. So yeah, basically I just want to talk a little bit about some housekeeping work I've been doing in the documenter.jl package, which if you're not familiar with documenter.jl, it's the package that you can use to generate the documentation websites for Julia packages. The Julia manual, like a lot of Julia packages use it, the Julia manual is generated with it, and so on and so forth. And the aspect I want to focus on today is the parts where Documenter actually can take and evaluate arbitrary Julia code that the user provides in the documentation. So to explain what I mean by emulating Julia code evaluation, so Documenter has this feature which is, so in general, in a Documenter, the inputs are markdown files, and within a markdown file, what you can have is a special code block which you tag with an add example. Within the code block, you can have arbitrary Julia code, and the Documenter will find it and will actually evaluate the code for you. But the code does not end up in the sort of terminal or anything like that, or the output, I mean. It is actually able to capture all the output and splice it into the final product, like the HTML or the PDF document that it generates. So the question what I really want to answer is how does that actually work? What is worth noting is that Documenter is by no means the only package in the ecosystem that does something like this. There's a whole set of what I would call documentation generation, or so document generation packages. So for example, Weave has this, which is for report generation, has the same thing. There's a code block and it will evaluate it. Same thing, Franklin, which is static site generator, can do it as well. So it's not specific to Documenter.jl at all. But okay, now let's imagine that you want to write this kind of program, Julia program, that will, has to evaluate arbitrary Julia code. So what are the sort of requirements? What do you have to think about? So first, you need to be able to parse and evaluate the Julia code. That's because the inputs will be from a markdown file or something. So after you have parsed those files, it's going to be just a string of bytes in your data structure or whatever you have. So to actually evaluate it, you first have to parse that, and then also somehow convince Julia to evaluate that within the same process that is already running your code that is parsing the whole thing and building the whole document, right? So that's one. Second thing, this might not always be a requirement, but it is a requirement for Documenter, which is you want to have a clean environment for each separate sort of execution of code. That is because, if you imagine your for example, your documentation is probably going to be made up of multiple pages, and each of those pages is going to, might have a bunch of add example blocks. You don't want variables and stuff and function definitions and all that kind of stuff from one page to sort of leak over and interfere with the other page. So every time you evaluate one of those add example blocks, it needs to look as if it is within a clean main module, but there is only one main module in Julia. So how do you do that? We'll get to that. And last but not least, output capture. So we are evaluating arbitrary Julia code, which means that code will likely print stuff into the terminal, have logging macros, uses logging macros. Normally this stuff ends up in in the terminal or maybe in your CI logs or that kind of stuff. We also want to capture that. So that's the third thing you need to think about. The good thing is, Julia has all the basic building blocks to actually do all this very easily. The issue there is, it is just slightly non-trivial to get it all working correctly, which means, in my mind, it is worth having good abstractions and good interfaces at this level, and have a little bit of code reuse. So this is where we come to the actual packages that I put together. That do this, and so the motivation really comes from the Documenter use case, but I hope that they're also useful for the community, more broadly. Something I do want to mention here though, like all the ideas that I'm about to show you and like the implementation, a lot of that has been done by other people and like has existed in Documenter for a long time. So Michael Hatherley, I think, would be like the author of a lot of these ideas, and then a lot of people have sort of added bug fixes over time. So I just want to acknowledge all the work that others have done, and I basically just put a nice, like I've just made it a little bit prettier. That's my contribution here, so I just want to acknowledge that. All right, so going in reverse order. Output capture, how do you do that? You can use iocapture.jl. Julia actually offers these functions called redirect std out stdr that allows you to take control of the standard output and the standard error streams in your Julia program. You can basically redirect all the standard output to a different stream or into a buffer or something like that. When it comes to the logging output, you can also use custom loggers for that. But as I said, like, it is actually slightly non-trivial to get that working. The naive implementation using like redirects std out will likely hang your program often because some buffer gets filled up and like everything hangs. So in iocapture.jl, it's a pretty tiny package, but we figured out some of these edge cases. And so you can just do this, where you have this do block syntax, and any code that executes within the do block, any output from that code is going to get captured. And what you get back is a nice object where you can access like the return value and the captured output and so on and so forth. I do also want to mention there's an alternative package called suppressor.jl, which basically works the same way, does the same thing, has just a different sort of macro-based syntax. So do want to plug that as well. 2. For the clean main environments, what you can do is anonymous modules. So in Julia, you can actually construct an empty module using the module sort of function call. I don't know what it is technically. And then you can start evaluating into that. What requirement you have is, so if you want to make it look like main, you also have to do some additional tricks because like the module is gonna have a random name, and actually when you're evaluating into main, like in the REPL, like you get stuff like the ands variable gets set and that kind of stuff. So core eval by default doesn't do any of that for you. So the evaluate function in code evaluation sort of takes care of all of these things. And code evaluation in general offers you this interface where you can just construct the sandbox, which is this thin wrapper around the this anonymous module, and you can like have as many as you want, and they're all more or less independent. Something that is worth noting here is there are limitations to actually both of these things, so including the capture. If your code is doing a lot of like stream, like mucks around with the streams a lot, then things may break. It's not perfect. It's a bit of a hack. Same thing here. Like if you're messing with the global state of Julia or something like that, that will leak over. So it's not perfect isolation of the environments, but it is good enough for sort of 99% of the use cases that say Documenter users see. So it works. Lastly, the way I've envisioned code evaluation.jl right now is like there's going to be also a bunch of like higher level functions that can handle like different ways you might want to evaluate Julia code. So there are 2 things implemented in there right now, which are very much Documenter.jl use cases. In one case, you just take a bunch of Julia code and just evaluate it. The only other thing it does, it basically parses that string into the expression first, which is very easy to do in Julia. There is also a function that just parses strings into Julia expressions. So the other one is a little bit more sophisticated. It can actually emulate like a REPL session for you. And I imagine like there could be a whole library of these functions. So all in all, packages are up in the Julia Docs organization. So if you're interested, please do get in touch or check out how they're implemented. They're actually really tiny packages, so they should be very accessible for anyone who's interested in how they work. So yeah, that's all. Thank you.
Round of applause. It was a good talk. So in the interest of time, we have to proceed with the next speaker. But Morten will be here, and if you have questions, please approach. And the next speaker is Niels. And the talk is going to be about building a customized application dashboard with Pluto.jl. applause for our speakers.
So, good morning and welcome to my talk. Oh. Okay. Today I will be talking about building a customized application dashboard with Pluto.jl. First, I will briefly introduce Pluto to those who don't already know Pluto. I'll talk about what our motivation for the dashboard was, previous efforts, what our approach was like, how we built the dashboard, some limitations we came across, a working example, and the future of our project. So first of all, what even is Pluto? Pluto is a notebook environment for Julia, which enables interactive development with live updates and dynamic visualizations. It has a reactive execution model, which means that cells automatically re-evaluate when their dependencies change. In the image, you can see a Pluto cell with some code in it at the bottom of the image that creates a plot. And the plot is then getting shown at the top of the image in the output of the Pluto cell. So we wanted to create a dashboard for Pluto to demonstrate a package using this dashboard in an appealing, convenient, and interactive way. So it's usable for everyone and not only for people who can code, like normal Pluto notebooks. It is, our main goal is that it should be easy for developers to show off their hard work, while also being accessible for everyone to target a bigger audience. There also has been previous work in the past, first being visualization dashboards with Pluto by Guillermo Gomes-Hettinger, which creates a dashboard by using Pluto's isolated cell feature and Pluto dashboards at Excel, which makes cells movable to create a dashboard. It's important that those projects have different approaches and are independent from our own project. So how does our approach even work? First of all, as we've seen in the first image, when we put some code in a Pluto cell, it gets shown at the output of the Pluto cell. And we can also put an HTML string into a Pluto cell, and it's then getting rendered at the output of the cell, as we see in the image below. We can do the same with JavaScript. We can just insert a script tag into the HTML string. And you can see in the image that I've put an alert in it, and the alert is then getting shown at the top of the screen. Now that we can use JavaScript, we can also add style or link tags either to the head or in the image below. I just put it in the HTML string. And we can use that to load CSS frameworks or add our custom styling. In the image below, I've loaded Bootstrap. You can also obviously use the integrity tag, but that would be pretty long for this example. And you see I am red and I am blue. And those are red and blue because I used the Bootstrap utility classes. So now the most important part, but also kind of most techy part. How do we create a connection between Julia and the browser so we can use JavaScript from Julia? First of all, we create a Pluto cell that contains a text box. We can see that in cell 3, down here, if you can see my pointer. And then we have a function to handle the text box value. The text box value is just a variable here that holds the text box value. And when we modify the text box value with JavaScript, so basically we just write something in here. In this case, it's hello world. It triggers the handler function to run because, as I said earlier, Pluto is reactive. And when the text box value changes, this cell gets re-evaluated and is, well, obviously calling the handle text box value. And the handler function calls the desired function that we wanted to call. In this case, it's, well, just a static string, but it can obviously also be a variable depending on a text box. And it returns its return value. So in the end, the return value can either be a HTML string, so HTML or JavaScript or even CSS, or a primitive type. Now we can assemble all those things, and this allows us to render custom HTML code wherever. We can either have it as output of a cell, or just move it below the body with JavaScript. We can also resize the whole notebook, or just hide it, so it won't look like a Pluto notebook anymore. We can load custom CSS frameworks, or use our own CSS to make styling everything easier, because CSS frameworks are nice to do that. We can also create interactivity with HTML components, like a button or text box or dropdowns, and JavaScript. And as we've seen in the last slide, we can call Julia functions from Java. We can call Julia functions from JavaScript and get their return values. And since it's still a Pluto notebook, we can give advanced users the possibility to write Julia code in traditional Pluto cells, so we can embed Pluto cells in our HTML, and much more. Only creativity is the limit in this case. There are still a few limitations we came across. First being it's not really generalized at the moment, so it's a high effort to create a new dashboard. Second being there's no implemented function to move Pluto cells, so they need to be moved manually by the developer with either CSS or JavaScript. And there's only a single user capacity, because right now it's not possible to host such a Pluto dashboard on a server, so only one user can use it at the same time. So in the end, you just git clone it and then use it. Here we can see a working example. As you see, it doesn't really look like a Pluto notebook, or if you are also familiar with Jupyter, it doesn't look like a notebook. And we can see at the top, there's a few HTML elements, like a button and a dropdown, where the user can input some data, and then the user can plot this data. And overall, this is way easier for people who can't code, because they, well, don't have to write code. They only have to put some values in there, and then they can try the library. This is also pretty interesting, because we can see some data. Each row is basically one Julia object that we fetch with JavaScript from Julia, from the running Julia process. And there's also a few buttons to change these values. And all of this is written in HTML and JavaScript for the interactivity. And we only fetch the values from Julia. On the last image, you can see Pluto cells. And as you can probably see, they look quite different from Pluto cells, because I've changed the design. I'm not a designer, but it still looks pretty okay, I guess. But yeah, for advanced users can just write some code in it and play with the library. It's also possible to add more Pluto cells, but yeah, those are sufficient for now. So what's the future of this project? Right now, the project is just a proof of concept of Pluto dashboards. We were just playing around to find cool features, and we were exploring possibilities coming from JavaScript, HTML, and CSS. And right now, we are working on a generalized approach, tackling the limitations. First being that we want to be able to move cells easily, have a more reliable connection between Julia and the browser, because right now it looks cool, it's hacky, but using WebSockets is way more robust and scalable. And last but not least, it should be easy and convenient for developers to create a dashboard, not only for users to use it. So our primary goal of the project is to give developers a toolbox they can work with to make Pluto dashboards. A thing at the bottom, you can see the GitHub repos. If you want to, you can test them out, but I would only recommend testing out the first two, because that's the project that you've seen on the big images. The last GitHub repo is the interface that we are currently developing, and it's, well, yeah, not really usable at the moment. Thank you.
Thanks, Neil. I encourage everyone to try it out. Thanks. In the interest of time, we have to proceed with our next speaker, but catch up with Niels later for more questions. So our next speaker is Keith from Siux. It's a very successful company from Eindhoven, and I know that they use Julia. And Keith's talk will be how Siux actually enables Julia in production, and how do they use Julia in a real-world environment. So a round of applause. Oh. Keith, the stage is yours.
Is it working? Yeah. It's very brave of you to brave the cold and the wind and the rain to be here. So yesterday we had Tom and I from Siux organized a mini symposium, which was very serious, very much about what we need to get Julia going in companies. Today I want to keep it light, and I want to keep it light by starting with a simple question: why are we here? All right, this is a very simple question, often pondered, and I don't want to get into the philosophical why are we here. I just mean why is Siux here, right? So a lot of people here are presenting packages. A lot of people are companies centered around Julia. We are none of that, right? We are a service provider. We are a high-tech service provider, and we are kind of involved in the whole chain. If you want to make a product, if you have an idea, but the idea is not quite right yet, you can call us. If you need to develop some software, you can call us. If you need to have it put through an assembly line, you can call us. We do the front-end thing. And I'm actually, and Tom, from the mathware department, which actually started out at the university, and we used to be called Lime. That's why we have this little mascot here. And we have a and we were incorporated into Siux, right? So we became part of the bigger company in 2011, which has widely been regarded a good move, and it enables us to really cooperate with the rest of the things. And our portfolio is centered around these different competences we have. And if we look back at this, oh, yeah, something's gone wrong in the animation there, but this thing, we tend not to get involved in this kind of final stage. We're at the beginning stage, right? So we're looking at agreeing an assignment, doing some pre-studies, some proof of concept stuff. Usually when it gets to an alpha release, that's when we say, yeah, this is as far as we go. This is the end of the road for us. For the mathware department anyway. So that might give you an idea why we're keen on Julia, right? So we're interested in this ideation stuff. It's kind of the Julia ecosystem. But does it really explain why we hosted the meetup in January last year? Why we created this 200 person strong Hot or Not event April last year? Why we sponsored the JuliaCon? Small disclaimer, none of these people have anything to do with Siux, but I love this photo. And why we're modestly sponsoring this conference, right? I mean, it might seem that we just love Julia, right? And that's, but there's more to it than that, right? It's not, we're a business. We have to make business. And the reason that we're so keen on Julia, I want to explain with a kind of surprising example. So in a moment, you might be very shocked. Actually, you guys might be shocked already, so I'll start with this. This might already shock you. There's a little MATLAB logo there. Okay, is everyone still fine? Yeah, everything's still fine. But this is for one of our customers, and they have a machine which has to do some calibration once a day. And this takes on the order of a minute. And I think, well, could we do something useful during that minute? But fine, okay, a minute, we can just about live with that. But now they're making a new machine where they've predicted that they need to do this action every 15 minutes, every 30 minutes. And then the projection is that this machine is going to spend a lot of its time doing this calibration rather than doing the useful thing it's meant to be doing. I'm being a bit secretive here, sorry, but we can't share too much customer information. So this was a projection. Well, customer would not be happy if this would happen, so they asked us for some help, right? And so, how do you make MATLAB faster? So first of all, we wanted to create this, right? We want to make these lines nice and thin that the machine is still doing the useful thing most of the day, and they would be happy. And of course, we did this with, sorry, everything still okay? MATLAB Coder. Yeah. This was the choice that was made maybe outside of our control, but it's also something we have quite a lot of competence in. So we said, yeah, fine, we'll do a MATLAB Coder, that's fine. We'll also help you along with some how to set up your Git properly, include some proper documentation of the release strategy. Okay. So now you might be wondering, why am I telling you? Why am I telling you this, right? That's a valid question. The point is that what we're doing here is something that's fundamental to the reason why we think Julia is good. What we're doing here is we're helping the customer. For some reason, this is charged in nautical miles, but we're helping the customer get to some point on their roadmap this year, right now. Right now, they're happy. But next year, their roadmap is going to want to be there. And we want to make sure for our customers that it's going to be easy to get from this point to the next point. And if we give them something that's very closed and difficult to work with, they might be happy now, but next year they will not be so happy. Okay, you could say they'll come back to you again and ask you again, but then we have a lot of work. And we don't want a lot of work, we're lazy. So the important thing that what we've done in this case with MATLAB and Coder and giving them a proper Git strategy with some documentation is we've made it possible for them to keep iterating on the improvements, or for ideally, of course, for us to iterate on their code. But again, to continuous improvement. This is something that I've dubbed an open deliverable. I've invented a new word. I'm very proud of myself. And the O is as in, everyone familiar with the SOLID principles? So SOLID is 5 software engineering principles that are it's an acronym, or it's a bit far-fetched. So the O is maybe the worst one, because the O stands for open/closed. So the O stands for half of something but the O means open as in open for extension. So the thing you write in software should be open for extension and closed for modification. But our deliverables should also be open for extension. And this means when we deliver something, it has to be workable. And workable means it has to be workable by the people we're giving it to, it has to be workable with the tools they have at their expense, and it has to be workable within the time that they reasonably have. And this kind of fills into something that, to me, was a bit of an eye-opener the first time someone said this. It's probably Uncle Bob who said this. But software must be soft. That's why it's called software. It's meant to be malleable, changeable, updatable, whatever. You should be able to do stuff with software. And to further labor the point, I got my kids involved, because that's why you have kids. And I asked my son, 6-year-old, to build a tower out of blocks, and he built this tower. I said, yeah, that's nice. And this is what I would call a very non-open deliverable, very closed deliverable. Just imagine trying to change anything here. You don't really know when it's going to collapse entirely, or what's useful to the construction, what's not. If you look carefully, you can even see the top blocks actually leaning against the wall. So So I asked my son to do better, because that's what a real parent does. No, I'm not what I mean. So I asked, well, maybe we should use this other toy we have, right? And here we have a lot of nuts and bolts, and we built this tower that's sturdier, and it's you can change it, right? You can unscrew some stuff and screw it back together again, but you do need some tooling. So then, of course, in the end, we always get down to our favorite toy, which is Lego, in this case Duplo. And we built a similar tower, but this one's really easy. You can just take it apart, put back together. You do all kinds of stuff with this. And I think, by analogy, what is our favorite toy in the room? Julia, of course, yeah. Yeah. So, if Julia is our favorite toy, can we do the same thing we did with MATLAB Coder with Julia for our customers? So I'm going to take you through some cases. I hope this isn't too salesy or braggy. Actually, it's not that braggy, because the first one we didn't actually, no. So this is for ASML. I am going to mention who this customer is, because this is, it's not a secret that ASML is doing Julia. And they have this inner source code base, right? And inner source is a bit like open source, but within the company. So it's software. And I'm not sure if you're familiar with the onion model. There's this notion that when you build software that you try and keep your object model, so your representation of the truth, very central, and that doesn't depend on how you're using it, but how you use the software depends on the truth and not the other way around. And the inner source tends to be centered around this middle. And this is actually one thing where I think the Julia package manager already really helps, because it makes it a lot easier to have different packages hosted by yourself. This code is shared by many different developer teams, and the goal is to get the quicker time to market, right? So this will pop back again. You can do almost anything with any tool. But with Julia, the idea is that if someone has a cool idea, they can type it out, someone else can modify it a bit, and then you can create an application, which should be quickly, so your customer is happy quickly. I think this is actually one of the key concepts that's driving Julia at ASML. A second case is something that we have in-house. This is Siuk's most successful asset. So this is a piece of software we own that we sell to many different customers, especially to people who are shipping expensive stuff and shipping it fast. Like medicine is often shipped by air because it has to arrive fast because it can't stay too warm for too long. And then if you're traveling by air, you have to pay by volume when you're sending something, not like the typical Bol.com or Amazon order where you get this huge box with this tiny thing inside. Here we're really trying to pack the box as tightly as possible. And we have this thing that actually consists of two parts. It says, given a box, and the items, how do I stack them? And then on top of that, given the items, which box should I choose? And we have this in Java, and it's awesome. Definitely, if you're in this kind of situation, anyone here, check it out. Cubic Select, Districts is the product name, or Siux. This is the thing you want. But here again, we have this problem. Our customers are annoying. Well, not really, but they do have a lot of wishes. And different customers have different wishes. And sometimes these requests can be really urgent, right? I don't think it really happened, but this example, but imagine there's some new vaccine out and you want to ship it around the world quickly and efficiently. Maybe you suddenly have this need for something new, right? We have a lot of interesting stuff. Like most things are modeled as boxes, but occasionally you have something that's actually like a plastic packaging, and you can stack them in a different way, and you might want to use that. So lots of stuff is going on here. So we decided, well, of course, what we want to do. So the risk we run is that the number of features the customer desires is we can't keep up with what we deliver. So we thought, well, for faster prototyping ideation, tiny subtle changes between this animation. .jl. We created our own Julia version of this to do some rapid prototyping. We did accidentally introduce a two-language problem. But I hope to solve this by eventually killing the Java implementation. But that's a long way down the road. But this is I'm very happy with, because the Julia code that has been written here by a colleague of ours. It's actually really a nice playground for new people starting with Julia, in our company anyway, because it's proprietary, of course. Then the next problem is about a very complicated machine. Again, not naming the customer. I've used this example. This is one of my favorite books, also one of my son's favorite books. It's about a very complicated machine, and in this case, we're trying to optimize. So this machine has lots of nuts and dials and stuff you can twist and adjust. And you also have you have a high-dimensional actuator space and a high-dimensional target space. In this case, the machine is trying to pick elderberries off trees, which is also quite difficult. And there's these equality and inequality constraints. And again, here, importantly, there are tight speed requirements. This has to be fast, right? We're doing this online. Something is happening in this machine, and it's happening really fast, and we have to keep up with our optimizer. And then during a presentation about this, a colleague of ours showed this slide. So this is a blatant steal of his slide, but I think it really illustrates well, at least it's a starting point, what is so great about Julia. This is right, preaching to the converted here, but what it allows us to do is we can, well, I'm not sure which one you start with, but that's the whole point, I guess, but you can increase your model complexity and then make it faster. And then once it's fast enough to work with, you can increase the complexity again. And then you get this kind of picture where you go from left to right, from not many features to many features, and bottom to top from being slow to being fast. Every step to the right is adding a new feature, maybe at the expense of being a bit slower. And every step up is saying, hey, I have this new feature, it's good, I need it to be faster, and then you're implementing it. I'm going to also nicely join in on Michael's bunnies and cheetah. So I'm not sure if anyone attended yesterday's talk by Michael about the 1.5 language problem. If you didn't, go online in the break and watch it. Bunnies are the naive Julia implementation. A lot of allocations, a lot of accidental, type instabilities, that kind of stuff. That's what the bunnies are doing. The cheetah is writing alloc-free, immutable, or writing the super fast Julia, right? And there's this trade-off. And what I think is essential here is that in many other languages, you could have the dots at the bottom right, or the dots at the bottom at the top left, right? You could have those four or those four. So if you're doing it pure Python, not that anyone ever does anything pure Python, you would have these 4 dots. If you're doing it in C++, you would have these 4 dots. Because what you're doing down here is probably not even feasible code in a strict language. And this is why our colleague, who, I won't name him, a different colleague to the one who was on the slide, his name's not anywhere. I don't like Julia, but I have to admit, for this project, it is the right choice. And this is kind of good. So if you have competent people saying this, because he's, I think, our most competent software engineer in the department, it means there's something good about Julia, right? It also suggests that the reason he doesn't like it means there's still a few things wrong about the newcomer experience to Julia, but at least we're really showcasing here that the language has a lot of value. Yeah, so these are, if you were to use C++, you'd probably have to somehow make those purple line jumps, which is probably impossible. Another benefit is if you use Julia and your iterations are faster, instead of doing this during the week, you start off your week like this, you continue your week like this, and by today, you're done. So you could all start taking your favorite hobby, which in some of us cases would be solving a Rubik's Cube. If you do like solving Rubik's Cubes, we have plenty of them at our booth. And the final case is, I'm sorry, I have to be really secretive here, so it's just called suspended droplet CFD, top secret, which is a case where they're doing some simulation in star CCM. Post-processing has been in MATLAB, and that means manually discretizing ordinary differential equations and then slow time stepping in the order of minutes, maybe towards a half an hour kind of time. And of course, that's no good, so we got in Julia, time integration automatically via Chris Rokokas's awesome SciML stuff. Or not SciML, what's I don't know what the exact name is, but it's done automatically and it's razor fast. Just takes seconds. The customer's blown away. So we're managing to build these bridges between what we're doing and our customer's roadmap in Julia. Okay, I am running out of time already, but the thing I'm actually more proud of at the moment is not the fact that we're building these bridges to our customers' roadmaps, but it's the internal bridges. So I started off this talk about CUX and the mathware department. It's a happy marriage, I think, but we're a bit disconnected sometimes, and I think it's fine for us to do our own thing. But at the moment, Julia is really turning into be something we can gather around. Wait, I'm going to skip this, right? So the mathware department, we have these kind of, this is our core, right? We're about algorithms, about doing stuff fast. And the software department is about maybe the more serious, long-term way of working. But we're really finding each other in this Julia language because we can both work on it. We can both do our thing together. So a few weeks ago, Tom and I gave a course with the package called forsoftware.jl. This course is called Julia for Software Engineers, which was a good clue to whom we were attending. And at the beginning of the course, we asked these people, yeah, what is your favorite language? So we got C#, a lot of C#, we got C++ and Java. And we hope to have convinced them, well, I know we've convinced them to also think about Julia, because, well, so Johan back there is one of the software engineers who took this course, and now he's here. Yesterday we had 2 others here, and on Wednesday there was another one, so it's definitely working. We're indoctrinating people successfully. The course is much appreciated. To name some feedback, a practical, well, this is really bragging, but we also had a colleague who said this, it is quite useful, which I think is the nicest compliment. And why I really like us getting together as software people is to kind of break Conway's law. So instead of these separate teams working in their silos in their own language and having this real disconnect between what you're doing and the final product, we can move towards a situation where as a team, because you're using the same language, you're all working on the same thing. You can really see how what you're doing is connected to what the others are doing. And I think we're already experienced this in some of our projects. That brings me on to our conclusion. So this is not really a conclusion of my talk, but I think something people need to realize maybe a bit more about doing software development in the real world is we're always aiming at a moving target. Our customers want to increase their roadmap, or they want new features all the time. They're a bit annoying in that sense, but they do pay us, so we're happy. And what we want to do via Julia or other ways is to be agile by having these open deliverables. We want to have faster product iteration. Again, Julia an ideal tool. And we see Julia also as a way to create stronger teams by having people more bonded together about things. I'm going to leave this up and take any questions if there are any.
Thanks, Keith, for a great talk. Do we have a question? Do we have questions from the audience? Okay, well, people are thinking. I have a question. Yeah. So, this colleague of you, why he didn't like the language and why it was actually the right choice after?
So why it's the right choice was because I think he also sees in any other language you wouldn't be able to do this combination of where you're iterating, and during the iteration you already have to know that it's going to be fast. You can't just develop something new and hope that after someone else has translated it, that it's still fast. And the reason he doesn't like it, I think, is for, I think maybe it being a bit too dynamic for his liking. There's some things he really misses, maybe. I think he mentions a few times, like, functions have a type, but not a type that bounds them to their input and output argument, signatures, something like that. And in general, I think also we may have let him loose on Julia a bit too much, and he started to do his own thing, and maybe he didn't quite follow the idiomatic route, which has caused him some pain as well.
I see. And like, how big is the team that uses Julia in CUX? It's only about 6 or 7, I think.
there's quite a few people who have used Julia, but it's not a continuous thing.
And what is like maybe the biggest challenge to convince people to use or to try a new language?
I think it's the newcomer experience. So within the mathware department, we're centered around a lot of Python, and we use MATLAB a lot because our customers sometimes have it as a requirement. And there, when you get started, everything's really easy and really friendly, and the internet is full of tools on how to use it. And when you get started with Julia, there's a few roadblocks. I definitely want to recommend Michael's talk because he mentions the survivorship bias as well, which is a problem. Us here, we don't know what's killed off the other guys who aren't here. Right? There's a lot of empty seats, and they could be filled with people who, for some reason, have given up on Julia.
It's funny that you mention it because I wanted to have a follow-up question. Like, in your opinion or experience, what would be like the key thing that Julia needs to invite more newcomers, to become newcomer friendly? Maybe
yeah,
it's like
I find this hard to say. I feel like I feel like the IDE might be one thing. There are some things that are a bit missing there, maybe.
Anyway, thanks for the great talk. Extra round of applause. So our next talk will start in a couple of minutes. So yeah, we have a small break, 2 minutes. So hello everyone. Our next talk is from Joe. It's called Molly.gel. So as you probably all know that molecular dynamics is an extremely difficult environment. That is extremely complex dynamics and also very big, like a lot of interactions happening. And I hope that Joe will uncover how Julia enables those kind of simulations of molecular dynamics.
Thanks very much for the introduction, and thanks for braving the weather to be here today. So this talks about a package which I started development of about 6 years ago now as a way to actually learn, to be honest, learn Julia. And since then it's grown steadily, and it's been a kind of major development focus for the last 2 years or so, because I use it in my research. So what is molecular dynamics? Well, you basically set up a physical system, which means you place the atoms in space somehow on your computer. You define the rules of how the atoms interact, and then you press play, basically. And pressing play means that you do numerical integration using Newton's second law of motion, F equals ma. And this is often very computationally expensive because you have to do one step after the other. There's really not very many shortcuts. I work with biologists, and MD has had many successes in biology. And it's also had uses across materials, across chemistry. It works very well in combination with experiments. So when you kind of use experimental data to validate, and then you make predictions that experimentalists can test. And as we look towards the future, we have kind of more and more compute resources. We have all this amazing machine learning, and better protein structure prediction means that these methods are just going to continue to develop. So for example, this isn't my work, but this group simulated a protein. So there's two views of the same protein here. And you can see on the bottom of the time scale, they're kind of getting up to half a millisecond of simulation. And you can see the flexibility, the dynamics of the protein, and they make, in this case, a Markov state model to look at how the different states are populated throughout the simulation. And this can obtain biological insight that you just cannot get via experiments. Another example from DE Shaw Research, so they have this amazing purpose-built hardware called Anton, which allows accelerated molecular dynamics. And you can see here the SARS-CoV-2 spike glycoprotein, which is a large protein complex where some residues are glycosylated, so they have kind of sugar groups attached, and you can see those vibrating around. And again, this kind of gives us insight into how these proteins work. So where has it been successful? Well, if you want to fold small, fast-folding proteins, you can just about do that. So this work on the right, again from DE Shaw Lab, it's quite old now, but they show that you can simulate these small proteins and they adopt the right structures. You can commonly use it for mechanistic interpretation. So why at an atomic level is my experiment showing this? And you can kind of have this feedback loop between experimentalists and computational people. You get atomic level resolution at every single time step, which is something you just cannot get with experiment. And in the last few years, binding free energy methods, so that's where you have, for instance, a protein and a small molecule ligand, and you want to know how strongly that small molecule ligand binds, and that's become useful in pharma. However, it's not all rosy. At the critical assessment of protein structure prediction kind of competition, which is run every 2 years, MD has fairly consistently failed to predict the structure of kind of actual proteins of the size that is interesting. Disorder proteins, which don't have a fixed structure, they flop about, are too compact in many force fields. So in the bottom right here, you would want the molecular dynamics simulation to show something like the orange, and it actually shows a compact blue structure. If you want to do enzymatic reactions, you can't use classical molecular dynamics because bonds can't break, and so you have to use QMMM or pure QM simulation, which is much more expensive. And really the key concern is whether your question of interest can actually be answered on the timescale available for study. And often the truth is it just can't. So recent developments, well, Moore's law is kind of holding in the GPU space, and so the available simulation length is going up and up. Software is continuously developing. It's basically to make use of that GPU and kind of larger clusters, larger numbers of CPUs. Force fields have been steadily improving, as you can see on the bottom right here. This is kind of recent work in force fields to apply to all sorts of biomolecules. And I'm obviously mainly focusing on the biology case, but that applies in materials as well. Free energy perturbation methods, as I said, they're now becoming an actual part of the pharma pipeline for lead optimization, used by all the big pharma companies. And AlphaFold, which some of you may have heard of, has dramatically increased the number of proteins which are available for simulation, which is really useful as well. Probably the biggest development of the last few years has been machine learning potentials. A lot of work has shown that neural networks are able to give quantum level accuracy, but at much faster speeds, 3-4 orders of magnitude faster. Typically, these methods are trained to match forces and energies on high accuracy quantum data sets, and they do often show issues on larger simulations when you go out of domain. The field is addressing these problems along with things like long-range interactions and the performance, which it's probably always going to be worse than classical force fields, but it's getting faster and faster. So these are really promising. They're not immediately applicable to larger biological systems, but there has been some work, for instance, shown on the right here, where that has been done. So what software is available for molecular simulation? Well, there's a number of excellent, really, really mature packages. I've shown some on the right here. And these really are jewels in the crown of academic software. These have, GROMACS, for instance, has been in development for many decades now. Arguably the largest and most used piece of academic code. Heavily optimized. They write routines for low-level routines for different architectures. I think at some point they thought the square root function was too slow, so they wrote their own square root function. That they're really, really focused on performance. And most of these packages work the same way. They have one or more kind of fast kernels that run the simulation, whether that be in C or CUDA. And then they have some layer on top which you can interact with. So for instance, in the case of GROMACS, it would be a binary, or OpenMM would be a Python interface. And that means that most packages are hard to interact with all the way down, because at some point you run into this kind of two-language barrier, if you like. And no mature MD package has support for differentiable simulation, which I'll describe later, but basically means taking gradients through the simulation itself. So what is Molly? It's a pure Julia implementation of molecular dynamics, one language all the way down. A simulation script is just a Julia script. In terms of design, it's closest to OpenMM, which has, as I said, a Python API, and then but has multiple kind of compute kernels under the hood. The key kind of defining concept of the package is that if you define a potential as a user or a simulator or a logger, it should be easy and it should be just as fast as the built-in features. And that really matches the Julia language itself, where the standard library is largely implemented in Julia because it's fast enough. Everything is defined imperatively. It's just code. There's no kind of config files or anything. And currently, in terms of kind of correctness, it can simulate proteins with the trajectories matching OpenMM. And it's differentiable using a combination of zygote and enzyme. And the gradients match numerical gradients. So just a quick rundown of the features available. You have the fairly standard non-bonded interactions, Lennard-Jones, Coulomb, gravity, etc. You have the bonded interactions, so harmonic bonds and angles. You can read in kind of OpenMM and GROMACS force fields, and any coordinate files supported by chem files. Yesterday you heard about the amazing atom-space interface and the atoms calculators from Rachel and Michael. And so you can, the systems in Molly implement the atoms-space interface. You can use atoms calculators in Molly, and you can also use Molly as an atoms calculator. Flexible simulators like Valet and Langevin, steepest descent minimization and thermostats. Also, we have one barostat at the minute, the Monte Carlo barostat, and variants of that. You can simulate in a triclinic box. You kind of have flexible loggers that allow you to track arbitrary properties throughout the whole simulation. We have various neighbor list implementations, including cell list map. At this JuliaCon, I heard about 2 new neighbor lists. One is spatial hash tables, and the other is point neighbors. And so I'm hoping to kind of hopefully add these as well to Molly. Implicit solvent methods. So we use unitful. It's optional whether the user uses unitful or uses no units at all. You have to choose one or the other. You can't mix them. We recommend you use unitful because it catches all sorts of errors. If you don't use units, that's fine, but you have to make sure you have in your head a kind of consistent unit system. We have some analysis, and we have kind of basic visualization. and you can run CPU threaded or on the GPU. So what's missing? Well, we have partial support for bonds and angles that are constrained in the integrator. That works on CPU in some contexts. We're missing particle mesh UL summation, which is one of the long-range electrostatic methods, which are used pretty much universally for biomolecules. We don't have full virial calculation yet, which prevents some barostat implementations. The system preparation is currently fairly rigid. It's not super flexible. You can't do things like add solvents or hydrate your proteins. We don't yet have alchemical free energy calculations. The API is changing as we're trying to find the right approach. And as I mentioned, kind of due to the maturity, we have limited test coverage, and the performance is, well, I'll talk about that later, but it's still getting there. So to summarize the kind of pros and cons, it's easy to add new features. It's one language all the way down, so hopefully it's easy to understand. And the differentiable simulations which I'll come on to, are fast. In terms of disadvantages, it kind of lacks maturity testing and features of the really well-established software. And the GPU and multi-threaded performance is somewhat below that of existing software. So let's dive in with some code. You can load in the package, and then you set up the boundaries. So this is the box that you're running the simulation in. We set up some atoms using the atom type. You can use any atom type you want, for instance, your own types. We then place the coordinates randomly without clashing. We give the particles some velocity. Whoa, Jesus. Okay. Should I wait a sec or should I carry on? I'm going to wait a sec. Should we try and put it back? Or? Okay. Okay. No, that's fine. Yeah, sounds good. All right, looks like the stage didn't like molecular simulation, but nonetheless we can carry on. So we use a Leonard-Jones interaction, which is attractive at long range and repulsive at short range. We use a velocity Verlet simulator, and then we kind of set up the system using this system call. So this is something which you'll see throughout, is this idea of setting up a system and then calling simulate on it. And then we use the inbuilt visualize function, and we see that this is a kind of very, very high density simulation of some kind of gas atoms flying around. You can also set up, like in OpenMM, which is where you read from a PDB file and from a force field file. So we read in the force field, kind of past an XML file. We can also read in GROMACS files. And then we set up the system using a PDB file. In this case, we're also using loggers. So loggers track properties throughout the simulation, so we want to track the total energy. And also the conformation, which we write to a PDB file. In this case, we do a minimization, and then we apply velocities. We use a Langevin simulator, which keeps the temperature constant. And then when you simulate, you get the thing on the right. This is visualized in PyMol, but the simulation is from what you see on the left. It's not just atoms. I mentioned it's flexible. So in this case, we can simulate planets. So we take the positions and masses of the closest planets to the sun from AstroPy, and then we use a gravitational interaction. We set up a system in exactly the same way. We use a Verlet integrator, and in this case, you can see that indeed, if you simulate for 1 year, you indeed get what you would expect, the orbit of the planets around the sun. So this is using kind of the same abstractions as for atoms. There's 3 types of interactions between between atoms in Molly. So the first is the pairwise interaction, which is between all or most kind of pairs of atoms. So for instance, I mentioned the Lennard-Jones potential, or its kind of generalization, that the Mie potential on the right. You can have specific interactions, which are between specific sets of atoms due to the topology, for instance. And there's also a very flexible type of interaction, which is the general interaction, where you take all coordinates in and you give all the forces back, or the energy back. And that's useful for machine learning potentials, where you would just pass off the call to another library, or to density functional theory. You can, for instance, call DFTK. And so if we wanted to find a new pairwise interactions, I said it should be just as fast and easy as the built-in interactions. So there's an example on the right. You define your struct, and you can have any properties you want of the interaction there. You say that in this case that it wants to use the neighbor list, which is the list of closed pairs. And then you define the force function, which takes in various arguments, and you basically can write whatever you want in there. It just has to output a static vector, which is the force. And you can also define a very similar function which outputs the energy. And that works on GPU and CPU just the same, without modification. And we're planning to allow more properties to go into that function. We've had a couple of requests for velocity-dependent forces, and also we should allow time-dependent forces. So I mentioned GPU acceleration. We use the CUDA.jl kernel language. Currently, the force summation kernel is really simple. You can basically see the whole kernel on the right here. Each thread just calculates the force for one neighboring pair, and then atomically adds it to the force array. Given how simple this is, performance is actually okay. In some cases, it's about 5 times slower than OpenMM. In other cases, it's a bit slower than that. As I'll come on to later, we're looking to develop this, but the nice thing about this is that this is all internal to Molly, so the user never sees this. The actual force functions they define are the same on CPU and GPU. An enzyme is currently the only way I know of to differentiate CUDA kernels like this, and works really nicely. So in terms of performance, if we take, for instance, a bulk water system of about 3,000 atoms, which you can see on the right, on a single thread you get about 18 milliseconds per step, which is just over 2 times slower than OpenMM. OpenMM is probably representative of the state of the art here. Multi-threaded, we're about 4 times slower. And on GPU on this system, we're doing quite well. I'd say we're about 4 times slower, with clear room for improvement. However, on a larger protein system, we are a bit more like 20 times slower, because they can they can saturate the GPU more. I should mention as a kind of caveat, this is on a current development branch, and we use reaction field electrostatics here. So if you use units, it really doesn't slow things down much. It's actually unclear whether it slows things down at all, but if it does, maybe it's like 5–10%. So what's the route to kind of high performance? Well, on CPU, we need better use of SIMD. I've done some work on this, but I found it challenging to get this working whilst still allowing generic interactions and generic atom types. So if there are any kind of CPU whiz kids in the audience who want to help with this, do chat to me. There's a lot of room here for improvement. On GPU, we should basically do what the existing software does and use the kind of clever neighbor ordering and reductions in more complex kernels, and hopefully we should have that by the end of the year. Realistically, we're not going to reach the speed of mature specialist software on, for instance, protein simulation. However, what we can aim to be is the fastest for kind of small to medium systems with custom interactions, which are often difficult in current software. And if we want to scale to larger systems, we need to do domain decomposition, which is where you split the system up into kind of smaller cubes. And that may be a long-term goal, but it's not currently being worked on. So I mentioned differentiable simulation. It's probably easiest to introduce this with analogy to recurrent neural networks for those who are familiar with that. So if you imagine you have a sentence, a series of words, and you want to predict whether it's positive or negative, happy or sad sentence, you can use an RNN, which kind of goes through word by word, and your network updates some hidden states, and then at the end you have the output, which is your prediction. You compare to your labeled output, which is and then you calculate some loss function, which is just a number. And because you've been clever and you've implemented this in an automatic differentiation framework, you can use backpropagation to change to get the gradients of that loss with respect to the neural network parameters. And this is how basically all neural networks are trained. And the idea of a differentiable simulation is you do the same thing, except you have your starting coordinates, you then step through the trajectory using molecular dynamics and your force field parameters. You then have some loss function. So in this case, I'm just showing you might compare the final coordinates of your simulation to a known structure and calculate the root mean squared deviation. And then you just do the same thing. You use automatic differentiation to obtain the gradient of that loss with respect to the parameters, and that lets you improve your force field to match arbitrary properties. So for instance, in this work I did a few years ago, we started off with kind of flat zero potentials, and eventually we learned a coarse grain potential for proteins that matched what you see in the PDB. And the reason this is appealing is because you have this huge variety of possible loss functions. I mentioned earlier that when you train machine learning potentials, you just train them on quantum mechanical data, forces and energies. But here you can train on pretty much anything you can obtain from the structure. So for instance, the radius of duration, how compact things are, flexibility, whether certain regions of the protein move, how strong the binding is, and fit to experimental data, for instance, cryo-electron microscopy data. So what software is available for this? Well, there are actually packages now that have come out in the last few years. JAX-MD, TorchMD, DMFF. These are all great, but they're all limited in some way, either by their scope, so they don't have biomolecular support, or by performance. They're nowhere near the speed of OpenMM and GROMACS. And so Molly can do this. It can do differentiable simulation, including on proteins, and it can do it fairly quickly. The way we do it is we use Zygots on the outside, if you like, to link everything together. And then the slower bits we call into enzyme. So we have this big file of chain rules which just call into enzyme, and including for the GPU kernels. And so my work over the last couple of years has been to apply this to improve a protein force field. So implicit solvent force fields basically replace the solvent molecules with a continuous medium for speed. So you can get rid of all your water and just look at your solute. However, they tend to overcompact disorder proteins. And so we use Molly to modify an existing force field and implicit solvent method to improve its performance on disorder proteins. And so on the right here, you can see in orange and green is the correlation of radius of duration, which is how compact these proteins are between experiment and simulation. And in the existing implicit solvent methods, which are orange and green, you see that it's a poor match. And the match of our new method in blue is much closer to the experimental values and to kind of explicit solvent simulations in purple. And if you want to read more about that, you can read about that in this paper. So we have more ongoing work. I mentioned we use Zygot and enzyme. That's a problem basically because Zygot doesn't allow you to do mutation, and that puts a limit on performance. So we're basically rewriting it all to use enzyme throughout, and that will allow us to kind of access the higher speeds I was mentioning before. There are a couple of blockers there. We are waiting on GPU support for broadcasting an enzyme, but I think that should be coming in fairly soon. James Sloss is adding kind of generic backend support with kernel abstractions, which we should be able to do without a loss in performance, and means that you should be able to run this on all sorts of GPUs. There is work being done on particle mesh U-automation and GPU bond and angle constraints. The API may change a little bit more as we try and find the right balance. But if you have any kind of suggestions or comments, do let me know and we can work that in. And at some point there'll be a software contributor with a software paper with kind of all the contributors. So just to kind of grab bag to finish off, I've said it can do protein simulation. You can simulate bonds, so here a diatomic gas. I showed you that you can simulate arbitrary systems that aren't atoms. I didn't talk about this case much, but in this case we're just training a simple machine learning potential to reproduce a familiar logo. You can make and break bonds throughout simulations, which is quite a nice feature you can't do in existing packages. And you can also use it to just kind of explore potentials and plot them. I started my group recently at the Laboratory of Molecular Biology in Cambridge, and there's funding for postdoc positions. There's also going to be a PhD advert coming out towards the end of the year. So do chat to me if interested. And I'll just say thank you to the contributors, many of whom have been contributing for a long time now, to all the amazing Julia contributors and package authors, particularly for Zygot and Enzyme. So big thanks to Billy Moses and Valentin for for basically fixing all these enzyme bugs. I think I've raised about more than 50 bugs on enzyme, and I think more than 40 of them have been fixed, which is fantastic. Thanks to OpenMM and GROMACS for the inspiration, and the Georges and David Jones Group for support at the LMB. And finally, thank you for your attention.
Thanks. It was a great talk. Do we have questions? No? Yes. Catch the box.
Yes. Oh, thank you very much for your great talk. A growing field in biophysics is that of active matter. So in active matter simulations, you do a simulation just like this one, but then for every particle there's another stochastic process that determines the active force. This, for reasons you've mentioned, is very difficult to implement in LAMPS or GROMACS or Blue or whatever software you like. So is this something that would be easier to do with Molly?
Oh, sorry.
Yeah, okay, thanks. We have this general interaction type which allows all coordinates in and all forces out. So you'd probably want to write some general interaction that basically applies that stochastic force on each atom every time step. And then if you wanted to apply other forces between atoms, those would be either pairwise interactions. So it's possible you may need to do a bit of kind of looping yourself. So you may need to loop over the atoms in that case, but I think it should be possible. Yeah, if you give it a go and it's not possible, then do let me know, because I know different fields use interactions in different ways, and my focus is very much on biomolecules, but it should be applicable to anything really.
Okay, thanks.
More question?
Okay, is there some related work on Poisson-Boltzmann simulation and molecular surface generation?
I'm not so familiar with that, so I don't think you'd be able to do that in Molly as it stands. But
yeah, but it would be some package which would use the Molly data and in some kind of consistent way to also allow the differentiation throughput.
Yeah,
something like that.
That would be great. Yeah, and if we get something working with another package, it would be great to have it as an example in the Molly docs to show that integration. Yeah.
Okay.
Hey Joe, great talk. You mentioned that you didn't have full VRL support, or...
Sorry, could you say that again?
You said that you didn't have full VRL support.
Yes, that's right.
And I don't know if you still support MPT simulations at all, or...
So we have virial support for pairwise interactions. However, I believe in bonded systems, the bonds and even the constraints also contribute to the virial. So we don't have full support in that sense. We don't have any piston-based barostats, but it wouldn't be too hard to implement one. The problem is it would only work on kind of gas systems, unless you were willing to compromise on the virial.
Because I know that OpenMM does without virial calculations.
So OpenMM has the Monte Carlo barostat, which we have. Yeah. So we have the Monte Carlo barostat.
Let me give you that here. Sorry?
Great.
Yes.
Great. Thank you.
Very much.
I also have a small question.
Yep.
So you mentioned that the Molly supports GPUs.
Yeah.
But does it also integrate well with HPC systems, high-performance computers, clusters with thousands of cores?
So at the minute, not really. There's multi-threaded CPU support. So at the minute, you'd have to have for instance, if you had a node with 256 cores, that would work. It would just use all of them. We don't have support for things like MPI or kind of multi-node or anything like that. That will probably come out as part of the domain decomposition stuff, because you generally want to, so on the right here, you generally want to split up things onto different, so that's more a long-term goal, and there's not really much point in doing that unless the performance gets kind of really competitive, but that will be a long-term goal, yeah.
Great. Extra round of applause. It was a really nice talk.
Thank you.
I think we have a small break, 10 minutes. We start again in 10 minutes.
Well, we have some time left.
Okay, we continue with our next talk from Philip. And his talk is going to be about how to migrate from Julia 0.4 to the most recent versions. So,
right.
Philip, your stage.
Thank you, Dimitri. So, hi all. Thank you for coming out in this weather. My name is Philip, and I work at Akamai on a performance product called Impulse. Right. Welcome to my stadium. Sorry, I mean my talk on migrating directly from Julia 0.4 to 1.6. So we launched our product in 2011, but we only added Julia capabilities in 2014. At the time, we were using Julia 0.2, but we very quickly migrated to 0.3 because naturally, even 0.3 was better than MATLAB. Right? Julia was moving very quickly, so by 2015, we migrated to 0.4. Our code base was fairly small. We had very few customers depending on this functionality. And Julia was improving a lot. So I attended JuliaCon that year in 2015, and I was already convinced we're going to be using this language for a long time. It's already better than Python. So I was hooked in 2015, and as you can see, I'm still hooked into this. So over the next few years, we were adding a lot of features, and we had more customers depending on this functionality. Many of our customers were large websites. They did not want us to change our code too often. We couldn't change APIs, and therefore we kind of got stuck on 0.4 for a while. I was also kind of assuming that migrating from 0.4 to 5 or 6 or 7 would be as easy as migrating from 0.3 to 0.4. So I was wrong on that, but we were building these features and really liking the language a lot. So in about 2019 to 2018, Julia 1.0 came out. And in 2019, it became the long-term support release. So we decided we're going to try migrating to 1.0. And the recommendation was first move to 0.7. You'll get a lot of compat errors. Fix all of them, and then 1.0 should be easy enough to do. But that was just taking so long to do because we had this huge code base, and it just trial and error, one module at a time. So we decided, screw it. We're just going to go directly to 1.0. But this whole process took more than 2 years. And while we were migrating to 1.0, 1.1 came out, and 1.2 came out, and 1.3, and 4. And then 1.5 came out, and there were so many new features that I wanted to use, and performance was so much better. So I spoke to our management team, and we said, if we're going to make our customers move, we need to make them move only once. So we're going to go straight to 1.5. I started working on 1.5, and 1.6 was announced as the LTS. So I said, screw this. We're going to just move over to 1.6. And so we started the migration to 1.6, and we finished it about the same time that 1.7 was released, which means 1.6 was officially tagged as LTS. So we were able to get something out on time. And so I started working on the stock, and I submitted it. But unfortunately, the stock is now obsolete because, as we've heard from the start of the conference, 1.6 is no longer LTS. It's going to be 1.10. Luckily, the migration will not be as long. So I'm first going to go into what we actually need to change to move from 0.4 to 1.6. And in all, there are close to 40 changes. I know the slide has only 5. That's not everything, right? That's not even the only slide. So there are about 40 changes, but hopefully you do not need to do this migration ever. And so I'm not going to read through all 40, and I'm not going to cover all of them. Just probably one on each slide. In this case, the change of all of the finds, so find first, find last, find next, find all, they used to return 0 on the case where it could not find something. From 1.0 onwards, it started returning nothing. So we had to change signatures a lot of places. We had to change. We could not do a comparison with 0 or just add 1 to it, for example. We had to do an is nothing check. Fairly easy, but it was the hardest thing to do on this slide. But more importantly, I think with the migration was a good chance to relearn a lot of Julia assumptions and thoughts of how to program Julia. Broadcasting, for example, was so much better in the 1.x series. 1.5, it became so much faster. So we learned how to do broadcast across all of our code base. Instead of operating in loops, use broadcast to broadcast our operators or our functions onto arrays and take advantage of things that the language already provides. So in this case, round was the function that pushed us over that, because round used to work on arrays, and then it stopped working on arrays. And so we started looking at broadcast. Some other things we did was we used to use tick and talk a lot to measure how long sections of our code took. And we would measure that and send that to our telemetry so that we could optimize pieces of code that were used a lot by customers. And tick and talk just disappeared in 1.0. So we had to figure out a replacement for it. Luckily, there are lots of ways to time things in Julia. So there's the @time macro, there's the time_ns if you want high precision time. So we ended up writing our own macro that measures the time of a block of code and also sends the results to our telemetry. So that simplified a lot of code across the code base. More with the find family, this seems to be a theme across our migration. Once we fixed one thing with find, we found another thing. Working with strings, if you try to find a character in a string, the order of parameters changed. So it's not like we could do a search and replace for where we had the order correctly. We had to manually look at every single call to find to figure out if we were doing it the right way or not. And in general, this made things better. It makes it more consistent with contains and occurs in and functions that can do fix1 and fix2. So we like the change. It was just hard to do. Logging is so much better, right? Yeah, or so much easier. You just add the @ macro before all of your info or warn, and you're done. The only difference being error, which was ERR in Julia 0.4, became error in 1.0. If you use error in without the macro call, it throws an error exception. So you have to be very careful about only putting the macro symbol where you actually need it. So most of these changes, most of the changes to our code base were because of changes in data frames and not so much the language itself. It's not Julia's fault, but we had to make these changes. Some of the biggest one that affected us here was when you call names on a data frame, previously it would return an array of symbols, and with 1.0 onwards, it returns an array of strings. So we had to go through all of our code and see if we were looking for symbols within the return value of names or not, and change that accordingly. There were a few more changes, but not too hard to deal with. Again, search and replace kind of fixed almost all of these cases for us. Testing became so much better. Like I said, we have 40 items that customers need to worry about if you're in the general public. Only 36 of those matter for you. Hopefully, you are not on 0.4 and 0 of these matter to you. So to do the migration, we followed a fairly straightforward procedure. It is not something I ever want to do again. Luckily, the migration to 1.10 is not going to be as hard. Right? It's essentially going to be these two changes. Most people won't have to worry about it. So var args, if you ever look for the type of the var args in your function, it's always been var args, but previously it was a subtype of type, and now it's not a subtype of type. So that's a change. And then if you ever use test logs in your tests, sometimes there is new amounts of white space in the log messages. So that's pretty much all I have. Thank you for coming out and listening to me, and happy migration.
Thanks, Philip. It was a great talk. In the interest of time, we have to move to the next speaker, but please catch up with Philip after the talk if you have some questions. And I hope next year we will be hearing about how to migrate from Julia 1.6 to 1.10.
Sure. All right, thank you. I go down this way? Yeah.
Hey, can you hear me? Yes. Awesome.
Pronounce your name.
Panayotis. I can do it. Give me. Maybe that's fine.
Okay. Our next talk from Panayotis.
Yes.
Is,
Awesome.
He's talking about Julia Hub's Ask AI, enhancing ChatGPT with Julia-specific context. Round of applause, please, for our speaker.
Hello, everyone. Thanks for making it in the cold. It's very cold, but we'll make it. OK, so I'm here to talk about one of the features of Julia Hub. It's called Ask AI, and it's basically a chatbot where you can talk with the docs. So, as I said, it's a familiar chat interface. You can find it. You can use it for free with your Julia Hub account. Small advertorial, there is a competition going on in our booth, so make sure to visit that. So it's specifically instructed to talk about Julia and hopefully nothing else. And it knows most, if not all, of the Julia docs. It's based on ChatGPT Turbo for now. We'll talk about that more. And that's pretty much it. So how do I find it? This is Julia Hub in dark mode. You just go here, and you ask something. So some history, how did you think about this? So a lot of smart people did a lot of smart things in order for us to be in the position where we can do this. But basically, you know, the Google Brain team, blah, blah, blah. This is from a SourceGraph blog post that was an inspiration for this. And one thing led to another, and July last year, we announced this. So it wasn't called RAG at the moment, which I think makes this call a non-RAG brag, because RAG brag is a thing nowadays. So basically, this tweet and this blog post from Supabase were inspirations, and we in Julia Hub are in a position where we rehost most of the docs for the Julia packages, and also have a lot more knowledge around what works and what doesn't in Julia. So we were in a very nice position to do this. So what goes in? First thing, like about any project that looks like that, the expectation is that you're going to do something super smart, right? Touch an AI model and do super smart stuff. The reality is that it's a data project, right? Everything around RAG is mostly like 90% cleaning the data and getting the data organized in a way that your system can use it. So it may retroactively seem a bit disappointing, but that's the reality. That's our reality. It's mostly about data and knowledge. So what goes in? Stack Overflow questions, all of the Julia documentation that Julia Hub rehosts, that is all of the general registry, some private registries around Julia Sim and stuff. Of course, if you opt in, you are not here. If you opt out, I'm sorry, you're not here. And some manual collected Q&A that looks like something like that. It's really an Excel file that just gets pushed. Yeah, that's not real. It's just indicative. So how do we do like that chunk? We get a 2 GB chunk of docs. How do we do it? We paragraphize the docs. Like this is standard in RAG. That basically means that you have the Julia docs, and you split it by, something like a paragraph. Not the best one, but pretty good. We add some metadata to that, location of the paragraph in the docs, the document that we are embedding. Is that a package or is it something else, and what version it is? Because as you understand, we have all the versions of all the docs, so we need the frontier of the latest, usually. If you have, there is some similar code in multi-documenter that does something similar to that paragraphization. And we save all of that to a Pinecone database, right? Simple stuff. And then it's standard drag, right? The user submits a question, like I hope you already have. And we search that thing. I call it the knowledge pack because I like the name. And we smartly inject like the top X related results from the search into the pinecone. And ChatGPT does the rest. So does it work? We think so. We hope so. We have gotten over 18,000 questions, which is basically 50 per day. Of course, not very homogeneously distributed, but here it is. There is also a small button that you can click and tell it, like, is it good feedback or is it bad? It seems that I'm the only one who have clicked that. So if you can, click that next time. And yeah, like what are the next steps? That's it, right? The feature. So the next steps is, the first step is to collaborate with the community more. We basically want to organize the data better, to standardize what a knowledge pack is as a format, so we can share this with the community. There is no reason for everyone who wants to do something similar to scrape the same docs and get the same embeddings. OpenAI has enough funding, I think. And on top of that, we have our private ones. So we like the Julia Hub offering will always have some extra sauce. So we're going to integrate prompting tools. Big shout out to Jan. Mainly to experiment with other providers apart from OpenAI, and also calibrate the strategies, which is something that we haven't already investigated. Now, big shout out to Avik, Venkatesh, and Morten for both this feature and infrastructure for this feature. Basically, as I said, 90% of this is collecting and organizing the data, and that's mostly Venkatesh and Morten. And of course, to the community and Julia Hub for pretty much the rest. And that's it. That's all. Thanks for listening.
Thanks. Thanks. Do we have a question from the audience? Yes, there.
So I recall trying this and seeing standard issue ChatGPT Turbo hallucinations and wrong answers, in addition to standard Google outdated answers.
Okay.
Is there some way to like make sure it's better than the Julia Wiki?
So, if you can read the docs and you can navigate yourself to the docs, it's probably, what works for you and what works best, right? And I have gotten feedback the past few days that, for undocumented stuff, for really niche stuff, it doesn't really work, right? It cannot fix your code at this point. It's not Copilot. And it is based on ChatGPT, so while the main thing we evaluated this with to actually provide it to the community was that it was reducing hallucinations versus ChatGPT 3.5. For example, stuff with request.jl that are deprecated over http.jl, and it was more up to date. You cannot, nullify the hallucinations completely because the engine we use currently hallucinates. And while we give it some context, like the whole grow up of ChatGPT includes hallucinations. So, basically the crash course is not enough to remove all the hallucinations. So, don't run this on your MRI device, and don't run this on nuclear power plants. And always look at the docs if you can. But we do think that there is value to be given for the normal use case, the entry-level use case.
Okay, in the interest of time, we have to move with our next speaker. But if you have more questions, please catch up with our speaker after the talk.
Okay, thank you so much.
So our next speaker is Thor. He just arrived from UK to enjoy the lovely weather in the Netherlands. And the talk is going to be about Turing. Turing.jl is a very well-known package in the ecosystem for Bayesian statistics, Bayesian modeling. And I personally use Turing a lot, just a baseline, because we also do Bayesian statistics in the university, but we use a bit of a different methodology. But Turing is great. I use it a lot, actually. So I'm very interested in the talk. Tor, the stage is yours, as you're ready. Please, a round of applause for our speaker.
Thank you, Dimitri. Hello, I'm Tor Fjelde. I work quite a bit on Turing.jl, which is a probabilistic programming language. I'm a PhD student at Cambridge, and I'm a research affiliate or associate or something like this with the Alan Turing Institute. And I spent a lot of time, too much time arguably, working on this project. So today I'm going to tell you a bit about it. But before we go into this, I'm going to tell you about Bayesian inference. I'm going to be quite brief, but hopefully it should remind people about what it is and give people somewhat of intuition about what it's actually doing. So, Bayesian inference, very quickly, is sort of the scenario where you have some real data, curly D, and you want to determine some parameters, theta, given this real-world data. And you're trying to inspect this probability density of the parameters given the data. And Bayes' rule tells us that we can decompose this into two components. Let me just get the laser pointer out. So here we have the likelihood, which is the probability of the data given the parameters, and this prior, that is the probability of the parameters that we choose before. And so because we do this decomposition, typically when in a PPL and also in mathematics, you write it in like this generative model formulation where you say like the parameters are sampled from the prior, and then the data is sampled from this likelihood. And so this is kind of the notation that you end up using. A very simple example is this, of this biased coin, where your data is a sequence of sort of heads and tails, and then you have like an initial belief that the coin should be roughly fair, meaning that, here we see that a lot of the probability mass is around 0.5, meaning like it's a fair coin. And then as we get more and more observations, we update our beliefs, and that's what you see on the lower right here. With the n here is the number of data points, and as we get more and more data, the posterior distribution over the parameters concentrates, and we recover the true parameters, but also with some uncertainty. I will give a brief warning, which is that people show these animations, including me, because they look very nice, and it gives the impression that you can just sort of update your posterior in this streaming fashion. Generally, that's not possible. If you do want these kind of settings, you need to work with certain models, and you need to talk to Dimitri, because that is what he works on. Another simple example is a linear regression example, where now you have pairs of points, or this input location x, and you have observations y, and here you have this your model is this linear kind of model, where you have some slope beta that multiplied by the input, and then you have some intercept alpha. Here we use put some prior probability over these, and then we have the observations, the y observations, which are in some sense noisy, with this variance sigma. And then you can do inference over this, and here you can also see a nice animation of what it looks like as you get more and more data. The problem is that Bayesian inference is generally not, the posterior that you're interested in is not generally available in closed form, right? As that means that requires various approximations to actually inspect this posterior distribution. Typically, that is done using what's called Markov chain Monte Carlo, or variational inference. And these methods can be quite annoying and difficult to implement, in particular in a way where you can actually trust the results, because these are stochastic algorithms, and so, it's kind of, if you implement it yourself, sometimes it does the right thing, and then sometimes it doesn't, and it can be difficult to actually identify what's going wrong. And so then it's nice to have well-tested, battle-tested implementations of these methods that you can just, pick and choose from. So in summary, it's a principal way of incorporating prior knowledge into your simulator, like the model you have of your parameters. It allows you to quantify the uncertainty over the parameters that you're interested in, but it is non-trivial to do for interesting problems, both computationally, but also statistically. You kind of want the methods to be well implemented, so they're fast, but they also need to be statistically efficient in the sense that they can actually get approximation of the posterior that you're interested in rather quickly. And this is where probabilistic programming comes in. So like when I first heard about probabilistic programming, like many years ago now, I thought it was kind of like, what's the point of this? It seems like there's a programming language which is just fundamentally non-deterministic. I didn't quite understand like why this would be useful. And I think it's kind of like, it's not the best terminology. Effectively, like, probabilistic programming is really just about democratizing Bayesian inference, right? Because a lot of people who have data, they might be experts in epidemiology, biology, or something like this. They're not expert in the statistics part. And so it's really just about like bridging this gap and letting these people who have interesting problems and interesting data to analyze actually get access to these methods. And so what you want with the probabilistic programming language is just that the user should be able to write down the model fairly easily and iterate on it, change it, improve it. And the rest should be somewhat automatic. Like it should be able to do something reasonable. So the way to sort of view probabilistic programming languages, in my opinion, is just as a suite of tools that allows you to easily specify models and also perform inference and inspect this posterior distribution that you're interested in. And there are tons and tons of approaches to this. So there's some that are like the Bean Machine, PyMC, Pyro. These are in Python. They generally are based on sort of an underlying computational framework like PyTorch, NumPyro, and TensorFlow. That means they're very, very quick, but it means that you, for example, you can't write naive for loops. You have to be a bit careful about how you write your model and stuff like this. Then there's Stan and Bugs, which are model where they have their own sort of domain-specific language that you specify your model in, and then they compile that to a lower level language, which is where the inference is performed. Say Stan's case, it's C++, for example. And so that creates a discrepancy between the implementation of the model, which is written in sort of this own DSL, and the actual inference language where the computation actually occurs. And that can be annoying because that means that maybe the packages, the functionalities you're interested in aren't actually available, and so on and so on. Then there's some like Anglican and Turing, which are implemented kind of where the DSL, the way you sort of specify a model, is done in the same language as where the inference is run. So Anglican is a PPL from quite a few years ago in Clojure. Clojure is unfortunately not a language that is like well suited for scientific computation, and so it hasn't really been applied as heavily as say maybe Stan. But Stan is sort of what we in Turing look at very often and think this is what we want to be, because they've sort of been incredibly useful for the scientific community. And so at this point, you know, you ask, if I'm standing here, is Turing.jl the perfect PPL? Of course it isn't, it's far from it, but it is different in the sense that it is similar to Anglican. It's sort of the DSL, it's implemented in the same language as the inference happens. And that means that, which is Julia in our case, and that means that you get a lot of really, really nice interaction with the community, like the remaining packages in the ecosystem and so on and so on. As I said, it's Julia all the way down. There's not really restrictions on what you can put inside a model. It means that we sort of, you know, the user is very welcome to shoot themselves in the foot if they really, really want to. But it means it also compiles very, very nicely with the ecosystem. Usually at this point, I talk about Julia programming language, how quick it is, why it solves a two-language problem, and so on and so on. This is Friday, like so you're quite far into JuliaCon. I feel like you all know this at this point, so I'm not going to do this. But quickly, I'm going to give you a brief overview of Turing.jl. As said, it's a general purpose probabilistic programming language. General purpose in the sense that it's not specialized on particular models. It's sort of very, very general in the models you can implement. Which models would actually be fast to run inference for, and so on and so on. And that's like a different aspect, right? But you can sort of implement whatever model you want in Turing. It's fully implemented in Julia, which generally means that it's quite approachable for users familiar with like MATLAB, Python, and R. And so that's like a lot of the people that we see are coming to us. They have no sort of Julia experience, but they start using Turing because they've been using Stan through R, for example, and then they try out Turing. That's also a way to get them into Julia, which can be quite useful. And it has been growing in popularity, I would say, particularly over the past 3 years. Obviously, like GitHub stars and like Google Scholar citations and so on, these are just proxies. They're not really accurate, but it gives you some indication of like people actually using it, which is quite nice. And I'll show you some example of this later. This is what a Turing model looks like. So here we sort of do using Turing like you do with any other Julia package. Then you define a model. The model is really just a function, like standard Julia function with this special tilde syntax. And this model macro, what it does, it just looks at the lines that have the tilde in it and changes those lines a bit. So like every other line in the model that doesn't have a tilde in it is left as is, which means that the user can do kind of whatever you want in there. You can put differential equation solving in there if you want to, which is a very popular application that people use quite often. And so it makes very few assumptions about the model itself. And so here you see this data sample from the prior. So there on the right-hand side, just like in the mathematical notation we saw earlier, the prior is a distribution, left-hand side is a random variable. Similarly, this curly d, which is the data, is sort of then a sample from the likelihood effectively. Then you instantiate the model. So this thing here generates two methods. One is for evaluation and inference, and the other is for sort of a constructor to define like this model type. So we make use of this here. We define the model, capture in the variable model, and then we condition this model on this random variable curly d being equal to some data that we have access to. This is very similar to what we write in mathematical notation. Capture this in a model cond variable, and then we can sample from this model cond, and that's how we sort of inspect the posterior distribution of this model. And so it's fairly straightforward. Mapping it from the mathematics, the generative model that we wrote down earlier, to this is quite simple. Here's a more concrete example with the linear regression that we saw earlier. On the right-hand side, you see the generative model. On the left-hand side, you see the implementation. And that's literally how it works. And so the nice thing here is that when you're, for example, working with people that aren't necessarily software engineers, or they're not like, super well versed in this, it's quite nice to be able to just have a mapping between the implementation of the model and the actual mathematical definition of the model. I'll point out this is a typo. This should have been in truncated normal, but otherwise it's the same. So, Turing.jl overall, the strength is that it's convenient and generally performant, particularly if you write the model in the right way. Really just thanks to Julia. It's very similar in design philosophy as Julia. It's sort of the idea is that we accept everything, we allow the users to do whatever they want, and then we kind of optimize when possible. And so we have like different modes of running the model effectively. One is faster than the other. And then models are just Julia functions. Distributions that we get from distributions.jl, they're just Julia functions. Sort of everything is just Julia, and so it works really, really nicely with the ecosystem. It does, however, because we make very few assumptions about the model, it means that certain operations that might be possible in other PPLs are not possible in Turing currently. There's nothing technically stopping us from doing this other than just developer time. But you can't, for example, do automatic modularization. It can be quite useful for certain models. And a naive implementation of a model might not be the most performant. So there's like some tips and tricks similar to how there's tips and tricks to how to write efficient Julia code. Similarly, there's for Julia Turing.jl models. And so these are things that are like useful to be aware of. Before I go into this, I'm gonna have a sip of water because it's not wet enough already. So, Turing has been around for quite a long time. To show you briefly, but it started out when Julia was in 0.4. And the last talk about Turing.jl and related stuff, I think, was at JuliaCon 2022, so it's been quite a while now. I figured it was time for an update. I'm going to tell you briefly of like the history of it. We started out with Turing.jl in Julia 0.4. That was very, very different days. I joined when it was Julia 0.6, which is still very, very different from what it is today. And then that was happening in 2017, and this was his publication with Kai-Su, Hongre, and Subin Garamani. And over the past 5-6 years, there's just been a lot of blood, sweat, and tears from PhD students, research assistants, and so on and so on. People that have been using Turing maybe for their research, and so they have also contributed to it, or people who just wanted to procrastinate on their PhD and then decided to work on it. And some people have actually been sort of doing some research with it and so on and so on. But it's been very much like people just sort of working on it for a few years, and then maybe they have other responsibilities, so they have to move on, and so on and so on. And so now, in 2024, I'm very happy to say that sort of with the collaboration and funding through the Alan Turing Institute, we'll actually have people, sort of like Marcus here, working full-time. They're research engineers working full-time on the project for the next 3 years at least. And so then we have a lot of proper people, just really, really good software engineers actually working active on the project. And so that's quite like a big thing for us, just because now this, very, very capable people actually make it able to take this to like a stable state, basically. So what has happened over these few years? People are actually using Turing for real stuff. And that's quite exciting, in my opinion. So here you see some applications. One of these involves some of the people who actually worked on Turing. This is just a snapshot that I've taken from Google Scholar. And this comes from quite a few different disciplines. And this is kind of achieved sort of in the sense of what we wanted. Like it's people that have actually interesting problem, interesting data that they want to do some inference for are using Turing to actually solve these problems. So this is applications that happen in biology, epidemiology, economics, neuroscience, and so on and so on and so on. And throughout the time, we've also gotten quite a lot of nice functionality. For example, back in the day, and this is still possible to do, if you wanted to condition a variable x on being equal to 1, like we saw earlier with this curly d, you would have to pass it as an argument to the model. And that's like for a lot of reasons. Like number one, it just seems a bit counterintuitive. The second thing is that it's just like, it doesn't really allow you to operate on the model very nicely programmatically, because you can't really inspect what is an observation, what isn't. So now you can sort of use this much nicer bar notation. And that means that you can also query the model and ask it what do you consider to be data, like what are observations. And then you can programmatically kind of remove things. So now you can sort of say, I want to fix this variable to be like x to be equal to 1. Then I can decondition it and remove the variable being fixed. And so that is quite useful if you wanted to actually like act on the model itself. Similarly, before, the really only thing you could do on a model was sample from it. But now you can also you can sample from it, but you can also using it like a sampler, but you can also just call random the model to sample from the prior. You can fix variables like the x, for example, which is similar to condition, but the log probability is not included. This is similar to sort of interventions in causal inference. You can call predict to predict from the model, and then your generated quantities is a way of extracting additional statistics or additional quantities from the model that you might be interested in, similar to like Stan's generated quantities for those familiar with that. These are just lists of operations, but they actually enable some quite useful things. So one very crucial aspect if you're doing Bayesian inference is that you kind of want to follow this standard Bayesian workflow if you want to be confident in your results. And I am just pointing to this paper by Andrew Gelman, Aki Vettari, and many other people, outlining quite an extensive document outlining a Bayesian workflow. Highly recommend it. But now this becomes kind of trivial to perform. I realize this figure is a bit small, but hopefully somewhere is readable. First thing, you define a model in maths, right? As we've seen before, that's what the first step to do. Then you define a model in Turing. So that's also quite like the translation there is quite easy to do. Here, you can perform prior checks, where now you can sort of easily fix parameters in the model, sample from the model that has the fixed parameters. Then you get your sort of a generated data from your model, given these correct parameters that you know of. And then you can perform inference on this thing again to check that you can actually identify the correct parameters that you see at the bottom here. It's called like a prior check. And if you do this over and over again, it ends up being something called simulation-based calibration. This is quite a useful thing to make sure that the model, together with the inference algorithm, actually works, and you can recover, under the sort of the assumption that your model is correct, you can actually recover the parameters. And so because now this ran and this fixed and so on, this operations, like this workflow becomes quite trivial. Then, once you've done that, you condition your model on the true data, like the actual observation you have from the real world, perform inference, and then you can perform post-inference analysis, look at stuff like important statistics like R hat, R ESS, and also perform predictions using on the data. And then you rinse and repeat until you're happy with the model and the inference results you have. Additionally, you can now combine models. This was not something you could do before. But now you can basically take one other model and embed it into another model. And that is quite nice. It means like, because it's also all Julia, I could implement a sort of a package of epidemic models that are sort of working on like analyzing like epidemics. And then someone else can come along and they can do using epidemic models, and they can just take like, say, an SIR prior, for example, and then just embed that into their own model that they're now working on. And so it makes like sharing and reusing models like very, very trivial. Still have to perform joint inference over these things, but that's something we're working on. This is kind of, for example, a real-world example from a project that I was involved in, where we wanted to sort of iterate on a model, try out different varied ways of modeling, say the effective R number. This is like modeling COVID in the UK. And then we also had a model for latent infections. And then we had a model for the actual observed number of cases. And so then it was quite nice to just separate all these components into different models, and then we can just swap out, say, like the likelihood, for example, for a different likelihood quite easily. And it was like, when we were working on like a much larger project like this is like, becomes incredibly useful. Another thing is that in Julia, we use sort of these packages that do automatic differentiation. And we do that also in Turing. And we make, and so when you, for example, want to do like, use gradient-based samplers to do inference, like Hamiltonian Monte Carlo, you need gradients. And so because we're in Julia, we just use forward diff, reverse diff, all these packages that already do AD quite nicely. Problem is that before it was kind of difficult to exactly benchmark the model and figure out which backend you actually want to use. And so now you can use this very, very easily using Turing benchmarking.jl. Now you just call benchmark model, and then you get a bunch of you can pick the 80 backends you want to look at and so on, and then you just can look at which one is fastest, and the one that's fastest, that's the one you pick. So this is literally what it looks like now. As that is also quite a useful thing, just makes quality of life much easier. Now when you have a model and you're wondering which 80 backend I should choose, just benchmark it and then you pick the one you want. Finally, there's also, like back in the day, when you run sampling, sometimes it can take days, which can be quite annoying if all you're seeing is just a progress bar telling you like how far along it's gotten. Now we still have that, but we also have logging to TensorBoard using TensorBoard logging.jl, thanks to Frames and other people. And this is what it ends up looking like. So here you see some sample statistics on the top here. Here bottom you see like the trace for the parameter that you're interested in. You get like histogram estimates of the parameters and stuff like this. This is also like quite useful if you have very, very long running inference runs and you want to kind of inspect how it's getting along. As I said, this is very much just like thanks to TensorBoard logging.jl. Another thing that has changed quite a bit with Turing since like its initial release is that it's no longer a monolithic application. So back in the day, it was kind of one single package. Everything happened in that package. Meant that like it was quite difficult to maintain. Much of it wasn't reusable, and so on and so on. And so we made like quite a big effort to just compartmentalize the different components. And that means that now, for example, Turing is just a shell around like a bunch of other packages, where the DSL is implementing a dynamic PPL. Samplers are in their own packages, but they implement this abstract MCMC interface. The nice thing about that is that you can use these sampler implementations that we work on and actively maintain without having to work on Turing. So if you think you can implement your model more efficiently than like you can write it in the Turing model, then you should do that and you should just use these samplers outside of Turing. Similarly, the hope is that this will also lower the barrier from people working on inference methods to actually make it to the user base that are of like PPLs who actually need these things, right? For example, you can implement your sampler in abstract MCMC.jl, and you can just run it on sort of standard log density functions. And if you do that, it's now possible to just use this in Turing.jl super easily. So that way, we should hopefully encourage more people that work in the inference part to actually just write them in Julia, and then once you've written in Julia, they're immediately available to the entire user base of Turing.jl for their day-to-day problems. Similarly, post-inference analysis is found in MCMC diagnostic tools and MCMC change.jl and so on and so on. This is quite like a useful thing. And so we're also, just so people are aware of this, like if you don't want to work with Turing.jl, there still might be like useful packages around that we're actively maintaining that you might find useful for your problem. So all in all, like this is basically what like the average user of Turing.jl sees, right? Just Turing.jl, this package. This is really more what the Turing-Lang ecosystem looks like. This is not actually quite it. There's probably a bit more of them. Here you see some orange highlighted packages, which are ecosystem packages that we don't own, but we contribute to them when we find bug fixes or we have feature requests and so on. And so we're super reliant on these packages. But these are actually not the packages you use. Like this is more like the packages you use, right? Which is very typical for a Julia package. But they this is all with compat bound, so it's like fairly stable, and it's like we don't really have that many issues with it. But it shows you how like reliant we are on the entire Julia ecosystem, right? And it means that we can reuse components from that people have implemented once and implemented really, really well. We can just use that. And that is quite different from other PPLs, which are tied to some underlying graph computational framework, or they're working in their own DSLs, so they kind of have to re-implement everything. And so we've had a lot of really, really nice applications coming out of this, basically. For example, there's hidden Markov models. Like we had a GSOC student called Jason Peskos who just sort of thought, hey, I want to implement this inference over a hidden Markov model. And I was like looking for implementation. We found hidden Markov models from Bill or Guillaume Dalle, I think. And he just put that into a Turing model, and it worked. Super nice. Similarly, differential equations is .jl. People just solve differential equations inside of a Turing model. This is probably when you look at research papers, this is really what people use very, very often, just because differential equations.jl is fantastic. So briefly, what's next? It's not that much, actually, which is quite nice, standing here and be able to say that. There's some like internal changes that needs to happen that will have performance improvements and also improve extensibility. Not super interesting for you guys. Now, one thing that we're really lacking is like just like documentation. Like that would be like the #1 priority going forward. Will just be to document everything. For example, recently, like turinglang.org is the website that we have, and we've got a huge overhaul thanks to Shravan Goswami. And another big thing is that enzyme.jl, I mean, most people have probably heard about it, like it's fast, and we've also seen that it can be quite fast when it works. And so now we're working quite actively with William Moses or Billy to actually make enzyme.jl work on kind of arbitrary Turing.jl model. And so that was like something we're quite excited about. And maybe, hopefully very soon, Turing.jl version 1.0 should be released. And that should be, I want to say give an exact date, but it should be like fairly soon. This is like obviously work that's been done over like tons of years together with a bunch of people. So here are more people, and obviously like everyone has contributed to Turing.jl and the Julia ecosystem as a whole. Thank you very much for listening.
Thanks, Thor. It's a great talk, great progress. Do we have questions from the audience? Yes.
Look behind you.
Hi.
Hi.
It's a bit loud. Yeah, thank you for this nice package. I really like Turing.jl, but maybe it's kind of not harsh, but support for state space models, and especially when you take in posteriors, is a bit verbose.
Yep.
Do you have any plans to maybe make it a bit user-friendly?
Yes, I mean, so there's actually there are people in our, the Turing-Lang team effectively working on this basically. And actually, they're specifically working on making state space models easy to implement. And we also have a person working on implementation for something called basically Julia bugs, which is a bugs version, like kind of similar thing, re-implementation in Julia. In which case, it should be much easier also to make use of more information, because then you actually have access to the full DAG of the model and so on and so on. So there is actually work being done on this. I don't actively work on this, so I can't really tell you that much about it, but there is definitely people working on this specifically.
Yeah, cool. That's great. Awesome. Thank you once again.
Thank you.
Maybe a follow-up question from me. So you mentioned that the PPL in Turing is pretty flexible, but I imagine it actually also makes it difficult to analyze the structure of the model and maybe to find the conjugate relationships between variables to make it more efficient. So is there any plans to actually go in this direction?
Yeah, so exactly. So Turing.jl, it's we make really no assumptions about the model, and so we don't really have access to the DAG, for example, at least not at the moment. But there's one person working specifically on Julia bugs, which is like a re-implementation of this old bugs PPL. And that case scenario, you actually do have access to the DAG, and then you can do conjugate, exploit conjugate relationships and these kind of things. But that is more in the development stage, and so I wouldn't necessarily say that go and use that basically. But it is something that definitely that's being worked on.
Cool. Yes, we have more questions.
Yeah, thanks a lot for your talk. Great progress. I'm curious about the state of variational inference backend within Turing ecosystem. How is that doing?
It's not. It hasn't really been great. Yes, I worked on this as a GSOC student now 5 years ago. But basically, Kyrie here has been doing a lot of work on this actually quite recently. So he's been really taking ownership of this stuff and really working quite actively on it. So I would say right now it's not the best. The thing is also if you compare it to say PyTorch or these sort of Python-based PPLs, which are fundamentally based on these sort of neural, these deep learning frameworks. This is kind of what they underlies them. They're also just better suited for doing variational inference, I would say, just because you generally typically when you do variational inference, I mean, it depends on what kind of families, but very often if you just want to throw something at it, often people use neural networks and so on, and then it's quite easier to do it with something where you have a deep learning framework. But so right now, I wouldn't say the support is the best. There's support for ADVI, and Seth has implemented Pathfinder, and there's nothing stopping you from implementing whatever variational inference methods you want. It's really just it hasn't been a huge priority. But as I said, Kyrie has been working very, very much on it quite recently.
Yeah, thanks.
Do we have more questions? Yeah, we have more questions.
So we heard about RxInfer earlier today. Would you mind highlighting some of the strengths and the weaknesses and maybe how those two packages compare?
So I unfortunately arrived like half an hour before my talk, wading through the rain. But I have looked at RxInfer like quite a few years ago, so I'm not fully up to date on it. So I think he might be able to answer better on that. Yeah. But basically, like RxInfer does this thing where it's able to exploit conjugate relationships, as far as I remember, and it does it it means that you can very much do like inference in a very streaming fashion. So Turing.jl is more like you implement a model, you fix your data, and then you run this kind of expensive like inference algorithms for that particular data. If you want to update your posterior, unless you want to do like start like hacking on your own, you kind of just need to redo this entire process again. While, if I understand correctly, RxInfer is basically like you just pop on another observation, then the posterior continues onwards, basically. And so I think that's a huge, huge difference, is that the conjugate relations is exploited in our RxInfer, and that just makes it way, way more efficient, right?
Yeah, I want to say that this question was not staged, but I'm actually the main developer of RxInfer, so I can also add a little bit. From my perspective, I think Turing focuses on universality and user-friendliness, and it's really great, but it uses sampling-based methods, which makes it a bit less efficient. And RxInfer really focuses on efficiency and scalability, so it really tries to exploit the structure of the model, so we create an actual graph. And we do message passing is a completely different technique, differs from message passing. So it really depends on your application. And I think, yeah, you just need to decide what fits best. Turing is best, if you really want this universality, and RxInfer is best if you want to process data in a reactive manner as efficient as possible. That also requires you to think a little bit more about how you define your model.
Thank you, both of you.
Thank you.
Do we have more questions? Okay, then we close the session. Thanks very much, Tor. It was a really good talk, really amazing progress. And we have lunch. So everyone is invited for the lunch.
Nice. Test, test. Hello, everyone. Welcome to the afternoon session of the last JuliaCon day. For our first talk in this session, we have Chef Jorge Vieira, and he will introduce Julia.Kitchen, the finest Julia recipes. Jorge, the floor is yours.
Britney Spears now? Yes. Thijs? Unplug it. I know why. It's my fault. 1 second.
Hello.
Hello.
You should see your screen here.
I should see it? Okay. Usually you see the clock.
Now it's working.
Now it's working? Oh, there you go. Nice. I don't see. Switch. No. Yes, finally. Okay. Thank you. Sorry about that. Now we just wait 1 minute. Good afternoon. Thanks for joining this last session at the last day of JuliaCon 2024. So my name is Jorge Vieira, and I'm going to talk about Julia Kitchen, the finest Julia recipes. So what is this story? So who am I? I already said my name is Jorge Vieira. I happen to be the patterning modules and algorithms architect at ASML in Julia. That doesn't mean much. The only thing that means that I get all the complaints by the users, like, oh, my module is not working. Oh, I don't understand how this works. Oh, please, could you explain how this works? I don't understand how, and they always want to know more about how things work. So this is just a thing that I start to think of how to do, not only for work, but also some of my friends told me that, oh, yes, this Julia thing is kind of hard to get into. So I thought, okay, maybe it's something I can work on my personal time, and that was the first problem. So what is the problem I'm trying to solve? As I mentioned, I want to help the new people to get the new people, that's a very important thing, and the current people to learn and use Julia more effectively. In my opinion, maybe I'm a little bit biased, right? Technically, Julia is the best programming language for scientific computing, but documentation needs some, well, it's an optimization problem, so we need to optimize it a bit more. I heard it that right now we were at the Julia survey, and only 30% of the people, maybe 32 or something, I forgot the exact number, thought that the documentation in Julia was great. I wonder who that 30% people are, but that was what people that are already biased towards Julia said, that, oh, documentation is great, only 30%. So I think we're getting to something. So that was the survey, but I also hear these things from my colleagues and friends that they tend to say this, like, okay, with Python or MATLAB, I can Google my way out. I can look in Stack Overflow. I can just find like gazillion tutorials and recipes in Python. In MATLAB, it just has a very nice website. So yeah, I can Google my way through. But in Julia, I also struggle. So that's what they tell me. Also, they tell me that, okay, I found this discourse thing. Oh, I see that the Julia people interact over there. But then I copy some excerpt from there, try to run it, and it doesn't work. So, okay, that's another thing that they hear. Another one is, yeah, well, maybe that's not mine, but they say, okay, there's usually some Julia documentation, sometimes only the README, and the README has exactly one example where the package author wants to showcase everything from his package.
has one very simple example, and let's throw everything and the kitchen sink at it. And it's very hard to understand how that package works. Finally, and maybe this is because the way Documenter works, I think, most of the documentation in Julia is more like a reference manual. So we are kind of like just documenting our functions using doc strings. And what that means is that tutorials are always kind of, there are great tutorials out there in Julia, but not for everything. And also examples sometimes are kind of, as I said, either the very basic ones or the most complicated ones. And it's very hard to progress towards your Julia learning experience. So that's what I usually hear from colleagues and friends. And I thought, okay, let's take a look on what's out there. So maybe I can just go out of the web. Let me see if I don't screw it up. Yes, okay, good. So first, I thought, okay, let's look at plots. That's why people usually look into Julia. So let's look at plots. How do I use I don't know how to use this keyboard. There you go. I have my personal keyboard. So there you go. So this is the plots tutorial, the website. Looks fine to me. It explains how to plots, okay. How to install, no internet, of course. That's why I have screenshots. Yes. Yes. Forgot to check that. Then we go with the screenshots, it's fine. So, well, okay, I check about the plots, and I see, okay, you have basic plots, you have everything grouped as plot attributes. It's kind of fine. I mean, it's just very straightforward. If there's a gallery somewhere here, the gallery is also fine, although there's not too much explanation over that. If you compare that with Matplotlib, Matplotlib has a different approach. And now that I cannot see the live version of it, can I just quickly connect? Maybe that, am I too optimistic? Can I try? This is already recording in YouTube. All my failures are recording in YouTube now. So how was it to connect? Wi-Fi, PSV. Do I need a special thing? Website. Any website? Yay, okay. I also need a tutorial on how to use my computer. Okay. No? Okay. Yeah, okay, whatever. It's okay. We can go through it. You can imagine. So what happens is that, what I'm doing, this has to be function, there you go. So what happens in Matplotlib, all the tutorials are kind of organized, and they have a gradual way of explaining things. So we say, okay, this is a line plot, fine. This is a scatter plot, fine. And then gradually explain every single kind of plot. It's a bit more didactical way of explaining how things work. So it's kind of easier to follow. Similar thing with the MATLAB website. So you go MATLAB. I know we don't like MATLAB, we don't like Python, but their website, the tutorial websites are amazing. So we should learn from that. So in case of MathWorks, I don't know if you can see it over there. So it has normal documentation with the functions, with some examples for each function. And then they have several sections with examples, more functions, so more cross-references. And that works quite fine. So it means that for newcomers, they can just start like copy-paste one small excerpt, and then you just go through it and learn to the next part. But in the end, it's a matter of taste. In the case of the plot ones, yeah, it's a bit like all on your face. Here you go. You sort it out yourself. But in the end, I think it's okay. It's not too bad. So the look, I would say, is about the same. For those, about the same. For MATLAB, for sure, it's well more polished. The simple examples are fine. The problem is when you want to do more. So the simple things are not the problem, but the problem is when you want to do more. When you want to have cross-references. I didn't show beautiful Mackie because I don't have a internet connection because I forgot. But Beautiful Mackie, it has a similar problem. So Beautiful Mackie has very nice galleries, and you can, in principle, you can copy-paste the code, and it happens to me that it's a hit and miss. Sometimes that code works, sometimes it doesn't work. It's not a critique on Beautiful Mackie, this is just in general. Because the code that's there is not versioned, so you don't know which version of Mackie was it generated for. So that's what I've seen. Also, references, yeah, it's kind of hard to link things in between. But okay, maybe I'm biased with plots. Let's look at another one. So similar thing happened with SciPy, and I thought, okay, let's look at optimization. They usually optimize this Rosenbrock function. They always have the same example. How does that look in SciPy? Well, okay, it's just, I'm not looking at the content of the language, it's just about the layout or how it is presented. So it's presented in a simple way. They have a small example here, a small introduction that the example minimizes this routine with the meld-or-meet simplest algorithm, doesn't matter. And they have this function. They don't explain that much, but doesn't really affect that much. And then just have some example code that you can just copy-paste. I checked back on the Wayback Machine. It's the same example that I used in 2002. So this hasn't changed in 20-something years. So I think that works for them. Well, okay, what happens when you don't make the correct screenshot is that you get a nice sad face. But that was the one for Optim. That was also a similar thing. It was almost the same, exactly the same example. So I will argue that was exactly the same. The difference that I found here was the MathWorks website, where I could actually not find the same example in the official MATLAB documentation. I had to go a little bit deeper. And I don't know if you're familiar with the MathWorks ecosystem. They have this thing called file exchange, where users can just exchange their own scripts or libraries, and you can just download them. And it's kind of nice because other people can just download. So it's a nice showcase of what you can do. They also have some functions and explain that and have some version history. So like, oh, that's maybe something that we could use, something that we need. Also something that didn't show the MathWorks website, they also have some interactive code. So you can click, and if the MATLAB something window will pop up. I don't like those pop-ups, but I like the interactive window idea. So I thought, oh, we can also use something like that. So what were the things that we can learn from this? Okay, what can we learn? So I could not show the Optim because I didn't learn my lesson. I should have connected to the internet beforehand. But what happened is that Optim, the example at least was almost exactly the same. It was the exact same one. It was a bit more verbose and a bit more technical on the Julia side, but it was kind of okay. The one in MATLAB, well, you saw, is more polished. It's easier to replicate, and it's interactive. Also, the examples are segmented. I cannot show that, but the examples are segmented. So maybe we can do something like that in Julia. The content, I'm pretty sure we can generate that. That's not the problem. The problem is how we frame it. So if you explain something, what happened here? So with fancy keywords, guys, unplug. So if we do some things with fancy keywords, then yeah, it gets very complicated, and then people don't understand what's going on. No? If you come from academia, hello.
No work?
No? Let me do this fancy trick. There you go. You can connect the HDMI over there. Yay, okay. Whew. Problem averted, more problems. So it seems that to them just technically challenged, so it's okay. So, so this Optim thing is very similar, and then what I've seen is that the content is exactly the same. The difference is how we frame it. We like to put it in very complicated ways that maybe it's technically correct, but that scares people away. And also sometimes the way the things are laid out, the version numbers, they're not in the right place. So I have more observations. Again, this is just not a critique. It's just I'm trying to improve things. And this is what the things that I think they need to be improved. So because we develop modules, all documentation is per package. So they're very package-centric. Sometimes we think, okay, we should have some connection with this A and B package, but that's not very comprehensive. And sometimes, it's version per module, but not version per interaction. Again, as I said, we tend to write it as references for doc strings. Tutorials are sometimes short or convoluted. Sometimes we only have a README file, especially on the modules that I like, unfortunately. And not many examples, or as I said, the all and the kitchen sink examples. Cross-reference doesn't happen a lot, again, because we're always focusing on our module. The exception is maybe when ecosystems for SciML or for which other ecosystems do we have? Tell me one. Okay, so for SciML that happens, or for galleries like in Beautiful Mackie, we can cross-reference all other modules, but not all the time. And what happens is that, yeah, we don't version the workspace, so maybe we can have something like that. So maybe with a new workspace feature in Julia 1.11 or 12, we will be able to do that more easily, but we don't have that right now. So, and what happens is that eventually all the packages, all the documentation gets out of sync. Why? Because, well, let's be honest, nobody wants to document. It takes a lot of time. It's hard to keep things in sync. You have to test a lot of stuff. So it's hard. And also writing clear documentation, it's also hard. And we have better things to do. We want to code. We don't want to document. So in the case of MathWorks, they have a team of people just writing documentation. That's their day job. Just one documentation. They curate all the examples. We don't have that. So, so in the end, what happens is that documentation is not very fluid, so I would say for new people, or even for not so new people, but you just want to do things fast today, not in 2 days. So I should hurry up. So I found out that, okay, these are the documentation requirements that we need. So we need to have something that's reproducible and version per group of packages. So that's very important, reproducible, such that when you copy-paste the example, it will work. And at least you will know which version for it will work. It should be easy to navigate and to discover. So when you go to the website for SciPy, or not SciPy, for plots, well, you go to one for SciPy, it's very easy to navigate and find what you're in. If you go for the same thing for SciML, sometimes are not so clear where you should go. As I said, we don't want to put too much effort on updates, so it should be easy to maintain. I mean, at least you should tell me like, oh, this thing broke, please fix me. We don't have that for documentation, I think. And as I said, we have to write 4 different examples. So the workshop at the TUI, I saw that it was documenter-centric. Maybe you should have a better guideline on how not to make anything that's not module-centric, something that's more about the user experience. So a tutorial on how to get started with your module, have some examples with increasing difficulty, maybe suggest a minimum number of examples per module or something, and cross-reference other things. Also references, and if it's interactive, that will be the cherry on the pie. So this will be nice if only there will exist a hub for Julia, you know, something where we can just put things together. There will be something like that. I don't know if some entity exists that could do that and would like to take that over. I don't know, anyway. If they exist, I think they have other interests right now, and they don't want to take over this task, which is very hard. And then I thought, okay. Then one of my best friends convinced me, yeah, why don't you do it yourself? And I was stupid to say, yeah, why don't I do it myself? So that didn't work out well. So, and I will tell you exactly what happened. So what happened? This is what happened. No idea. Yes, we were happy. I told everybody, and that never happened. Why didn't it happen? So, well, my first attempt failed. I thought, okay, we'll do it with Documenter or with Franklin or something, and didn't work out. So, this is a learning opportunity. So, what happened? So, first I got the nice name, which is Julia.kitchen. I bought the domain. It was available. I thought, okay, we can put all the recipes, what I told you. They should be versioned, as I told you. They should be easy to navigate. They should be interactive. We should have all these examples in a gradual way. And should tell you exactly when things break, when packages are updated. Then I got very excited. I submitted my apps to JuliaCon, and surprisingly it was accepted. And then thought, okay, well, now I have to work on it. So I tried to put some things we're working on. First I tried with Franklin, but I thought, okay, if I want to do this with Franklin, I have to write the whole thing from scratch. So that's not going to work out for me. So, okay, what's the next thing? I kept looking for other stuff, so I tried Literate. Literate was, okay, at least I can have versions, but it's kind of reproducible, but the other parts is, I mean, the layout is kind of fixed, so you need to change it if I want to, and better template stuff. I don't want to do that myself. So it was still not super easy, but at least it supported some interactivity, I think. I now remember, I forgot what I put that over there. But then, okay, if I want it interactive, the obvious place is Pluto, right? So I thought, okay, these are my requirements. I thought, okay, I think it could be done. I just put some shell around it and try to make it happen. So I talked this with fonts, and font said, like, no, dude, that's not going to work out the way you're describing it to me. So look for a different solution. So like, okay, dreams shattered. Let's do something else. Let's look around. So back to square one. So let's look outside the Julia ecosystem. So I look for all the things outside of the Julia ecosystem. And I found this thing called MD Book in Rust, which I don't know if you know it. It has a very nice, so the Rust book is written like that. So it has these interactive snippets of code where you can just change your code and it compiles on the fly. It works quite nicely. It generates, it's markdown based, so you can just write your tutorial. It's basically as Documenter, but in Rust, but interactive. I thought, oh, maybe it can work in there. So I realized that the interactivity only works in Rust, so you have to plug in your Julia stuff, and then what happens is that time ran out. So as I said, I was only doing this on my free time, so that didn't work out, unfortunately. But these are the lessons learned, so I will keep trying. I will see if I can make it work still. So sorry, that was anticlimactic, I guess, but we can learn from that. I can learn from that. However, I want to give a shout out to logs.jl, which was the best documented package that I could find. Like it's exactly what we need, I think. So it's easy to discover. The tutorials are gradual. The manual is clearly divided into, this is just for you to learn. This is the API stuff. It has cross-references, its version, and all the modules, and all the examples work. You just copy-paste them work. So it's just chef kiss. So I will try to use whatever they use to make Julia Kitchen work. And so I will contact them. So I don't know if there's a logs maintainer over here. I will try to contact that person. And I will use that. So the main takeaway of this is success is the ability to go from one failure to another with no loss of enthusiasm. So I'm still enthusiastic. I still think that we need to do this, because otherwise we will keep having people saying, oh yeah, Julia's too difficult. Oh, I cannot learn anything, Julia. Oh, it's very hard. And I think we want more people in Julia. We want to fill in the stadium, right? So with Julians. So that's what we keep trying, and I will try to do that myself. So if you want to join the cause, and you are better at me at defining how these things work out, please let me know. Thank you.
Thank you for the talk. Do we have any questions from the audience?
Careful with your finger.
Thanks so much for the talk, and I'm really looking forward to seeing where this goes. I wanted to ask, in your quest to build a unified kind of one-stop shop for documentation, what I've gathered from this conference and this community is that the kind of developer-user ratio is a lot larger on the developer side for Julia than, say, Python or MATLAB, maybe even Rust. I don't know much about that community, but it seems like there's a lot of developers for the community. Does that play any role in how you think Julia packages should be doing documentation, or should we just kind of apply what would be best for users, for developers as well?
Oh. Thanks for that remark. That's an amazing remark. Yes, indeed. I think that's exactly the problem that we have with documentation. Because developers, we don't like to document. Let's be honest, we don't like. We like other people to use our packages, but it's like writing our thesis. That's just a delay, like, oh no, I just want to do the minimum. It's fine. And I think that's what drives the documentation. That's why the way it is right now. It's just reference-centric. We can deal with that. If it's not complete, go and read the code. That's perfectly fine. If you need an example, I don't want to write one. Just go and ask me in a Slack or Zulip or whatever you prefer on Discourse. And we can deal with that. But not everybody is like that. So maybe we want to keep it like that, just to keep only the developers into the community. But if we want to expand, we need to make documentation not only for developers, also for new people that want to use our tools. So yes, indeed, I think that's exactly what's driving the documentation right now. That's why it has that shape, because it requires a special kind of person to be very happy about writing documentations and writing documents. So I think MathWorks is a kind of pouching those. Maybe you should get a few of those as well over here.
I look forward to seeing what happens.
And me too. And I hope that there's some kind of hub for Julia. They will support on that.
Thank you. Any more questions?
Yeah. Okay.
Thanks. So you had this role discoverability, I guess. What makes something better or worse in discoverability? And how could a backend be assistant with this? Like, it seems like this is, are you going for search engine optimization or?
Yes, I think I understand your question. So it goes in two levels. First, it was search, not even search like Google, you mean? Like that I think what I do right now is just I want to do something in Julia programming languages. By the way, everybody that should look for any documentation of any sort in Google, just write like optimization in Julia programming language, because that's how Tyobe measures what's the usage of Julia. So just every time you look for anything Julia, just type whatever you want, Julia programming language, and that's how you bias the algorithm, and then we'll be higher in the rank. End of side note. So what we want to do is just have a way where you can look for, let's say, I want to make histograms or histogram plots. Okay, how do I do that? If you go to, you type that in Julia, it will lead you to either the plots package or distributions package. And the distributions package show you how to plot a little bit, but it's not very extensive. It talks more about the histograms themselves. The plots package, or Mackie for that matter, or algebra or graphics, that shows you how to just do some bar plots and doesn't tell too much about the histograms themselves, how to combine both. So maybe we need some recipe I can tell you that. So I would like to have a search engine that can catalog those kind of examples so you can look for that. And that's one aspect of that. The second aspect is just the UX. How do you specify the layout on your website? Because otherwise, it's very hard to find.
Thank you. Time to move to the next speaker. Let's thank Jorge once again. Our next speaker is Lilith Hafner, who will introduce Python.gl to seamless blend Python and Julia. Please join me in welcoming the speaker.
All right. Hello, hello. Today, I'll be showing you Python.jl, which is a seamless blend of Python and Julia, which you're going to realize you're going to want to seam. Let's see. Could we get a... Oh, it's working. How delightful. OK, so this is a Julia REPL using Python. Isn't that great? What a lovely package name. And I can now use Python. So like I can do a for loop with Python syntax. That should work. And that println, that's a Julia function. Isn't this delightful? Mix and match. OK, but there's more. You can use, this is actually a superset of Python, this programming language. This like, once you say using Python, it's a superset of Python. So we can use classes. I'm not retyping this. So this class, for the folks who don't know Python, this is a class. It's an object. We've got an init function. We've got this self. You know how Python works. OK, I'm not explaining Python very well. And then this rand function. Rand is not a function in Python. That's the Julia function. So let's just define this class. And then let's make rn equals rand near 1,000. So what this class does is it returns, when you call gen of it, it will return a random number near that. So I can do like rn.gen float 64. So that's going to be a random number near 1,000. Hey, look. And I can ask for an int 8. Huzzah. It's another random number near 1,000. So we're just like mixing and matching Python and Julia. Yeah. And the performance here is great. Gotta have good performance or it wouldn't be a good mix and match. So let's say my range equals this times some, OK. You know, that's pretty quick. And then if we do a bigger one, I mean, Python performance, but oh, no, it's Julia performance. Great. Instant. Love that. Yeah, so it can do all the things. Time to first plot, if any of you have heard of that. Let's see. OK, it takes a bit. You know, pretty reasonable, solving time to first plot. And, oh, love that import as syntax. Hopefully we get that in Julia soon. Oh, and we still have Julia packages, of course, like grass. OK, we'll get back to this. And you can do cool stuff with Python, like, we need to, using Python, and then, like, I'm going to import web browser. I'm going to, it's just cool to be able to do all the Python things. I'm just launching my presentation right now. Give me a moment. OK. Adding a button. Like, I'm making a GUI in Python because Julia needs better GUIs and better time to first X. That's why we make packages like this. Window.main loop. Yeah, there we go. And now here we have click me. I'll click that. Let's see if it's finished precompiling. Nope, not done. OK, let's do a presentation. There we go. OK. So Python.jl, hello. These are the slides, QR code if you want them. Seamlessly blend, you will want to seam. OK, the demo, that already happened. There's a bug. That's fine. That's not supposed to be in the slides. So Python.jl is a new front end for Python call that leans all the way into automagical. So there's this scale where over here is kind of like sane and reasonable, but also like everything has to be explicit. It's a little bit laborious. And over here is like kind of intuitive, automagical, does the thing without prompting, automatic conversions. And so PyCall is over here, and Python call, the successor of PyCall, is over here. And I take Python call and I wrap it way over here. Gotta make everything automatic. Yeah. So this is great for demos and sales pitches. I could be telling y'all that this is the future of programming languages. It's not, but if I wanted to sell it, that's how I would do it. Magic is great for that. It's OK for like scripts. You can run scripts with this. It needs work for anything that's like shared, for packages, compatibility with the ecosystem. OK, a little side note here. The whole unreasonable effectiveness of multiple dispatch is based on people doing work behind the scenes to make sure things are compatible. It's not something that just happens. It's something that looks like it can just happen, which means people can do the work to make it just happen for the user, but you got to do compatibility with work by hand. Also, bugs and edge cases, like array indexing, is that 1-based or 0-based? Hard to know. Hopefully somebody will ask some good questions in Q&A. So how does this work? We've got a split runtime. When you call using Python, it launches a Python runtime. So now we've got a Python runtime and a Julia runtime, both present. So when then you give code to the REPL, it parses it. It tries to compile it in Python, because Python has a compiler. And if the compilation succeeds, then it runs it in Python. Otherwise, it runs it in Julia. That's great. That seems like a great option. Not going to hurt anything. And then globals are just automatically transferred. You set a global in Python, transfers to Julia. You set a global in Julia, transfers to Python. And so that's how we can, for example, have the Julia standard library in Python and the Python standard library in Julia. And this whole thing is less than 200 lines of code. I think it's 181, which is kind of cool that it's that easy to make something that looks so promising. So, So yes, it's a joke. I don't think people are going to be using this, should be using this for production code. Like, this is not Python call. This is not something that we can use in diffie-qpy. But also, it's not a joke that you can make a DSL that does really cool things very easily and very seamlessly in the REPL. And it's not a joke that the grass is still precompiling. Yeah. And for something less ambitious than a full programming language as a DSL, I think something like this is much more plausible to work out all the bugs from. So yeah, learning that Julia's incredibly hackable, that magic looks cool, but I mean, we haven't learned that it's hard to make robust. I'm counting on questions for this. I'm not going to show you it going wrong. Yeah, I saved a lot of time for questions. I have more. I can talk more if there aren't enough questions, but let's see. Yes.
So Python set syntax is curly braces. And their dict syntax is curly braces.
Yeah.
Julia's where clause is curly braces. How does that do?
Yeah, well, let's see. So if you want to declare a dict, you could do something like dict equals, what is this Python syntax? Like x:3, y:7, 4? That's not that. OK. Cool. Oh, how do you do dicts? Cool, cool. Yeah, OK, great. So that works. And then for like where clauses, so like f of x colon t, where t equals. Where t, yes, great, great, great. Cool, so then f of dict should be a Python dict, right? Yeah, works fine.
But why isn't it parsing that T as a set?
Oh, well, because it's a where clause.
Oh, no.
Next question, please.
Macros, question mark?
Yeah, macros work. Like the @time macro works, but we could do @threads. Yeah, let's do. Okay.
What about like code lowering for these mixed Julia Python things? What does it do with that?
Oh. What's this?
Capital T threads.
Sorry, live coding. Is it base.threads?
That's good.
Ooh. So it's using, so the problem here is that Julia and Python have range exported from their respective standard libraries, and it's kind of assuming that this is the Julia range. So I would have to say like something like that, and then it would work. And they're all in order because I'm in single-threaded mode. And you asked about code lowered?
Yeah, like what happens if you do that with with some of this like mixed Julia Python syntax?
Yeah, so if I, like when this thing that was, so this is going real fast, so the code lowered has to be neat. Yeah, that seems like it works. Decorate? Okay, I'm not good at Python. Sorry, how do we do, or? I heard decorators are a mess in the REPL, but maybe it's better here. Anyone confident enough in decorators to, like, let's skip that, because I don't know what a decorator is.
Two questions. Question one, how?
Aha!
Question two, why?
Okay, so question one, how? That's a great question. And the answer is, I'm still doing magic. Like, this is actually running live, but it parses either in Python or in Julia, depending on whether it can correctly parse in Python. So the real answer for how this where clause is correctly interpreted is this is not valid Python syntax. So it just parses it in Julia. And this is valid Python syntax, so it parses it in Python. And you can't actually mix syntax. It's the syntax of a REPL entry or a top-level statement in a file has to be homogeneous. So the syntax can't be blended, but because the global environments are blended, and so much of what a programming language is its standard libraries and namespaces, it can actually, it looks like there's a lot more blending than there actually is. The blending is just like pick which to interpret. Why? I think I was working on blending the languages in a more sensible way, and I thought, why not take this to the limit?
I have a kind of usage example. Okay, we have a team that develop AI models in Python, and we also need work in Julia, and I want to plot graphic things, and I need to extract the data from simulating. So I need a bridge in data frames. So the data frame could be you fetch some data on the Python side, and then you use it on the Julia side.
Yeah, that seems, oh wait, you get the data on the Python side? You want to use Python for ML and Julia for plotting?
Well, I have to work with that.
Okay, cool. Yeah, I mean, let's see if plots is, no, okay. So you're going to have to wait for pre-compilation. But yeah, I mean, if you want to deal with a system where like the REPL's just kind of guessing for you what language you're using at any given moment, that could work in principle. Like when I did this, that's passing a vector of float64 straight to a Python function. And that's all using Python call.jl plus a little bit of type piracy to make the conversions a little more magical. But that's like totally, yeah, you can totally transfer language. And you can also do that in a sane, sensible way with Python call. So yes, can do.
Thanks for this amazing vision. I was wondering, right now what you do is you try to parse it in Python, and if it doesn't work, you go to Julia. What I want to do is, if both parsings work, pick one randomly. And I'm wondering, what would be the most interesting consequence of that, in your opinion?
Oh, indexing.
Thank you. Two very distant questions, but the first one was, did you call a variable dict beforehand?
No. Yes. What? Oh, I did? Oh.
So that's a Python keyword.
Oh, that's fun. So like...
I love this.
Dict is a Python keyword. How do we use that?
Yeah, you convert something to a dict.
How do we... Yeah, so the trouble here is that I assigned a variable to dict, which is something legal to do in Python, and maybe, let's see, let's get up a real Python. Yeah, and so then if I now call dict, I get that same error. So because I assigned to dict, it's not a keyword, actually. It's just a built-in.
Oh, okay. So I guess my question then is, how does it work with keywords?
Yeah.
In Julia versus Python?
Yeah, so it's the same like clever, the like clever auto parsing. If it's using Python keywords in a way that Python keywords aren't supposed to be used, then the Python compiler will fail, and then we'll use it in Julia. Whereas if you're using, or if you're using Julia's keywords like struct, Python. Yeah, so like this will correctly define a struct, and then I can make a of 4. And if you want, like, say, struct, I heard from Oscar struct equals 1, but we can just do struct equals a of 6. And then struct should be, yeah. You see, just a little mix and match. Yes, they're in the back.
Cool. Shall I? Okay, you ready?
Got it. Unlike some exceptions, perhaps, but let's say I'm scared that I might accidentally type in the wrong language, and I want it to behave predictably. So, would it be possible to add a feature where you disable the Julia parsing, so if the Python doesn't parse, it just errors out?
Yes. Yeah. Over there's a question.
What in the world is the? Oh, sorry. What in the world is the type of a paren 6 that you've turned struct into? In Python, you could just call type on a thing.
Yeah, sure.
You just call type on that. What? Because that. Okay.
So what's going on here is that this is all just Python call with, yeah, okay, yeah, it makes sense, great. Frames?
We do have a number of other interrupt libraries like rcall and several others. Can we do more? Can we keep going?
So yes, I think that the way that I would recommend, I don't know if this is a good idea or not, but I think determining what language something is written in is a great task for a large language model. Maybe we could pass it to a large language model, because we got this suggestion to use a random number, and I think that's a good alternative. It's not a random number, it's very reliable, it's like 99% reliable, which is perfect for a programming language, because you need that kind of high reliability. And so I think that if you have a large set of programming languages, you could pass the source code if you can chunk it in some language agnostic way and then pass each chunk to the large language model to dispatch to an appropriate runtime.
So are you proposing a Tower of Babel.jl? Just write once, runs in whatever language it needed to?
Yeah, it would be, you could just use, it's not write once, runs in whatever language, it's write many times, run all in the same language.
So one further question, why has no one stopped you?
So I stopped myself. I haven't decided to register this in general because I'm concerned that people might take it a little too seriously. The last time somebody made a silly superset of Python, and like the last 10 times somebody's done that, it's been very well funded and a big waste of time, and I don't want this to be the next version of that.
So, can you define a Python class and do multiple dispatch on it?
Ooh, how can I pretend to do this on stage? I mean, with interface traits or some sort of way to dispatch on traits, yes.
That's cheating.
Yeah. So the tricky thing is all Python types are... Okay, yes, we can do this. So g of x int equals a, and then g of x, we'll just do, like we can dispatch on a Python int versus a Python object. That's not an int because the ints automatically convert. But if we have two different non-automatically converting Python classes, JuliaCon represents them both as
pi, I think.
Yeah, I think so. Yeah, so they're both pies. All the things will be pies. And so it would be possible. It would be, the options here would be either to make different Python types turn into different Julia types, which is kind of a problem because in Python, that would make all calls to Python type unstable. Because you know it returns a Python object, but you don't know what, because we can't run type inference through Python. And that's why Python call chose to make all things return pi. We could just automatically convert pi objects to like silly pi, or I don't know, like magic pi, with a type parameter that is maybe a string, a symbol that represents the Python class name, and then you do dynamic dispatch based on name with no name spacing. So it's possible. You could also do it more sensibly. I think there's a way of extracting a symbol representation of a Python type that is globally unique. And so that would also be, then you could, yeah. So if you're willing to suffer all calls to Python being type unstable, then we can do that.
Thank you so much.
Could you actually make it, because Python has super type, right? So you could theoretically make pi any a subtype of any and then embed the Python class hierarchy in the Julia type hierarchy.
Yeah, and then we'd have to define new types on the fly when new Python classes are defined as part of the global variable transfer. Yeah, That could work. Then we'd have dynamic dispatch with subtyping. Yeah. And it'd be multiple dispatch, of course.
Does this mean I can finally use Python type annotations in my Julia code?
How do you do a Python type annotation?
That was the correct answer.
The correct answer is we already have comments.
But
oh, there's somebody up there. If you just shout it, I can call it back. So from the audience, great suggestion. Could you just have like a Python REPL mode, basically? Press a key to turn to Python, press a key to turn back to Julia. Yeah, you could totally do that. That would solve the whole switching modes based on guesswork issue. And then we'd just be left with Python call plus global variable transfer, and that merging the namespace, which I think could be workable. Yeah, also up there. So the question is, what if you want to call Julia code from the threaded Python code with a global interpreter lock? I think that should probably be fine. I mean, that's a Python call question. If it works in Python call, then it works here. If the Julia functions are treated as external code, I think it could run asynchronously. But I don't know. That's a Python call question. All right. I think that's all the questions. And oh, yes, Frames.
How much type piracy?
Let's see. Definitely not any. So just like redefining the basic operations on Pi. So it's not pirating base, it's just pirating Python call. Is that our time? Okay.
We have time for one short question, if there's one more. Okay. If there are no further questions, let's thank the speaker for a very interesting talk. Yep. And our next speaker is Miklos Koren, talking about Catchy.gl, a data analysis package for economists. Please, the floor is yours. Let's welcome the speaker.
Hello, everyone. Thanks for coming. So my name is Miklos Koren, and I'm here to talk about KZJL, a data analysis package for economists. And this is joint work with Gary Atilakish, who's sitting here. So before we get started, just a few words about myself. I'm an economist by training, and I make it my mission to teach my fellow economists some computing best practices to help maximize the impact of their research. And I teach economics at the Central European University in Vienna. I'm also the data editor of the Review of Economic Studies. So that's one of the leading journals in economics. And there my job is to review the code and data that the authors are submitting to the journal. So these are like the supporting materials for the articles. And I develop educational materials and software at my business, Coded Thinking. Now you also get to know a person by kind of the company they keep, or in this case, the programming languages that they use. I've been using this programming language called Stata for more than 25 years. So by the way, Stata is a registered trademark of Stata Corp LLC. I'm not affiliated with them in any way. This talk has not been endorsed by them, and I hope that by the end you will see why. Since 2003, I've been using Python. I use it, so Stata is for statistical analysis, plotting, model building, and model fitting. So Python I use mostly for data cleaning, web kind of work, web scraping, but not really for statistical analysis. And I'm, of course, a big fan of Julia, not surprising. By far my favorite language, and I use it for model simulations. But again, not really for doing any statistical work. So at this point, you might be wondering, what is this data that economists are so fond of? So I don't want to extrapolate from my own personal experience, so I brought you some data. So if you look at the replication code, the research code that authors are submitting to our journal, then we get some data. So these are some of the best economists in the world, hopefully submitting some of their best research. And so we looked at, with Gary, we looked at 357 replication packages to see what do they do, what kind of programming languages they use, and how do they use them. So when it kind of comes to comparing programming languages, we can have some hard data. So the first thing to note is that economists don't really use Julia. Okay, so only about 3% of the replication packages have at least one JL script in them. Okay? So even Fortran or the various flavors of C are more popular among economists than Julia. Okay? So that's a sorry state of affairs that we have to kind of keep improving on. So the most popular programming language is Stata, and MATLAB is also very popular among economists. They are actually used for different purposes, often used together at the same time. Stata for cleaning your data, estimating your statistical models, and MATLAB to do model simulation. That's kind of a popular use case. So the our aspirations with this package is to move some of the people from Stata and kind of help them transition to Julia and give them a good user experience with that. There are similar efforts to move some of the MATLAB users to Julia as well, because I think for model building and model simulations, Julia is already really, really excellent. So what is this data? How does it look like? So if you look at the programming language, the code example on the left, these 5 lines, I would say it's pretty readable. So it's as a kind of very high-level data analysis language, it's very good for the user. It's very easy to get started. I don't really have to explain what it does. You load a data set called trade DTA, then you do some transformation on the distance variable. You want to enforce that distance can never be less than, say, 5. Whether it's kilometers or miles, we don't know at this stage. There are no units in Stata. Then you do some log transformations, and then you run a regression with heteroscedastic robust standard errors. Okay? And on the right, I try to do it in pandas. Of course, I know that there are different APIs to work with pandas, and of course, there are like various excellent data wrangling APIs for Julia data frames as well. I just wanted to kind of give you a quick example of what an economist would see when they first come to move away from their familiar Stata scripts. And they would be annoyed by 3 things here. One is that there are lots of packages I want to load. So what do I load? Which packages should I turn to? And how do I load them? The second is, kind of, I think this data manipulation API is just ugly. I think it's very hard to read, very hard to maintain. I think this is much nicer. And the third issue is, suppose I have a statistical model. How do I estimate it? How can I make sure that it's the same type of estimation procedure giving exactly the same results as people are typically using in economics? How do I set kind of, what are the parameters to make sure that's happening? So we then dig deeper into what people use inside Stata and looked at the code that they write. And we found that the vast majority of the comments that they work on are data manipulation comments, or maybe some programming tools. But only about like 5% of the comments are actual statistical estimation comments. So when we thought to write KSDJL, then we thought, well, maybe we should build something that implements all of the usual data manipulation comments, and then gradually we'll go towards exploratory data analysis comments and estimation comments as well. Because we want to make sure that our users are kind of happy with being able to do what they are typically doing. Now, so when we thought about this, okay, so let's write something that looks like Stata and can wrangle data, we faced a bit of a problem. So we got some feedback from the community that there are already a lot of good data wrangling interfaces in Julia. And I agree that they are excellent. There's data frames itself, there's data frames meta, there's query, there's tidier data. So kind of why do you need a new one? So we were facing something like this XKCD comic when you have 14 standards and you set out to unify everything, and now the situation is worse than before, and your users might be more confused than before. But we realized that in our case, it's actually not, that's not the relevant meme to think about. I think a more relevant meme for us is the Madman meme, where Julia users might feel bad for a Stata user. They are limited in all their options and all that. But as we saw in the data, most Stata users don't even think about Julia at all. Okay? So there is already this tool and this kind of interface that's pretty popular. So our goal is explicitly to have the Stata users. So the question is, what do these users want? And I think it was yesterday that Michael talked about happiness and speed. So economists don't care too much about speed because the data sets we're working with are not super large. So we thought it's going to be convenience, or another term for happiness, I guess, in here, and correctness. And we want our code to be kind of easy to type, easy to read, easy to edit, and you kind of super easy to interact with our tool. But we would also like to make sure that our research results are actually correct and we don't get into embarrassing situation by finding weird bugs. So if you think of just kind of comparing languages, if you think of a language like Rust where you have static typing and memory safety, it's more likely to be correct, less likely to introduce bugs, but it may be less convenient for a research scientist who's not a programmer. Whereas Stata is like super easy to get started in, and I'm not saying it's incorrect. I'm saying it's easier to make bugs in Stata. Why? Because it makes a lot of default choices for you, which is actually leading to the convenience. And I'll show you some examples because we had to make decisions about these ourselves. But then if these default choices are made for you and you don't know them, that's where bugs can hide, right? And recently there have been a number of quite embarrassing retractions due to some of these hidden default choices. So with this in mind, we want to be mindful that there is this trade-off. So I don't think we should, there's like one language or one tool or one data wrangling library that solves everything. You have to be mindful of what your users want. So if your users are here, you don't really want to give them this, right? Because then they're not going to adopt the package. So we're going to move kind of the needle a little bit here and make sure that the Stata users are getting comfortable with Julia. Of course, they're going to get a lot more in Julia, and that's what we're trying to convince them. So let me kind of show you the features of KSDJL. So here we have the Stata, the same code example I gave you before, and the same thing in KSDJL. So the command syntax is almost exactly like in Stata. Literally, the only difference between the left and the right is the at symbol. So this is Julia code. This would not be correctly parsed in Julia, so we're using macros to ensure correct parsing. So that, if you're a Stata user, not a lot of things to change, so that's kind of convenient. Something to note maybe for a Julia audience is that nothing in KSDJL is a function, or at least the functions are not part of our public API. Everything is going to be a macro, and we even have this row level if if clause. So basically what it does is it executes a command only on a subset of the data frame. And we are using the word if because that's what data users are used to. We understand it's very hacky, and we hope we don't get banned from JuliaCon in the future. But it's actually the power of Julia that makes it happen because macros are parsed from left to right. So by the time the compiler gets to if, we have already eaten that up and we have already consumed the symbol, so it's no longer there. But that's going to be expected by our data users. Other kind of convenience features, variable names are going to be referring to columns in the data frame as opposed to Julia variables. And there's auto-vectorization of function calls. So here log is actually a call to log dot. So kind of automatically vectorized, which is what the user would experience. There are going to be some exceptions that I'll show you in a second. So one thing to note here, and this is the Julia syntax, is that you load a data frame into a global scope, and then you operate on that global data frame. And so that is an example where it's super convenient. You can kind of get something working very, very quickly, but it is pretty much prone to bugs because you're manipulating a global state, and if you go for a coffee break and you come back and you have no idea what you did 10 minutes ago, then it can lead to weird bugs. So we're kind of keeping that functionality, but our suggestion is to only use it for like very quick iterative work. When you're quickly hacking together something, as soon as you have like 4 or 5 lines of code, you can write this in a more idiomatic way, and you can actually wrap your code in a begin end block. And then we have our own with macro, which is going to basically ensure that your code does not have side effects on in the global scope. So that's kind of a more reproducible way of writing it. And of course, in Julia, we don't need to separately create these columns because the stats model's formula API allows you to just enter functions in there directly. You don't have to create them as variables first. Okay, so that's kind of a nicer way to do it. So what are some of the features that are kind of a given for data users but might look strange to this audience? My favorite is what I already mentioned, this if clause. So every single comment can operate on a subset of rows in the data frame. So here, let's keep the rows in the data frame for which distance is not missing. Or we've already seen this. Let's replace distance whenever it's less than 5. But regression or data aggregation can all use this if clause. So there are a bunch of, this is super useful for if you're, again, trying to get something done very quickly. There are a bunch of strange behaviors that we had to think about how to deal with. Missing value treatment, I'll get to that in a little bit. And also type conversion, we're working on it. I think we can do the most typical type conversions like integer to float or things like that, but with more complicated cases, we are still working on that. I mean, here, because the replace would just work on like a subset of rows, and so you would have a vector where some of the elements, I say integers, and others are floats. That's kind of, that's still the easiest part of type conversion. Missing values is another big topic. So this is where I was actually tripped up very often when I started to fully switch over to Julia and load my data set and start getting something. And I always got the error that, I cannot do this operation on missing. And so that was not super convenient for me because I was a newcomer. I had no idea how to do skip missing or pass missing or what to do with missing values in Julia, whereas everything just magically works in Stata. And so, and that's kind of what we adopted in CaseDJL as well. So for example, here we have this data frame on the right. What do you think the output of collapse sum x will be?
7.
Exactly. The answer is 7. So, and literally what we're doing is we're kind of skipping over the missing without explicitly saying it. And that's kind of, the user expects that. so that's good. You just have to have a simple line of code, and they get their expected output. Similarly, if we have the same data frame and we want to filter for x being less than 3, which rows would be kept?
That's a hard question. Missing is smaller than 3 or not? I don't understand.
And so this is actually something where we introduce something even kind of more convenient and maybe more bug prone, I'm not sure, than in Stata, because we decided that missing is always going to evaluate to false in an if clause. So that when you ask for x being less than 7, you're getting x being less than 7. What you're not getting may be greater equals, 3, less than 3. What you're not getting may be greater equal 3, or maybe missing or something. If infinity or not a number could be other magical values, but you can be sure that at least the rows you're getting are going to satisfy your condition. Now, so that's another example where this is all on the, remember the trade-off? We are all out on the convenience scale. Users love it. But of course, real-world data frames don't have just 4 rows, but they have like many millions of rows, and you will not see that there are missing values there, and you get into problems. So we are actually thinking of making it possible to turn off this feature. So if you're not used to living with missing values, you can turn it off and on. We haven't implemented it yet, but that's something we think kind of to be able to move on that Pareto possibilities frontier, if you like. Now, so these were kind of things that look strange to Julia people. So what are some of the things that are totally natural to a Julia audience, but we hope will feel like a superpower to the Stata audience? Finally, there would be proper data structures. So in Stata, there are no lists or not a lot of data types. So let's say you have a data frame where you have a string with a comma-separated string, and you want to count how many different elements you have in that list. So then you can, so this is case.jl code. You can just split the text. It's going to be a list or a vector. And then you count the length of that vector. And the result of this is the number of terms that are in each of the cells, right? 2, 3, and 1. And so this would be totally magical. Of course, it's possible to do something like this in Stata with a lot of hacking. String processing, counting the commas or something like that, but not as real lists. Now note that there's length dot here, so I promised you that it's going to be auto-vectorization. The reason here we are explicitly vectorizing length because we are telling case.jl that we want the length of an object evaluated in a single cell. Okay? Because otherwise length would actually be not auto-vectorized because it's a kind of an aggregation function, and it would give us the length of the entire data frame, or in this case, 3. Another feature would be like user-defined functions. Actually, you can use any Julia function. So interoperability with other packages, I think, would be a great benefit for our audience. But you can write your own function. So you can wrap this counter into a function. In this case, this is operating on the cell itself. And the second, of course, is the same name, just a different method. Would be summing across all the different rows, so all the different terms in the data frame. And then we can use the function. If we use it with a dot, it's going to be vectorized, so we are using the method that's defined on the element for text. And we've introduced a convenience function to say do not vectorize, DNV for do not vectorize. And in this case, because this is not vectorized, it's going to use the aggregation function. So it's going to add up all the different terms. Okay, so for example, this is an example where you can already enjoy the benefit of the simple syntax that Stata offers, but all the power that Julia can bring to the table. So let me say a few words about the roadmap, where we are and where we're hoping to go. So case.jl is now in general, but I would say it's in beta, so we're very much looking for feedback and suggestions and comments. It's working, it does what it promises to do, but there's a lot of things that are still not implemented yet, so we are going to be working on that. So what are these things? So in terms of statistics, we'd like to add a lot of functionalities in terms of fixed effect models, whether it's linear or nonlinear. These are very popular in economics. We use these type of models everywhere. And then there are often kind of some edge cases in how do you treat these fixed effects, but we're gonna be working on that. Output reporting after regressions would be important for the users, of course. Something that came up in community discussion is wall testing. So if you have like multiple constraints and you want to test your regression, whether say two estimated parameters are equal, that's kind of hard to do, and there's no single package for that, and we're happy to take that on, for example, in terms of statistics. In terms of data wrangling, there's a number of low-hanging fruits that we just didn't get time to get to yet. Merging, appending, reshaping data sets. We clearly have to do these. Maybe improve speed of file input-output a little bit here and there, because we want to give users a good experience. So let me show you something that in terms of programming features we are thinking about introducing. I mentioned that we want to parameterize the risk tolerance of the user. Like, do you want KSDJL to behave more like Stata, or do you want it to behave more like Julia? Okay. And so we think that it would be helpful to the user to kind of, make this choice explicit. So maybe we can use preferences.jl for that. And then an additional thing we're working on is passing variables into our begin end block, into this local scope. So here, just give you an example. So here, when we say that this y variable, then in this formula, the y is not going to refer to a column in the data frame. It's actually a Julia variable, which could be a way to introduce for loops or any other, conditionals or anything that, regular programming tools to be relatively seamlessly integrated with code that has a totally different syntax than standard Julia syntax. Okay, so these are kind of the plans for the future. So just a couple of slides on the acknowledgements. So we got inspired to even start doing this by tidyr.jl and Karandeep Singh and all the contributors to tidyr.jl. We've been thinking about the problems for some time, but when we saw tidyr data come about, it's actually possible to do it in Julia. So let's try it. Johannes Böhm has a similar package, kind of working with almost data code in Julia, taking a different route than we are. And here are all the packages that we are relying on right now. Of course, we're going to keep adding more when we add more functionality. And just maybe a final slide, like why the name? So why KSDJL? And so this is to honor the memory of my late colleague Gabor KSD, who was a great economist and actually a great educator about data analysis. And so he has a textbook about data analysis for business, economics, and policy. And we kind of thought this is appropriate to name such a package after him. So we are very much open to your feedback, suggestions, and contributions on the GitHub repo. Thank you.
Thank you for the very nice talk. Do we have questions from the audience?
Please. Oh. Yeah, thank you very much. It's a cool project. I'm also a big fan of the work that Karandeep and the team behind Tidy are doing, and you're doing something similar, so hats off, really nice. One thing I experienced when I did my undergrads in economics and also some courses during my master's was that professors who were kind of stubborn on still teaching us Stata and using Stata for everything the reason they often mentioned was that, yeah, some of the things that we rely on in Stata, so certain panel models, panel regression models, they're simply not implemented in other languages. So my question is, do you think that this package could help translate some of these Stata implementations into Julia packages? So really go to the Stata source code and use these macros to make that process easier?
That's a great question. Unfortunately, I don't think the answer is yes to that, because Stata suffers from the two-language problem, as usual. So if you want your Stata package to be actually really fast and performant, you don't really write it in the Stata. There's actually a subset of, a different feature set of Stata, the matrix computing language, Meta, and that looks completely different, so we haven't touched that at all. So KSDJ is not going to help with that. I think our goal is more facing towards the end users who are analyzing the data and not necessarily building packages. But given that it's much easier to build cool stuff in Julia, so kind of you could build a package in Julia and then integrate it into KSDJ would be super easy. I think the porting, so it is true, and then the size of the community is of course very important. That there are a lot of new methods, and then when you develop a new method, you want to also show that it works, and then you want others to use it. So you write it in the language that you know or you expect others to know. And so there's a big kind of network externality in this if you are economists thinking about this. So it's hard to change the language of an entire community. We want to make maybe a little bit of progress here. So we'll see how it goes.
Thanks. And
any more questions from the audience?
Maybe I have one here. Yeah, you said that you wanted to attract Stata users by making a more robust tool. So do you plan to do some benchmark to prove it actually?
So robust,
that was your business case. You keep the convenience, but you make it more robust. So how are you going to prove it to the Stata community?
So it's a great question. What is the proven benefit to the Stata community? And so we have some benchmarks on speed, for example, and of course this faster, but I don't think that's the big benefit. I think the main benefit, other than of course Julia being free, I think the main benefit is the interoperability with other tools. So I think that could actually be an answer. So if that already in Julia there are other packages develop new methods, you can link to them more easily. I think that could be a big benefit.
Thanks.
Just one follow-up. Have you already spoken to colleagues? Are some of them already using Casti instead of Stata, or planning to teach classes in Casti instead of Stata?
That would be awesome. So now we are already using it. So now, but basically the first time we submitted to general was last week. So, but we're kind of hoping to go in that direction, because the idea is to mimic the. We've actually had discussions about this at the choice of programming language at CU when we are teaching statistics and econometrics. And a big argument for Stata is exactly convenience for users and the user experience. And so that's where we're hoping to get a foot in the door.
Thanks.
There's a question over there.
Hi, I was just wondering what the plotting libraries look like in Stata. What do people use? Do people draw graphs in Stata?
Yeah. So we didn't touch that yet. It's a pretty decent plotting library. So the default, so very much in the same spirit. Like if you write scatter yx, you get a scatter plot that looks pretty good. Now, if you want to change some of the styling, it's very hard. But the default, get to your first plot, and I don't mean the compiling here, just kind of the user producing their first plot is actually super easy, and it looks pretty okay. we didn't want to get into this yet because you can, of course, do the data manipulation and use any of the Julia libraries to do your plotting.
I only ask because I'm the one who wrote tidier plots, so I'd love to contribute if it.
Yeah, we should talk more. I'd be super happy to talk about that.
Let's thank the speaker one more time.
Thank you.
We'll now have a 10-minute breaks, and we'll be back at 3:40 for the next talk. Welcome back, everyone, to the second half of the afternoon session. Our next speaker is Avik Sengupta, and he will introduce Horus, robust background jobs in Julia. Please join me in welcoming the speaker.
Thank you. Thank you, Pablo. The sun is coming out almost, so that's good. So today I will talk about a package that I've been writing for the last few months called Horus. And Horus is a package that allows you to run background jobs in Julia. It's similar to packages in Ruby called like Sidekick, or packages in there are packages in Python and Java that does similar things. It's probably the most similar in spirit to Sidekick, but there are tons of other packages that does this. So I guess the first question when talking about this is why, right? Why do you think? Why do I think we need something like this? And the use cases that I'm trying to support are essentially if you have a process that receives user requests, maybe a web server, a web application. You don't want to be running anything that is either heavy compute or something that can block, can take time or is error prone. You don't want any of that to run while your user process is, your user request is running. So you want to offload that to something asynchronous. And that's the primary use case that I think we need to support here. And given that there wasn't an existing package in Julia that did this, I felt that this is something that could be done to a certain level of sophistication by a very simple package, and that's Horus, right? It's about maybe 200 lines of code that has a reasonable amount of functionality at this point, but that functionality is very carefully calibrated, right, in terms of what it does support and what it doesn't support, right? So the primary architecture that this package has is essentially to use Redis as a data store and as a queue. So the idea is that we have what I'm calling clients, which are essentially these Julia processes that receive user requests that you want to offload compute off. And there are a set of processes that I'm calling servers or runners, which essentially run the job. They run the program that you want in an async fashion, right? And the idea is that you can have multiple clients running parallelly, all enqueuing jobs, in parallel, and you can have multiple runners running in a cluster that are also executing these jobs parallelly. And the idea here is that the clients themselves and the runners themselves among each other do not communicate. All network communication is via Redis, and so each of these runners are essentially stateless or can be thought of as stateless, right? So now, there are various ways of doing this. There are different levels of transactional guarantees that you can provide. What I have written, gives you a few guarantees. So, for example, one of the guarantees is that when you have multiple runners running, only one of them will pick up a job, right? So that's guaranteed, and that's guaranteed by essentially the design of Redis's BR-pop primitive, if you're aware of what Redis does. You are also protected against exceptions in the executor that you create. So the code that you're actually running, so you're sending an email or you're making a database query. If there's an exception, everything runs within a try-catch, and you're protected against that. However, you're not protected against crashes of the runner process itself. So if you run out of memory or the computer itself crashes, it'll just crash, right? Because that's the very difficult thing to do. And I wanted something simple that works in 80–90% of use cases. If you want something to be completely transactional, you probably want to use something like Kafka, with transactional guarantees around receiving messages. For using Horus, what I would recommend is to run a log aggregator that you can have a centralized place where logs go. And Horus logs a lot, and from the logs, you can figure out, yes, this crashed processing this job. You can do a manual workaround. You should also use a process monitor that if a job crashes or a process, a runner process crashes, you can restart it automatically. So in this day and age, you would probably run it as in Kubernetes, with all of these things sort of, available pretty easily, right? Now, when you're running the jobs, obviously the jobs can fail due to, either the database being unavailable or, the email server not being up or, logic errors in your code. What Horus tries to do is when it sees an error, it will requeue that job with an exponential backoff, an exponentially delayed runtime for that job, right? So, it'll first retry after 2 seconds and then, 8 seconds and 64 seconds and so on. And that it tries that for 20 times, and if it doesn't run for, if it fails 20 times in a row, and that takes about a day and a half, I think, at the current setting, it'll put it into a dead letter queue and it won't be, where it won't be tried again, and it'll expect a manual, some manual workaround to work at it, right? So, and you can use this facility to explicitly schedule jobs at a particular time. So you want to run the job in an hour, you can use the same facility to retry, to enqueue at that time, right? So let's quickly go to maybe a demo. So and that shows you, what you as a user has to do. The first thing that a job is described in a struct, and that struct contains all the parameters for that job. So in this case, I'm writing a job that adds something clearly, and it has a value that it adds, right? That's the input that you send to that job. And this struct has to be available both in your client and in your runner or your server, right? And so you would probably put it in a package that you would use, and that would be available at both places. On the runner, you would describe the compute that you want to run using this horus.execute method. So you would write your own method of this execute function based on the type that you created. So in this case, this is the function that says, when you receive an add job, what you want to do is basically add the value that it contains to a global, right? And if that global goes beyond a certain limit, you would throw an exception. And you would then run this as a script by including the type, creating a server config that basically has a descriptor of where your Redis server is running, and you would start the runner, right? That's all you would do. So let's try and run that. Julia, and I would do that. Okay, CD examples, and that I have a minute, I think. So this is where on the left you can see the server starting up, include the exception before that. In another place, in another machine, you would run this within a web server, for example, where you would use Horus. You would include the type that you have, and then you would say for, here I'm running a loop and I'm enqueuing the job. And if you see in the job, I have the configuration. Okay, let me create the configuration. Right. And for, right, you have the configuration, and I create the add job type with a parameter that changes. And on the left, you will see some of the jobs are executed, and then it starts getting the exception, and everything that is an exception will get requeued in maybe 10-15 seconds time, which we don't have for you to see, but believe me, it happens, right? That's all that I had to talk about. I think, do we have time for questions? One question? No, no questions. Find me after that. Thank you. Bye-bye.
Thank the speaker. We will now move to the next speaker, but if you have questions, please contact Avik and do not hesitate to ask.
I'll take my bag.
Our next speaker will be Fredrik Ekre, and he will talk about service monitoring with Prometheus.gl. Please join me in welcoming the speaker.
Okay, so welcome to my talk. So today I will talk about service monitoring with Prometheus.gl. And this is kind of a spin-off from the package server work that we have done. So if some of you were on my talk 2 days ago, that's what we are using it for. So what is Prometheus.gl? Well, it's a Prometheus client for Julia. So that's done, but what is Prometheus? So I think it doesn't make sense to talk about Prometheus.jl without describing Prometheus a little bit. So Prometheus is an open source monitoring and alerting system. And the core of it is that it's a time series database. And it's a pull-based metric collection or scraping over HTTP. And you can do some metric labeling. It has a query language from QL, and it has some limited visualization and dashboards. So usually you combine Prometheus with something like Grafana to get pretty dashboards. So this is a small visualization of how this setup works. So in the middle here we have Prometheus, the server. And in this image to the right we have 3 different clients. So a client is basically something that provides metrics, and the Prometheus server in the middle requests metrics with certain intervals, so every 30 seconds or every minute or however you configure it. So that's why it's called a pull-based, because the server itself requests the metrics and collects them and puts them in the database. And then we have to the left some other tooling that talks to Prometheus. So for example, Grafana, which uses this query language to request data. And there's also the alert manager, which can send alerts, emails, or Slack messages or something if something in your infrastructure goes wrong. So this is just a small example of what a scrape looks like. So if you request or if you do an HTTP request, this is what you get. So I just want to break this apart a little bit. So each metric contains or consists of 3 lines, and it has a unique ID. It has like a description or a documentation string. It has a specific type. So Prometheus has 4 different primitive types, and in this case it's a counter, which is just a monotonically increasing value. And finally we have the value itself. So in this case it's the total number of allocated bytes in this Julia process. So what is Prometheus.jl? Well, that's a client implementation for Julia that implements the client specification. And this one is actually a very detailed specification in the Prometheus docs, which made it very easy to implement. So it implements these 4 basic or primitive collectors. So there are counters, gauges, summaries, and histograms, which you can provide, and then compute various statistics or metrics based on these. There is also 2 different custom collectors. So there is a process collector, which basically scrapes the proc file system, and a GC collector, which gives you a lot of statistics about the Julia garbage collection and allocation. And it's also very easy to build your own collector. Okay, and this looks, well, doesn't really matter. I don't know why it's cut off. So this is basically what happens when a scrape request comes in from the left. So what you really are scraping is something called the collector registry, where you have added a bunch of these metrics. So you can have multiple counters and multiple summaries or whatever. And then you have to instrument your code. So this is a small code snippet from the README of the package. So basically what you have to do is that you need to create the collectors. So in this case, I have a counter. You need to supply a unique name and the description, and then you can use it. So here I'm just starting an HTTP server, And for every request, I'm incrementing this collector or the counter. And then the expose function here just returns the text-based format that we had a look at, this representation. All right, so time for a demo. And for those of you who were on my talk 2 days ago, this time it's a working demo. So first, just let's take a look at this example here. Maybe I can make it a little bit bigger. So this is just a small dummy program. It creates various collectors at the top. I have a dummy function which does some matrix multiplication just to get the allocations and GC working. And then I'm instrumenting my code here. I record the request time, and I record some other things here as well, and then just exposing it. So if we just go to, let's see, I can go to the next. Oh, I have to escape from this one. Go to the next. So if I'm requesting this server, this is what you get. So there's a bunch of default metrics. Here are the ones I added, so I call it my histogram. And then it's a bunch of default stuff from the Julia GC and so on. That's not super interesting to look at. So Prometheus itself has some very limited things you can do. And I think I will skip through this because the most interesting thing is when you connect Grafana to Prometheus. So here is, for example, from my dummy function, the average element, which is a gauge. Here you can see, let me update, the matrix size. So it was time-based, so every 5 minutes it loops around and does smaller and smaller matrices. You can get some, for example, the CPU usage. When we have small matrices, nothing really happening, and then it goes up. You can see the allocations. So this is the rate of allocations. So at the top here, we allocate 120 megabytes per second. You can see the number of live bytes currently in your Julia session, which I think is pretty nice. So then you can see here that the GC is working. So we go from something like 1.2 gigabytes down to 300 megabytes in this case. And here you can actually also see when the GC. So these are the rate of GC calls. And then you can see things like the request rate and the request time, and also things like this histogram where you can see the request time goes up with increasing matrix size. Of course, this is just a silly example, but you can imagine that you can instrument your code and get actual useful statistics out of this. And just as a final thing, we use this for the package servers. So if you go to this URL, it's just /metrics on the package server, then you can inspect and see what the server is doing. All right. That was my last slide, so thank you for listening.
Let's thank the speaker. We have time for one short question, if there are questions from the audience.
No.
OK, if there are no questions, let's thank the speaker one more time. And time to welcome our next speaker. So our next speaker is Wouter Nuyten, and he will talk about RX environments, reactive multi-agent environments. Please join me in welcoming the speaker.
Am I on? All right, nice. Hello, everyone. My name is Wouter. I'm a PhD student here in Eindhoven, University of Eindhoven, and I will talk you through my new package called RX Environments.jl, which are called reactive multi-agent environments. So first, I'll talk you kind of through the problem that RX Environments is trying to solve, and then I'll talk you through how RX Environments solves this problem, and I'll give a live demo of what the package does. So Arcs Environments is concerned with agent-environment interactions. So an agent is a system that perceives an environment in which it lives and which can exert actions in order to change the internal state of the environment that it lives in. So these are mostly agents that you see in like reinforcement learning or like control theory, stuff like that. Usually there is some desired environment state that we have to realize, some goal that we have for the agent. And Arcs Environments is specifically a package to design the environment in which your agent lives. So a popular framework or popular protocol for environment design is that whenever my agent emits an action, the environment will take this action, will step the environment one time step forward in time, and then emits an observation with a reward. So this protocol is used by both reinforcement learning JL and stuff like OpenAI Gymnasium. And you can see in the function signatures from both these packages, which are down there, that there's no notion of the time step or of different agents or whatever. It's just we have the environment, we have one action, and that's the only protocol that we have. That's the only thing we can use to let the environment step forward in time. But what if we have different sensors that operate on different frequencies for our agent? For example, we have a spot by Boston Dynamics. This thing has like proprioceptive sensors in all motors. It has a camera. It has a microphone. There's all kinds of sensors, and with the previous protocol, you cannot really encode this information because all of these sensors run on a different time frequency. So what if we have multiple agents in the same environment? My laptop seems to freeze. This is a very famous football goal from 2014. I would have loved, or this is Robin van Persie's goal against the Spanish. I would have loved to play the Spanish again on Sunday, but unfortunately we lost. But in an environment like this, so if we would have a football environment, we would have 22 agents, all in the same environment. And what if you then have, like, all of these agents would have to emit a certain action before the environment can step forward? And with the algorithm, the protocol that we just saw, it's not really possible to have like one agent or two agents or 5 agents, because all we have in order to step the environment forward is just this one step function that takes one action. Or what if, like Spanish goalkeeper Iker Casillas is demonstrating for us, want to do nothing? Do we include like a nothing action? I mean, it's kind of an awkward protocol for designing designing our environments. So that's why I coined something that I call a reactive environment. It's an environment in which an agent can send or receive an observation or an action at any point in time. So as we can see in this video, what if when I'm golfing, I hit this ball. So the action is I hit the ball and then I just let it roll. I don't want to emit any more actions. I just want to let it roll. So this is a separation between two kinds of states for the environment. One is a state which I can influence, and then there is a state that just kind of changes when it evolves over time. So I can influence a state of the environment, but I can also there's also just the flow of time which changes the state of the environment. And these are two internal and external processes that we should clearly separate. So yeah, instead of having this explicit protocol of interaction, I just want agents to listen and environments to listen, and for everything to just happen like it would in real life. So how I'm going to realize that is through reactive programming, which is a declarative programming paradigm where we basically only show how we handle certain events, and then by letting these events happen, like the control flow kind of appears. It's implemented in Julia by observables.jl, reactives.jl, rocket.jl. There's all kinds of packages to get reactive behavior inside of your Julia functions. So Arcs Environments.jl is a particular implementation of reactive environments in Rocket. As a user, you should just define how your environment should react to certain actions, to certain impulses, what would change in the internal state, and also how this internal state evolves over time. And then Arcs environments will just do the rest. It will manage this network of subscriptions for you. It will make sure that the right messages, the right actions are delivered at the right places. So it's kind of like a plumber, but then for your environment design. So how is it used? You just write your environment, and then you wrap it in the Arcs environment method, which is kind of decorates your environment with this behavior. You can add agents to this environment with the add bang function. You can delete them with unsubscribe, bang. And there's basically only 3 functions that you have to implement. What to send, so what is my agent going to receive as an observation from the environment? Receive, bang, how is the internal state of my environment going to change when I receive an action? And update, bang, how is the internal state of my environment going to evolve over time? So the design philosophy of Arcs environments is basically that indeed all agents, all environments, they have internal states and they have interaction states. So if I kick a ball, I interact with the environment, but the internal state is really just the position and velocity of the ball. So if we borrow this a bit from active inference literature, we have a Markov blanket, where every agent has a set of sensors, a set of actuators. The environment also has sensors and actuators, and they're kind of like symmetrically linked together. This doesn't stop us from hooking up multiple agents to the same environment. So we can have a second agent that also has sensors, actuators. We hook it up to the environment. And if we look at this figure, kind of the only thing that's different between an agent and an environment is that I wrote agent or environment inside of this box. So in Arcs environments, I implemented like a super type, which I call an entity, and all logic is implemented on the entity level. So just take that out. Agents and environments, they're basically like the same thing. They can just react onto each other. So with Arcs environments, you can model agent-to-agent interactions if you'd want to, or you can make composite environments which are like hooked up onto each other. You can go completely crazy with this. So here we go, live demo time. Can I do this code? Well, this is probably small, isn't it? So I have prepared for you a mountain car environment. Here we go, a plot. This is visible, isn't it? This is. So the mountain car is quite a well-known environment from reinforcement learning, where we have this landscape, and we have a car, which is inside of this valley, and it's supposed to drive out of this valley, but by its engine force alone, it's not able to go out, so it has to kind of swing and use gravitation to its advantage. So let's send a command to this agent. We have this throttle function, and we see live that this guy is going left, like he's or right, and then he's going left, and we can make him swing, and it's all fun and games. Then okay, let's make sure he actually gets out of the valley. So I have some for loop that does something. It waits a little bit and then swings this throttle. While he's busy, let's add a second agent, because we can do this. Now there's a second agent, and we can also control this guy. We can just go crazy with this. Then, I don't know, let's do something like this, like agent is add agent. Like, let's do like this, and then how are we going to control this? -1 plus 0.2 times I. It should spawn like 10 agents. There we go. The font larger, like this. So now we have like 10 agents. They live here. They're doing their stuff. We can see the results live. And with the same code, I can do 1 agent, 10 agents. Doesn't matter. Like I can go crazy with this. So we can push it even further with the football analogy. We can make a football environment, like a pitch, like you can see behind me. And we can.
Still compiling?
What?
At Grass still compiling?
Grass is still compiling. It's, you know, this is supposed to be a digital twin, so on my PC it's compiled. And we can have a player, we can put him in, we can make him run around. So we have a player, and I just send some random commands, and I mean, he's running around, he's having fun. And with the same code, I can play a 3v1 game. So I can put 3 players of the red team, then 1 player of the blue team, and with the same code, we can have them play together. And we can even go further and simulate a full 11v11. So this is all with exactly the same environment code. We just code how the environment should react to the different actions of the players, and it will just resolve itself. So I couldn't really design an intelligent agent, so I just made them do random stuff. But there's more. So we have all kinds of control over when we want to emit stuff to our agents. You get fine-grained control over every single step in this emission graph. You get control over the speed of your environment. So if you want to design a controller, but it takes up too much compute, you can just say that my environment time is going to be twice as slow as real time. So we can kind of demo with computationally more expensive controllers and then see how they behave in a real digital twin. And everything is based on Rocket, so we have native support for RX and FurGL based agents, as like these guys were. This is a project from my master's thesis student. Thanks, Felix. But this is all being controlled by RX and Fur agents. So that natively works. So what is it not? So right now, or it will never be a package containing an environment zoo. I want to make a separate package that ships like all kinds of default control theory environments, like reinforcement learning environments. But I don't want to pollute the base repository with that. So for now, it's only boilerplate code. There are examples in the documentation of like mountain car and like windy grid world, stuff like that. It's also definitely not a differential equation solver. So even though you have to specify how your environment evolves over time, please just use differential equations if you want to solve differential equations, right? Differential equations jail is an amazing ecosystem. Just use that and then use the result of that in RX environments jail. So this is the end of my presentation. If you want to try it out, it's available on the registry. If you like the talk or the package, please leave a star on GitHub. I'd really appreciate it. And if you have any questions, I'd be happy to take them. And I rushed. Holy. All right. Any questions?
There's a question on the left.
Hi, thank you. You briefly mentioned that there was support for RX Infer. Do you have an example of how that would look?
In code, no. Like not something that I can demo right now.
Okay.
But I mean, I could show you after the presentation. It's not something that I can do live on a stage.
Thank you.
Okay, I have a question. So, at what, how many agents can I actually add? Like, did you test? How does it scale? Can I add 1 million agents interacting, or maybe it's 10,000, or?
It depends on how expensive your function is that basically computes this over time. So, for example, for this football environment, like because actually moving these agents, it solves a differential equation under the hood to move them through time. So 22 agents was already like quite expensive. It also depends on your update frequency. So do you really want these guys to update every millisecond, or is it okay if they update like every second? Hundreds of thousands, I mean, you probably can if your transition functions are really cheap, but that's kind of mainly your depending factor. Over there. Mikola.
All right, so I was wondering, I saw that it was based on observables, right?
No, it's based on Rocket.
Rocket, okay, no, okay, but I would imagine, but it works kind of in a similar way, more or less. Do you know if it has easy integration with Mackie to make, what's it called, interactive environments where you can actually do drag and drop on the environment? Because that would be super cool.
I have tried to integrate it with Mackie. Like these plots are it's not an integrate. I hacked Mackie kind of into this, but I cannot yet pull anything from Maki, but in theory it's possible because actually the thing that plots it is just another entity that listens. So it's just another thing in this compute graph that listens to the environment that you want to plot, and it just doesn't send anything back. So the communication protocol is there, but since Maki is based on observables and this is based on Rocket, that was it was quite difficult to hack this one-way interaction into it, and sending anything back is.
Yeah, because that's why I was asking, because I misunderstood that point. But that would, but still probably still possible to do, right? So.
Yes, in theory, yes.
Okay.
A question,
Andreas.
This looks like a game engine, basically, that you developed. Like, under the hood, is it a game engine? Like, is it this entity component system kind of thing? Or can you make some comments about the architecture, basically, is what I'm asking.
In theory, yes, but if you say game engine, then usually people think of like graphics engine, physics engine, and kind of all that. Those things are not in there. It's purely a communication protocol with like time-synced communication, or asynchronous communication, basically. So I mean, you could hook it up probably to, well, I did with differential equations. Maybe you can hook it up to Mujoko, something like that. And then sure, but like in a traditional sense, it's not a game engine.
Okay, but like, what's the general architecture? Like, do you have like any fancy data structures, or is it just like a vector of entities, or?
What do you mean?
For example, I think one very common optimization is that you have this struct of arrays data structure because you have many entities with the same properties. Do you employ any such things, or?
Yeah, yeah, I do. I haven't. Yes, I do. In a sense, it's just an array of entities that know how to communicate with each other, and I managed kind of the plumbing work for that, in order to make sure that what you send ends up at the right place.
Okay. Yeah. Thank you.
You're welcome.
More questions from the audience? There's plenty of time.
Do you have some project that use data from real sensor?
Not yet. So the idea is indeed that this is able to mimic in some way a real sensor, because you can actually live or determine the emission frequency. But I haven't done that yet.
Okay.
I first want to integrate it with RxInfer such that I have like a decent controller that controls something in real time, and then maybe swap it out to see how good the digital twin actually is.
Okay. Thank you.
You're welcome.
Do we have more questions from the audience? Still plenty of time for discussion if someone wants to ask something. Yep, we have a question over here.
So you mentioned about reinforcement learning environment and open edging. So could you like explain why do you want to like remove the step, because you still need to somehow determine the frequency, and that is kind of the reason they have the step, because you can it basically like each time step you got a step.
Sure, but with this framework, your action frequency does not have to match the frequency of your sensors per se. So not every time you get an observation from your sensors, you have to do something. Or what if I have multiple sensors, like I have camera and a microphone. So my microphone will trigger at like 44 kilohertz. Do I let my step be 1/44,000th of a second, and then once every 200 samples I include an image that comes from my camera, and the rest of the time it's nothing, and I have to emit an action 44,000 times a second? I don't really want to do that. I just want to, get sensor data when it arrives and send stuff whenever I want to send stuff.
So does that mean like the controller have like different action when they take different kind of sensors data?
Yes, and it doesn't necessarily have to be on the same frequency as your sensors. Yeah.
Thank you.
You're welcome.
Do we have more questions? Yep, we have a question in the middle.
Hello. Do you think this is something that can only be done in a simulation, like this reactive paradigm, or can it also be used in a real robot?
I don't know enough about robotics to really give an insightful comment about that. I built it to get us close to how, you know, a close enough digital twin to a robot, but I don't know about the actual implementations in robotics, whether or not it would be feasible.
Okay.
We have a question on the top right.
Thanks. Very nice talk. I'm curious about the plumbing a little bit more that you didn't talk about. So you talked about different frequencies that your different sensors provide. So what do you do internally? Because the computer eventually has a clock cycle. So how do you do that? And is it efficient in a way that it would scale up to many sensors that receive data at high rates?
It depends on what you define by many sensors. Is it like 15 sensors or like a million?
Well, let's think about a million.
A million sensors would probably not scale very well. In the same way as Dimitri asked, is basically just if I have a million sensors, I kind of have a million entities that emit on a different frequency, and my agent will, well, it will get a lot of messages, like seriously a lot of messages. So probably the plumbing work would then dominate the time that I can actually use for computation. If that answers your question.
Partly yes, but how does the plumbing work? You said you have this, this array of entities which are structs or something like that. Do you scan through them on a regular cycle to decide what happens to what has to happen?
No. The agent is subscribed to a sensor. So whenever the sensor emits, the agent will be notified and a packet of data will be sent, which you have full control over what will be sent, whether it be data or like a notifier or whatsoever. But this is kind of the computational speed up of why I use reactive programming, is because I don't have to scan through like arrays and arrays of who subscribed to who, or where do I have to send what, because I subscribe from A to B. Whenever this thing emits, all its subscribers will be notified. So I only compute when it's strictly necessary, and I don't do something every clock cycle whatsoever.
Okay, and the rocket, so the the actual communication is then
Yes.
done by rocket, probably, right?
Yes. Yeah. Yes. What RX Environments does is make sure that so Rocket actually delivers the message, and then the RX Environments kind of exposes the internal state of the entity to you, and it will it will basically abstract this story of entities away for you, such that you just have to write synchronous code, and it will turn it into a reactive Rocket under the hood.
Okay, cool, thanks.
Do you have any further questions? Okay, if there are no more questions, let's thank the speaker one more time. And since we are a bit ahead of schedule now, we will have an extra 7 minutes break to stretch legs and get some coffee, some cookies, and we will be back at 4:30 for the last talk of the parallel session. See you in a bit. Okay, welcome back everyone to the last talk of JuliaCon for this year, before the last keynote. Our next speakers are Ian Butterworth and Ryan Benasutti, and they will talk about a cloud-native parallel data processing application in Julia. Please join me in welcoming the speakers.
Thanks, everyone. So for those who don't know me, I'm Ian Butterworth. You might know me for Julia stuff. I've done some things around kind of PKG and things like that I'll talk about a little bit. But I'm also CTO and co-founder of a medical device startup where we use Julia. And Ryan is our senior software engineer. So we're going to be talking about some uses that we have for Julia and some issues that we want to highlight. So the need that we're going after is in chemotherapy, there is a significant issue with the risk of the chemo itself causing hospitalizations. And the reason that that happens is that chemotherapy has a side effect of causing low white blood cell counts. And so the typical way that you have chemotherapy is in the hospital, you get your chemo dose, you get a blood draw to check that your white blood cells are high enough. Then you're sent home for 2 to 3 weeks. And in that time, you don't know what your white blood cell count is doing, but it will probably be dropping down to high-risk ranges and come back up. And then you go back to the hospital for your next dose and you get another blood draw. But the problem is at home, you may have low white blood cell counts and develop an infection, which can trigger going to the hospital, can delay chemotherapy, or in itself be dangerous. So what can be done at the moment is really only extracting blood for analysis, and so typically that only happens at the hospital. But what we've been developing is a device for chemotherapy patients to take home called Point Check, which is a non-invasive device. It can be used at home. It takes a few minutes to take a measurement, and it's cloud connected so that it notifies the care team if white blood cell counts are low, and enables earlier intervention if their risk is especially high. And the way that we do this is by looking through the skin in the region just above the nail, where is a relatively unique place in the body where capillaries flow parallel to the surface of the skin. So it gives us an opportunity to look at the capillaries from the side, and this is the type of video that we collect. So I'm hoping that you can see these on the screens. But what we're seeing here is the dark red blood cells and then the bright white blood cells going through those capillaries. So our device collects these measurements, and we've designed the device to work in the hands of untrained users. So it's a smart microscope, basically. And we've tested it with people that are completely untrained, and we've published some data on that, which you're welcome to look up if you're interested. But fundamentally, the way that the device is designed to work is collect measurements at home, upload those measurements to the cloud, analyze them, and send the screening information back to the clinical team, so that the clinical team can decide what to do if what's called neutropenia, so low neutrophil counts, has been sticking around for too long. The clinical team might want to administer prophylactic antibiotics or other things such as growth factors, which can stimulate the growth of white blood cells. So that's the data center at MIT where Julia was founded. And this is Building 36 at MIT, where Luca was founded, or where we started the project. So back in the day, we did a lot of our original code base. We were originally a small group of kind of machine vision type engineers and PhDs. And our original code base was MATLAB. And while we were at MIT, we were hearing of this cool thing that potentially could solve the two-language problem. And we were fortunate enough that when we actually spun out of MIT, Julia was good enough for us to start using it. So it became a really logical thing for us to start using. And we've been trying to help develop Julia to be even more helpful for us as well. So the two things that I'm talking about, or the two things in terms of Julia at scale that we have, are one being our kind of product infrastructure, which will exist when the product is out in the real world and analyzing real measurements, or we do analyze real measurements, but analyzing in a product sense. And that system will be continuously available, and it will be scalable and highly available. But what I'm talking about mainly today is our R&D setup. So we've done many studies, we've collected many measurements on people, and every time that we touch our Julia code base, we want to make sure that not just our unit tests and integration tests are passing, but that our diagnostic performance on our large data sets is adequate. So we've developed a system which can, so that a developer can open up a PR, make their changes, invoke a GitHub comment, go off, massively scale up the analysis of that, and post back a report giving us the diagnostic performance and a variety of rich kind of information. There's a lot of stats up here, but ultimately it scales up to having 600 EC2 instances at its maximum parallel at once, which, just to visualize, is probably this small slither of an AWS server farm. What we call Leucotester, which orchestrates this whole thing. So we have an S3 bucket. We spin up workers that grab from that S3 bucket, and those workers, as I said, could be 600 in number. And once they've analyzed those measurements, we'll send their kind of data-rich objects back to S3, and then from that S3 bucket, we have a single worker that then does kind of total analysis on those rich individual measurements, and then saves some information at the end. And the part that is really very slow, and we think has great room for improvement in the Julia side of things rather than our own code base, is the downloading and uploading of data from a single worker node, and that's what we're focusing on. So our objectives in this part of the presentation is to benchmark Julia's S3 data transfer performance, see what is actually the best option out there if you're doing this in a variety of different database dataset setups, and then figure out what's actually possible and what our bottlenecks are, and if there's something that we can help figure out and fix in Julia in the community.
Yeah. Okay, so I'm going to talk briefly about our methods for this benchmarking, and then I'll get into the results that we have. So we have two data sets. The first one there is a copy of one of our actual data sets that Leucotester has processed, just so that we're getting results that are actually applicable to Leucotester. And so if you're seeing that weird number of 87 gigabytes, that's why. And it is split over quite a large number of objects. They're not all the same size. Most of them are less than 5 megabytes in size, which means that we'll get them in a single GET request. So that's not testing multi-part downloads, which is why we have our second data set, 10 objects, each one's 10 gigs each, so that we can test multi-part downloads. And then for software, of course, we're testing Julia with the familiar aws.jl package and its two backends. We're also testing Cloud Store, which is packaged by Jacob Quinn that interfaces to lots of cloud data stores, including S3, with a brand new backend for that, http2.jl, which is a new exciting reimplementation of the HTTP package using the AWS CRT, which is a set of native libraries AWS publishes. And we'll see why that's important later. We're also testing against Go. As Ian said, we want to know not just what Julia can do, but what is a realistic goal for Julia to reach for. And Go, you'll see, will perform very well on all of these benchmarks. So that is a good point of comparison for us. And then there's a ton more variables that we are leaving out here. So if you want to see how this works, or if you even want to contribute your own benchmarks, because this is an extensible framework, you can do so at that repository. So I'm not going to spend too much time on these next few slides, but we just want to give you all an idea of the breadth of what we've collected. So each row here is a unique benchmark. We sample each benchmark 3 times on both data sets. And then for each benchmark, these are the types of metrics that we collect to make sure that the benchmark is doing what we expect, to make sure we're testing what we actually think we're testing. One thing to note here is on the top left, you see CPU usage. Go is around 8% CPU over the course of this benchmark. And in comparison, Julia is at like 50%, almost 60% sometimes. So that's hinting at some scheduler overhead we'll see later and room for improvement there. So here's a simplified view of our first data set. So this is 87 gigs over all of those objects on an instance which should be able to achieve 12.5 gig throughput to S3. We can see Go is doing very well near the theoretical limit for this instance. And in terms of Julia, our best option is Cloud Store with that new backend. And then the familiar AWS package with the HTTP backend is doing OK. It's maybe just over half of what we should be achieving on this instance. And then the downloads backend is not doing so well. Unfortunately, that's a theme throughout all of these benchmarks. Here's the other data set. So here we have 10 objects. Each one is 10 gig. And we have a similar distribution. And then one last slide to look at. Here we're running on that same data set, but we have a much larger instance. This instance should be capable of 100 gig throughput. Go gets close to that at around 85. And then Julia is about half that at 40 gig. Here, I actually have an open question to the audience. If anyone has observed a single EC2 instance achieving S3 throughput of 100 gigabytes per second, or gigabit, excuse me, then please let me know how you did that. AWS does document that this should be possible, but in all of my testing, I never achieved more than 85 gig. So if any of you know, please get in touch. So to summarize that, if you need lots of throughput in Julia, right now your best bet is going to be using Cloud Store with HTTP 2, though do note that is not quite production ready yet. So this is really like a call to the community to get involved and start trying out this package. It's in a pretty good state, and I know Jacob is using it internally, but now it's at a point where we need people in the community to start using it so we can get more miles on it and figure out any last issues there. If you do need something that's production ready, then just continue using the familiar AWS package with the HTTP backend. We also went in deeper on a couple of these benchmarks with some profiling to figure out where we're going wrong. With AWS and the HTTP backend, we're spending almost half of our time waiting on the libuv IO lock. If any of you aren't familiar, Julia's IO system is based on something called libuv, and it has a very large global IO lock in it. So when we're trying to do tons of concurrent IO, we end up having a lot of contention on that lock. And that's the main reason that Cloud Store with the HTTP 2 backend can achieve much better performance, because it doesn't use libuv. It's using the AWS CRT, which has a totally separate IO system. But even in that case, we're still spending a non-trivial amount of time in Julia's scheduler trying to figure out what tasks should be running instead of getting useful work done. So that's another point of future work. We need to keep profiling that, figure out what's going on in the scheduler. And then lastly, if any of you want to follow progress on HTTP 2 or on anything we're doing with a CRT, because it's not just limited to this, then you can check out the Julia Services organization where Jacob and I are collaborating on those packages.
Yeah, and so we also just wanted to talk about some of the tools that we're using along the way. So we'll talk about containerization, our source management and profiling. And on the first point, something that's working really well for us as a company is to have an internal registry. So we use local registry to manage that, and we have actions set up so that we enforce that you can override it, but we promote people to do new releases for every PR merge, and we have that system fully automated to release those versions, and that's working pretty well for us. Yeah.
Yeah, and I'm happy to get to finally announce that Trivi, if you're not familiar, it's code and configuration scanner that can identify like vulnerabilities, secrets you may have committed, and it can generate reports like software bill of materials or SBOMs, which we do for like all the artifacts that we build in our CI pipelines. But finally, my PR adding Julia support to Trivy has been merged. So now if you get Trivy, the latest release, it will understand like what a project TOML file is and what a manifest.toml file is, and you'll see your Julia applications and all your dependencies in your SBOM. You will also see JLLs in there because they do have project files, but there's a little more to JLLs with the artifacts that they rep, the sources those come from, and those licenses of those sources. And now these new JLL TOML files coming in Binary Builder 2. So there is some more work for me to do adding all that to Trivy, but it's at least in a usable state today. OK, so now we're going to move a bit to how we build the analyzer. So if you remember earlier where we had that diagram of we're taking data from S3, spinning up lots of servers, processing all that data, putting it back into S3. The code running on all those servers in parallel is what we call the analyzer. So we have this in a monorepo where we have the top level is the analyzer package, just a standard Julia package. And then in that we have another package which we just call service, which exists to take that analyzer package, which doesn't have any concept of like doing things over the network or processing requests, and we adapt that to work with a service-oriented architecture where it's like running continuously and receiving requests, and we bring all that into a Docker container. So the fact that we bring it all into a container gives us a good opportunity to optimize our startup time, which we could do with package compiler, but unfortunately, it takes like almost an hour to build that system image, and we would be doing that in CI, so that would extend our developers' iteration time, and it's not really worth the benefit because the amount of time that it takes us to analyze a measurement is much longer than the time we would spend in the JIT on the first invocation of this. So maybe that could change in the future with like Julia C stuff, but for now, not so much. And then two notes about anyone that is building Docker containers with Julia code in them. You should be sure that you're setting your Julia CPU target correctly, because it's probably the case that the server you build the container on has a different CPU architecture than what you're running it on. So like we build our container in GitHub Actions, and then we deploy it onto EC2. They're both running Intel processors, but for this number crunching heavy like numeric code, we really need to take advantage of all the local features available to our processor. So be sure to use multi-versioning with your Julia CPU target, set the appropriate ISA in there. And I hear it works with package images now. Sort of. Sorry, I put you on the spot, Gabriel. Yeah. And then the other thing is, when you install packages, you get the entire source tree of the package. You don't just get the project.toml file and the source directory. You also get things like the test directory, any build scripts they may have, other applications within the package to generate bindings. So you end up putting all of that into your container, and then you don't just want to put that whole thing into production, because we don't want any unnecessary code running in production, and we certainly don't want any code in our SBOM that makes it appear like we have a larger risk profile than we really do, because we're never running that code. So we have a cleanup script that runs that just searches through the whole file system of the container, deletes anything called test or things like that. And now for the last point here about profiling, I talked very briefly about profiling before, but we're going to go more in depth now. We tried the profile.jl standard library, Tracy, and Intel vTune. We found vTune to be the most helpful because of all of the features that it has. It supports a variety of programming paradigms, including multiprocessing, so it can profile an entire process tree, like if you're using distributed or something, a variety of hardware, and it scales really well as you have huge numbers of tasks. It's like our analyzer will spawn around 50,000 tasks over analyzing one measurement. And Profile and Tracy really don't scale well with that many tasks. But the biggest problem with it is lack of documentation. We do want to address that. I have some later points about that, but you may have a bit of a hard time getting up to speed with vTune because of that. But I do have some notes to hopefully make that easier. One is you may want to build Julia with that flag in your makefile. It's not required, but it can give vTune some extra information that can help you out. And I have seen at least one case where vTune failed to finalize a profile because I did not have that flag. It shouldn't be necessary, but try to recompile if you can. What is necessary, though, is running Julia with this environment variable. Otherwise, vTune will have no idea what is going on with your code, with codes popping out of nowhere at runtime because of the JIT. So you do need to run with that environment variable. And then there's this great package called Intel ITT. vTune will let you start profiling your application in a paused state where it will initialize everything and then wait to start collecting data. So if you have a warm-up period or compilation that your code has to go through first, you can use that package to tell vTune to resume collection whenever your code is ready to actually be profiled. And then a quick note about avoiding hardware sampling, because I've heard at least one case of it breaking somebody's computer, and it has a pretty finicky kernel module you have to use, and really 99% of the time you don't need it. So just to illustrate how we used vTune and to give you all a very brief introduction to it, I've extracted the part of our analyzer that was being slow into this example. What this does is we have a @threads for loop, and on each thread we create an FFT plan and then use that to filter an image. We found that this was being pretty slow, so if we look at it in vTune, this is what the interface looks like. If we zoom into that, then we can see there's this function plan RFFT, which is dominated by another function called Julia slow lock, which, as the name implies, it's taking a lock, which really, that doesn't seem right, because the plans should not have any dependencies on each other based on that code. But actually what's going on is the FFTW planner is inherently single-threaded. So therefore, any call to make a plan is protected by a lock, even though we can't see it, but we see it here in our flame graph. So if we instead refactor that plan to outside the loop and then reuse it on each iteration, we should do a lot better. And here's that profile. Now that pink section is plan RFFT, and it's so quick that it's not even worth zooming into. So great, we fixed the bottleneck. Hopefully this gives you a brief idea of what vTune looks like. And now Ian can talk more about how we actually did that optimization.
Yeah, so the actual change to image filtering is available at that PR if you're interested. The main thing I want to talk about is that I think it's nice to sometimes float some of these issues up to the surface, and I consider the surface to be the @time macro. And so this was actually an example of why, or this is the exact case, which prompted me to propose that we add the lock conflicts to the @time macro, so that users can be told when locks are contending and you're potentially having design issues.
So just to summarize this stuff with profiling, we basically recommend vTune to anyone that is profiling their Julia code, especially if, like us, you have very high task counts. There are a ton more features to vTune than what we showed, so please go take a look and explore that. And basically, we're going to take what we learned in this process and try to improve Julia's docs so it's easier for all of you to get started with it.
Yeah, and then we're just going to finish up with some gripes in the spirit of the gripes channel on Slack. So for us, originally, pre-compilation used to take too long, and that was why it was actually pretty critical for us to speed that up. So that was a big motivator for myself to implement parallel pre-compilation. But I say kind of because now that it's parallel, I think more stuff is being pre-compiled. So we're kind of using up the time that we saved, which is, so I'm excited about the work that Stefan has designed in potentially putting package images up in the package server and reusing those. The other thing was that for us, CI was just so slow that we couldn't, that CI with coverage was so slow that we just couldn't use it, and that was a motivator to fix that. So now if you run CI with its default configuration from package.test, or the Julia run test action, it will only generate coverage for your package, and that's a lot faster now. And then a more recent thing, which Curtis helped with, was that we were finding that we would just every time we ran CI, it was pre-compiling, and it was because the Julia cache action, which has been around for a while, never cached package images because there was a couple of details I won't go into right now, but they're now fixed, and it means that you can actually cache your package images, and I really recommend that people add that action. And we are talking about maybe adding that to the setup Julia action as a default, so that could be something to consider. And then another thing is that for us, we'd love to be able to use some ARM systems, Linux ARM systems, both lower power machines, but also in the AWS infrastructure. They're more cost effective. But because Linux ARM is tier 2, we don't quite have the confidence to do that. And I know that there are some issues remaining there. And then the great thing that would really kind of instill some more trust is to do like a package eval run on Linux ARM. So we're happy to help that along.
Yeah, and then about the test standard library, test is really simple, and in all due fairness, it's really good at the limited number of things that it does. But some users, especially like companies like us, need some more things. Like we really need parallel evaluation of tests, both threading and multiprocessing, and we need to generate test reports in multiple formats. The text format's great for seeing in CI, but like we need to take test reports and put them into our QMS, for example. So we need like other formats like JU to XML, for example. So if any of you feel similar, please do get in touch, and we can collaborate on that. Next, I talked briefly about what happens when you install a package. You get the whole source tree. This also affects like cloning with monorepos. So if you clone 5 packages from the same monorepo, you get the whole monorepo 5 times, and then you need to clean up all of those files. It's not totally clear what we can do about this, like if we could ship artifacts or something like that. But if you feel similarly, then please get in touch and we can brainstorm something. Next, the dependency confusion issue. Unfortunately has been open for 3 years now. Stefan proposed a pretty well thought out plan for what we can do about that, and there wasn't much community disagreement with it either. The issue just sort of fizzled out, unfortunately. So we would like to call more attention to that and hopefully get a fix for that. In the meantime, I do have a tool there called Registry Scanner, and I would encourage any of you that run private registries with private packages to run Registry Scanner and just make sure that no one is trying to do this attack against your organization. And then quickly about JLLs, we have had to test lots of unreleased JLLs throughout this process, and doing that is a ton of work, a lot of manual work, so we're working on some automation to make that easier.
Yeah, and then so highlighting lock contention in that time, that's solved. But in a similar spirit, and something that actually has come up in this JuliaCon, and I have a PR open for it, is an idea to expose in at time when too much time is being spent in the scheduler. So for instance, there's kind of the classic case of whether you do at threads 4 or 4 at spawn. So just spawn a load of tasks or get at threads to do something that's a bit cleverer. And it can kind of not always be obvious that you're making a mistake in like spending too much time in the scheduler because you have too many tasks that are too short. So this is a PR that's open as of yesterday. I think the metric needs some work. We need to figure out what the right threshold is. But if you can see in the bottom right, we're reporting that this case with the busy equals false, so just at spawn nothing, spends like 60% actually scheduling and not doing any real work. So yeah, that's just something purely work in progress. Yeah, thank you very much.
Thank you very much for the very interesting talk. We will now have a 10 minutes break before the next keynote speaker. So just to note that the keynote is at 10 past 5, not half past 5, as was mentioned in the slide, so in 10 minutes. And meanwhile, if you have questions for the speakers, feel free to reach out to them. See you in 10 minutes.
Thanks.
Thanks.
OK, take your seat. Welcome, everyone. So, welcome to the last but definitely not least keynote of JuliaCon 2024. Our keynote speaker is a very important member of the Julia community, program chair of JuliaCon and applied scientist at Amazon. So I'm glad to introduce Catherine Hyatt, who will tell us why she uses Julia for quantum computing. Please join me in welcoming the speaker.
Thanks so much, Luca. So I have to confess, while I was preparing for my talk today, I was really confused because I kept seeing on the slides, Dr. Catherine Hyatt. And I was like, oh, I bet that person's talk's going to be really good, but I don't know who that is. Because even my own mother writes Christmas cards to me as Ms. Catherine. So I had a little bit of a struggle figuring out who exactly was giving this talk today. But hopefully, I'll be able to explain to you sort of the advantages of using Julia for a lot of different tasks in quantum computing, some of the things people today are thinking about, and opportunities for people in the community to contribute. So when we talk about quantum computing, we should be a little bit more specific about what exactly we mean, because there's a lot of different things going on under the umbrella of the field we call quantum computing. So we can talk about using Julia for things like designing quantum devices, simulating those devices using classical computing. And then when we've actually built the device, trying to calibrate and control it using the microelectronics we need to actually make the device do what we want. And from there, we can also discuss things like constructs and algorithms for actually programming the device at a high level in a way that's sort of more feasible for human beings to read, write, and think about. We can think about problems that are probably pretty familiar to anybody who was watching the main stage talks over the past couple days. Things like IR lowering, figuring out the types of various objects, trying to translate constructs that are more familiar to us from classical computing back to quantum computing. And then sort of algorithmic implementations of things to control and deal with errors and noise. Again, anybody who's been watching talks here on the main stage for the past 3 days can probably understand the importance of dealing with noise. So that's something that we also really want to understand if there's a role for Julia for. And then finally, doing purely classical simulation of the quantum algorithms we'd like to run. So what I'd like to address in this talk is both what's already happening in the Julia community and what are the opportunities for us to contribute further. So what do we think of as Julia's strengths? Well, I think for this audience especially, this is the last keynote. I don't have to motivate this too much. We, of course, know that Julia is highly performant. It has great routines for linear algebra, numerical integration, PD solving. It's easy to compose tools from a variety of packages, which is great if you have a lot of different packages that are all working together in the same ecosystem. This means you don't have to constantly reinvent tooling necessarily. We have a strong ecosystem for probabilistic programming like Turing.jl. And what's also very important is that we have a really big community that's really happy to start working with early stage technologies where things are changing very quickly. And our community is really willing to adapt as things change over time. For example, when I started using Julia, my first Julia was like 0.4. If anybody remembers Array Apocalypse, that was a very sort of disruptive change, but it was for the better. And as Julia has evolved, we've also experienced these kind of pretty paradigmatic changes that kept the bones of the language intact, but we had to adapt to as we go. And I think this is a really big strength that we'll see called out throughout this talk that makes Julia a really great tool for this community. So 9 years ago in JuliaCon 2015 was my first talk. You can see there's a little screenshot there from the YouTube, and also the top picture from the hackathon that was the Saturday of that year. You might see some familiar faces in the picture of that hackathon. So at that time, I think there was like 1 or 2 quantum talks on the schedule. I confess I didn't actually go check the 2015 schedule. And now, 9 years later, the quantum community has really grown. We've had 20+ talks that are more or less about quantum computing, 2 keynotes that are pretty connected. It's the 2nd year of our mini symposium about quantum physics. We have multiple organizations that are supporting Julia developers in this area, both with like permanent positions and with micro grants. We have Julia code actively being used in industry to design devices, and most relevant to me, and luckily you can't really tell from the screenshot, I finally have gray hair. And I won't say whether this was caused by quantum computing or Julia. You can draw your own conclusions about that one. So since this talk is, fortunately or not, only 45 minutes long, and we have a lot to cover, I've added a couple icons here. So if you see this mortarboard, it means that this is actually a very complex topic, and many people have written a lot of PhD theses about it. So I'll try and include references that you can follow up at your leisure if you're interested, or find somebody at the hackathon for many of these topics that you can find out more about it. But in the interest of time, we're going to have to be brief. Presumably, you all don't want to be here until 3 in the morning. And then I've also included the little Julia icon if I think there's an opportunity for us to make a difference, or for us to sort of make inroads in a certain area based on the strengths of Julia that we all know and love so much. And again, just for the physics folks, since there's wonderfully quite a lot of you here, just keep in mind that the fact that we're going to have to go through quite a few areas means I can't cover yours in depth. So I apologize for that in advance. So I think one thing that's really motivating for me and a lot of people who are kind of working in this field is that, and this is a direct quote from someone who will go unnamed, we need scientists to be writing the prototypes that we use for this sort of early stage technology, but we also need the code to be really performant. And in a way, this is, to me, like a sentence that sums up the entire Julia community, where you have people who are both domain experts in whatever it is they're doing, like whether that's earth sciences or quantum chemistry, or even graphic design, but then they're also writing really performant code. So in effect, they're sort of, with their right hand, that's actually my left hand, whoops. With their right hand, they're doing their domain expertise, and with their left hand, they're also sort of getting a second software engineering degree, writing performant code. And this is something that Julia allows us to do relatively easily, and it's something very important for people who may be interested in coding, but what they really want to do is drive the field forward. So if we think about quantum computing today, maybe a rough analogy for where we are today is that we're kind of in the Cambrian era of this technology. So why did I pick this analogy? In the sort of Cambrian era of the evolution of life, we went from having like not that many different life forms. Again, I don't have a biology degree, so I'm sorry if I say something that's like a little off. And then in this era, we saw a complete explosion in the diversity of life, and I saw a nice quote that said that the major forms of sort of complex animal life emerged during this era. And today we have a pretty diverse array of quantum hardware platforms that have emerged and people are actively working on, from photonics, trapped ions, neutral atoms, topological quantum computing, and the one we're going to talk about most today, which is superconducting qubits. So I don't mean that to say I think superconducting qubits are necessarily going to win, or they're best, or they're worst, or anything like that. It's just one example that I'm most familiar with that I think is sort of illustrative for the rest of the field. And the reason I think this caveat is important is if you somehow like time traveled to the Cambrian, or you look at fossils, you might say like, oh, like there's all these trilobites. Damn, these trilobites are doing really well. Like, there's so many of them everywhere. I bet these guys are going to have a really great run for the next, however many billion years on Earth. And they hung out for a long time. They did pretty well. But, of course, today we know there's many other varieties of life, most of which aren't trilobites. So it's a little dangerous to over-index or over-rotate on what you're observing right now, rather than trying to look forward maybe at the large diversity of platforms we have coming on stage today. So with that, we're going to dive a little bit into the sort of device physics of superconducting qubits. So one thing I just really want to emphasize early on is that many of you have probably seen a picture like this one on the right. So this object on the right is a dilution fridge. And you'll often see in the media something like this picture on the right called a quantum computer. This object is not a computer. It's a fridge. The computer is the little chip on the left there that lives inside the fridge. That's where the computation happens. You need the fridge to make the computer work, but the fridge itself is not doing computing. It looks nice, which is why it makes a great piece for the media, but the fridge is not, it's essential, but it's not the same thing as the actual computer. So if you take one thing away from this talk, please let it be this. The object on the right is a fridge. And these fridges are really amazing because they manage to allow us to store a long-lived quantum state in a superconducting circuit. And when we actually cool these chips down, they're colder than basically open space. So open space, if you measure like the cosmic microwave background, is about 2.7 Kelvin. And the fridge is actually cooled to about like 10 millikelvin. So it's, I don't know how substantial the difference would feel to you, but to quantum objects, this difference is really significant. So this fridge, when it's working, is quite a bit colder than deep space. And inside, we have this little chip that is an engineered wafer. If you went to the ASML keynote, you may remember we were discussing wafers and semiconductors. So this is an etched wafer with some sort of photolithography, and it lives inside this fridge, and when it's cooled down, it can implement some kind of superconducting qubit. And there's many kinds of superconducting qubits. There's many different architectures. So even when we discuss superconducting qubits, just like the trilobites, there's actually many different varieties. And we're just going to discuss one of them quickly. But you should just keep in mind that there's actually a whole ecosystem, even in the what might seem like a relatively narrow area of superconducting qubit design. OK, so how does this chip actually work? So here is a relatively older, nice picture of a 4-qubit transmon device from IBM. So in this device, when it's cooled down, you have a bunch of electrons running around in the circuit. And those electrons get so cold, they pair up to form what are called Cooper pairs. So if you don't know what that is, completely fine. If you go on Wikipedia and look up BCS theory, you can learn all about what these silly little pairs are. But they only form at extremely low temperature. And in fact, for the computation to be effective, we have to cool the entire chip so much that these pairs are mostly in the qubit are mostly in the ground state. And that's why we need the really big fridge that we showed on the previous slide. So without the fridge, none of this works and we can't do any computations. And then on the chip, you can see there's 4 little traps. And we make an idealization that within the trap, there's either 0 pairs or 1 pair. So that's called like a charge box qubit. And this transmon design that they have here actually does something even more sophisticated to make these pairs, or the states that represent 0 and 1, longer lived. But that's effectively the bare bones description of what's going on here. So we trap these little pairs in these 4 regions, and we can say there's either none of them or one of them. And that lets us do computations with them. And we manipulate them with the wires you can see on the outside of the chip. So we have all these wires that are connected to the external environment, and we send microwave pulses through the wires to control the device and do computation. Awesome. Wonderful. Now we're computing. Great. So this would be, we'd be ready to go, except, of course, when we're controlling the device, it's not isolated. So if the device were completely isolated and we never had to talk to it, these quantum states would be super long-lived. And everything would be great. But for us to do computations, we have to interact with the device by controlling it and then initializing it and reading it out. And this introduces a lot of potential for things to go wrong. So we're kind of trapped in this annoying dilemma where we want the device to be totally isolated up until the exact instant we want it to do something. And then it has to become unisolated. And then we need to isolate it again really quickly. So the entire sort of dilemma that we face when designing these devices is that we have a lot of trade-offs to make. So we have to draw a layout for these wires and these qubits. And then, again, as we saw in the wonderful ASML keynote yesterday, we have to actually create the chip, which is itself a very complicated process. Using that layout we drew, we put the chip in the fridge. Great. We cool it down. We run our workloads, see how good they are. Usually they're not so good. And then we improve steps 1 to 4 by gathering data. OK, so we're going to discuss steps 1 and 4, because those are the ones that are probably most relevant here. But if you want to know more about 2 and 3, or especially 2, you could probably find someone from one of our awesome sponsors, ASML, and learn more than you ever wanted to know about wafer deposition. So when we created a device layout, we have a bunch of trade-offs we have to make. And this is true, of course, in classical chip design, but it's true in quantum as well. So one of the big ones is the fridge we're thinking of has a fixed size, and it's really not very easy to expand it. So we got to get the chip to fit in the fridge die. And we want more qubits on the die, because that will let us do more computations. But we have to be able to address and control each one of those qubits. And the more components that are close together on the die, the more potential we have for quantum interference effects, for all kinds of errors to be introduced. So we have this odd sort of trade-off we have to make where we have something of fixed size and we're trying to cram as much stuff into it as far apart as possible, in a rough sense, which is pretty problematic. And that's something that we can do computationally, and it's something where we need a lot of very high-performance simulations running quickly many times per day. So how do we actually do this? When we come up with the layout, we don't stand there waking up from a dream and just draw something, or maybe some people do. But usually what folks do is they say, okay, luckily, we've been studying electromagnetic physics for a long time. We have a pretty good idea of how both classical and quantum electromagnetism works. So what we'll do is we'll first draw some layout of the components we want on the chip. And then first we do a classical ENM simulation of the circuit, which has a bunch of nonlinear elements. So effectively here, you're doing some sort of finite element simulation, and there's a lot of nonlinear pieces that go in there. This is, as many people can tell you, a very computationally difficult problem. And for every single layout you want to do, you've got to do this first to make sure, as effectively a sanity check, like even without considering any quantum effects at all, is this feasible? And then once you've done that, okay, looks good. You do a Hamiltonian simulation that involves the sort of purely quantum physics that combines the classical results you got in the previous step with quantum effects. So just to shout out quickly to some of my colleagues, we, for example, have released classical ENM software called Palace that you can check out, which is mostly written, I believe, in C++, but has Julia bindings that you can use to simulate device layouts like the one I've shown here, which has actually been fabricated. So what you can do is you can simulate first one unit cell of, you can see there's sort of a repeating pattern here. So you simulate one unit cell, okay, looks good. Then you simulate 2, and then 4, and then more of them until you run out, effectively, of ability to simulate this classically. Then you can go to the fabricator, fabricate it, put it in the fridge, and see how it does. But you need those classical steps to figure out whether it really makes sense to go to the fabrication step at all. And then you fabricated it, and again, if you want to know more about how that works, I suggest finding somebody from ASML. Okay, so we've done some fabrication. We have a chip. Now what? How do we actually control this device and make it do something useful? So it's stuck in the fridge. The fridge is running. It's super cold. Okay, now what? So we're ready to run some experiments. And the way we do this is we actually have to send a bunch of low-level pulses to the device. So the device doesn't really have any notion of like our logic gates of, you can't just walk up to the fridge and yell, do a C0 at it. You need to be able to control it using these sort of low-level continuous waveforms, and it's a very complicated problem in general to figure out the correct, or not correct necessarily, but best way to do that. You want something that will both be accurate, but then relatively quick to run, and then it's again a complicated trade-off at any time to figure out the correct sequence of pulses to keep the program and the chip running at acceptable quality. And so you also have to decide, like, so I've run a bunch of experiments, and how frequently do I have to reset the entire device and recalibrate it between running various experiments or running people's workloads? This, again, is a complicated problem you can model computationally, and it's something that we actually have a lot of folks in the Julia community working on. Hopefully, some of them are still here. Okay, the device is calibrated. We've made our measurements. Awesome. And now our results look awful. What do we do? So we run our quantum workload, for example, like some sort of Grover search, let's say, and we see something unexpected. The device quality is really bad. Very occasionally, we might see something better than we expect, but oftentimes it's worse, which is very sad for us. So we need classical simulation here, too, to understand what the cause might be of the device not performing as we expect. Because we did a bunch of simulation before we fabricated it that gave us some sense of, okay, we think the device will perform like this, and it's not, so what's going on? And we need a complicated physics model of each device component, and then we combine all of those and integrate a very oscillatory time-dependent PDE, which again, as anybody who's worked with some of the Julia PDE integrators can tell you, this is not an easy problem to integrate one of these devices, especially in a performant way. And we need to use our results from this process to figure out what could be wrong with the device. Is it that our e-beam lithographer has something wrong with it, in which case all of our subsequent fabrications are not going to work, and we have to get somebody to come fix it? Is it that our pulses were bad, and that's why the results on this specific qubit don't look very good? Or is it that the design we came up with is bad for a reason we don't understand? We have to go back and consider whether we understand the physics of this component, or whether we modeled an incorrect approximation for some aspect of the design. And this may require doing some sort of like open system integration using a Lombardian or master equation. And it's pretty difficult because factors even outside of the chip and the fridge can play a role in it. So for example, quantum computers like these really don't like having variable magnetic fields. So if you have the device in a building and somebody very occasionally is taking the elevator. The elevator has a big block of iron that's its counterweight often, and so very occasionally if the elevator is going up and down, there's a variable magnetic field that can affect your device quality. And you need to figure out, is that what's causing this, or is it something else? Is it the device is bad, or I need to tell people to stop taking the elevator? Which one of those is maybe a harder problem to solve than the other one. And now, okay, so we have, we've had the device fabricated, we've done some simulations, the quality looks good. So now we actually need a way to program this thing at a level that we can understand and we can devise algorithms for, which means we need a way to specify the actual workflows we want to run on the device. So we may have like a very high level construct here, like we have some input state, which I've drawn as psi here, some algorithm, for example, the quantum Fourier transform, and we want to get some output state from it. So again, how do we actually turn that into something we can run on the quantum computer? Because similarly to before, we can't just walk up to the fridge and yell at it, please do a quantum Fourier transform. It probably won't understand. So we need a way to communicate directly with the electronic components and say, we need to do this quantum Fourier transform in a way that's performant and more or less error resistant on your specific device layout. So just like in classical computing, we take each component of this and we sort of break it down into into individual pieces. So for anyone who's taken like a CS class, maybe in like assembly language, or if you're familiar with instruction sets, this is effectively the same process where you have some complicated operation you want to perform and you're breaking it down into, classically this might be opcodes, and in quantum computing instead you have a series of quantum gates that you apply to qubits in the circuit. So this is an idealized representation of what we're doing on the device. You might have noticed that there's like a lot of layers of idealizations in this process. So part of the challenge you face is you go from something high level like this that's super idealized and you have to translate it down to something very device specific, which is a problem we're going to discuss in detail. So we have our input state. We initialize the device all in the 0 state, so like the lowest lying energy state. Okay, we're ready to run our algorithm. So we have some operations we apply just to prepare the input state for our algorithm. This itself can be a complex process. And then we have some more operations that we apply to actually implement the algorithm, and then we make sure measurement at the end. Great. Okay, so where did these operations come from? Like, what are these operations we're going to do, and how do we know how to write them down and how to translate them to something the actual physical device can understand? So when we talk about a quantum gate, we idealize the qubits in the device as having 2 orthogonal possible states, as we talked about before, 0 and 1. And so these gates are implementing a particular logic operation on qubits, and it can be on 1 qubit, 2 qubits, however many. And luckily for us, we can represent this process with probably, to people in the Julia community, relatively familiar complex linear algebra, everyone's favorite topic, matrix multiplication. So these quantum gates can implement operations that flip the qubits, they can rotate them around various axes in phase space, they can entangle them together so they can induce correlations between them. So there's a lot of different operations that they can apply, and we can combine these to end up with some more complicated algorithm that actually does something interesting for us. And a very crucial point here is that some of these gates are easier to implement on certain types of hardware than others. So when we take a high-level algorithm description like quantum Fourier transform, it may be the case that the actual gates we use are very dependent on the device or like the underlying hardware technology we're using. So here we have a 2-qubit state psi. If anybody here is a C user, don't at me. And then we have a gate, the XY gate, so this rotates the 2 qubits that psi is addressing, and we can write down its matrix representation here. And you can see this is going to rotate the 0, 1, and 1, 0 states, and we just matrix multiply, or in this case, matrix vector multiply xy times our input state, and we get the output state phi, which now has a rotation applied to it, but only on the 2 states 0, 1, 1, 0. So this is a relatively simple gate, and by combining these, we can end up with the full implementation of some algorithm like the quantum Fourier transform. Okay, so that's great, but the fridge and the device we're talking to doesn't know anything about linear algebra. Like if you go up to it and then start yelling like, here's my matrix, it's still not going to be able to do anything. So you need a way to teach the device how to implement this operation using the microwave signals it actually understands. And this is a problem that we need a lot of classical computing for. So we have 2 qubits, and we have some gate, this XY gate that we want to implement. And the question is, what's the best pulse to send over the wires into the device to actually implement this gate? And there's lots of different techniques folks are using to try and figure this out. One example is you can use reinforcement learning to try and understand this. And unfortunately, or fortunately for you, the answer to this question can actually change over time as the device is running. So the gate pulse you run when the device first turns on at the start of the day might not be optimal 6 hours later. So then the question you have to ask is it worth it to use a pulse that's like kind of raggedy and out of date, or spend a bunch of time recalibrating the device and then figure out a new set of good pulses for it? And this trade-off, again, is not super obvious what to do, but generating these pulses and determining their optimal form is something we can, and many people are, using advanced classical computing techniques for. And if you want to know more about that, I definitely suggest hitting up the piccolo.jl folks, whom, again, may still be here. And so we have a lot of work to do still to figure out how do we turn this linear algebra representation that's like relatively understandable by humans into an optimal set of pulses in a reasonably short time frame for the device. And of course, if we're looking at this, you might say also like, you know, like linear algebra is okay, but I don't really want to write down all these matrices all day. Like this is kind of annoying. Even if you're one of those weird people like me who kind of likes linear algebra, like writing down a lot of matrices like this and multiplying them is like, am I really doing this? Am I back in undergrad? Isn't there some kind of higher level, like, you know, in classical computing, you can write down a bunch of truth tables and do effectively like a similar process, but we don't do that. We write down instructions, and then there's a whole set of compiler steps that turns that into something the computer can understand, and we don't have to worry about it. So can we come up with something like that for quantum computing? And similarly to sort of the situation in the hardware ecosystem where we have the emergence of many different options, we also have the emergence in kind of the programming construct space of several different intermediate representations for quantum programs. So we take some high-level circuit, like the one I showed with the psi, quantum Fourier transform, and output state, and we want to lower it to some kind of IR. Or maybe we want to take the IR and parse it back into one of those high-level representations. Like if somebody comes to you and they say, I have an IR for this circuit. Can you turn it into a Julia object for me, and then I'll try and manipulate it and compute some gradients on it. You need a way to take that IR and parse it, which means you need a lot of information about the IR, what are acceptable symbols, and things like that. And especially for the lowering step, you need a lot of device-specific information, because if you take your high-level circuit and you lower it to operations that are very hard to implement on the quantum computer, you're going to end up with a circuit that doesn't run very well. So you need a lot of up-to-date current information about the device to do this lowering process in an efficient way that generates effectively good sets of instructions to then send to the pulse generator that goes to the device. So there's quite a few different IRs that are in use today. Probably the 2 most common ones right now, I would say, are OpenQASM3, which is open source and come up with by a collective, and then QIR. And then just to plug a project of mine, so I recently open sourced this new package called quasar.jl. It's actually a submodule right now, but it's a purely Julia OpenQASM parser based on Automa. And if you know the Open Pulse grammar really well, come talk to me at the hackathon, because we need these kind of constructs to enable the Julia community to be able to quickly work with these kinds of IRs, be able to translate back and forth, and make use of the higher level constructs we have and the lower level packages that, for example, generate these pulses. Okay, so what does it actually look like when we represent some quantum program like this? So we have some OpenQASM file here. Probably many of you looking at this can guess what language this might have been inspired by. The def is pretty telling. So if you wanted to write a program to run on some quantum device, it could look like this. You have a header that says like, hey, I'm an OpenQASM program, and here's my version. And then you define some functions. You have a function bell that operates on 2 qubits and applies some gates to them, and it generates a bell pair. So this is a relatively basic quantum circuit. It's one of the things you got to be able to get right before you get anything else right. So this bell function entangles qubit Q0 and Q1, whatever those are that you pass to it. And then we have another function, nbells, that, and this will shock you, it applies this bell entangling procedure multiple times to the qubits. The indexing here might also tell you where they drew some inspiration from. And then we have a bunch of variable declarations that say, like, okay, this circuit runs on 4 qubits. We're going to entangle qubit 0 and qubit 1. And then we're going to run this bell generation procedure 5 times on qubits 2 and 3. And finally, we make some measurements just to see what the output state is. And that will be the result of our circuit. And then, of course, the device takes this file and turns it into the pulses for us. But the goal is, if we want, we can specify this pulses. But if we don't, we can just say, like, all right, I trust whoever programmed this device to have some decent pulses set up for me. So I'll just give it this thing, and it'll run it. Awesome. So under the hood, what's actually happening from this sort of linear algebra construct point of view is we have an input state psi up there, and we're going to apply this bell function. So we have this H gate and this controlled NOT gate, which is effectively a flipper on Q1. And if we actually write out the matrix formula for this, we can see that the first gate we apply has this form. It's just this little 4x4 matrix here. And the C NOT, which is a controlled NOT, has the form I've shown here. And we can actually just multiply these together to get a unitary matrix that represents the entire circuit. Hurrah! So it's relatively easy to see for a small 2-qubit circuit like this what the matrix form of the entire circuit operation would be. And from there, you can generate all your truth tables and everything we love so much from classical CSC. OK, so now we want to consider what happens if there's one other qubit that we have to worry about. For example, when we start applying gates to qubit 2. So then we need to consider the states on qubits 0, 1, and 2. And on each of those, there's 2 possible states, 0 and 1. So the total length of the state vector is 8. And it means the operation of that first gate is now an 8x8 object. And so each additional qubit that we include in this problem increases the size of the matrix we have to consider by a factor of 2. So generating the entire circuit unitary very quickly becomes infeasible, which is part of why, even if you don't care about the pulses, these kinds of intermediate representations using these, if you like, quantum DSLs are really important for us. We need a way to, instead of having to write like a 2 to the n by 2 to the n matrix to specify our program, we just want some human-readable instructions. And coming up with a good set of these is not necessarily a trivial problem. And then from there, we can go all the way even higher to these sort of diagrammatic representations and start building something that we can actually like pass into an auto-differentiation library if we want. OK. So if we start chaining together all these abstractions, we can end up with what's effectively a relatively robust pipeline that goes from, I want to run some algorithm that I heard about from some quantum textbook, all the way down to the pulse level. And we can even stack things on top, like computing gradients with autodiff, making optimizations for measurements, making mid-circuit measurements so we can do control flow. And the result of this is that one program that we want to run on the device may become many thousands of these open chasm instruction sets. And even worse, we might need to compile the instructions to take advantage of specific features of the device. For example, when we do our calibration, we see that some qubits are working better than others, so let's focus on running our stuff on those. And as many of you no doubt know, we have this amazing community package, yao.jl, that's really more of an ecosystem that allows us to do a lot of this kind of work. And so just to kind of elaborate a little bit more, and specifically in the superconducting qubit context, this is really important because not all of the qubits are connected. So if you are familiar with classical HPC, this probably isn't that unfamiliar because, of course, often when we're running on a classical cluster, not all of the nodes in the HPC cluster are connected to one another. So your algorithm's performance can be really degraded if you don't take into account the specific topology of the cluster. And it's exactly the same for a system like this, where not all the qubits are all connected. The reason for this is that the devices, when they're created, have a definite layout. And so we need to consider, how do we apply a gate on 2 qubits, like the one in red and the one in purple here I've shown, that are not directly connected? So we may have to decompose the operation we want to apply between these two into many intermediate gates. And you also then need to pick a path to apply those gates through the layout of the device, taking into account the specific fidelities, or if those qubits are supposed to be running other gates at the same time. And so it's effectively a large graph problem, which again, I hear that there's a language out there that has really good libraries for this kind of weighted graph optimization. If anybody knows about it, please let us know. And there's even more complex and irritating problems we have to solve. Like, for example, if the device has a lot more qubits than the circuit, which qubits should we pick to run the circuit on? Picking a good embedding in the device can, again, drastically affect the quality of our results. And we also might need to consider, let's suppose we fabricate 3 of these chips that have a small number of qubits, but we want to run a really big circuit. Is there a way we can do that by effectively chopping up the circuit into pieces and sharing information between our chips? And so this problem is also probably relatively familiar to people coming from an HPC world, but the different latency between the devices presents a really big problem for this, and we have a lot of work to do to understand how can we use compilation and our understanding of sort of the layout and the current properties of the device to compile the algorithm we want to run into something that the device can actually do. And even worse, the devices are subject to noise. So the devices that we use every day, like our phones and like our classical computers, of course, are also subject to errors. For better or worse, they've been around for a long time, and we've gotten really good at classical error correction. So we often don't think about the fact, like, if you've ever used a GPU, you might have some like ECC, which is for the error correcting code on the GPU, turned on, and it's like, okay, I don't know what that is. I'm not going to worry about it. But unfortunately, the quantum devices that we're using today are subject to a lot of errors, and it's partly a result of the fact that we want them to do things. If they were perfectly isolated, we wouldn't have these problems, but they can't be because we need to give them instructions. And so there's various types of error that can exist. So for example, we have here like a sort of cartoon diagram where we have the 0 state of the qubit is the lowest energy state, so that's why it's on the bottom. And then the 1 state is higher energy, which is why it's on the top. And so we've prepared our qubit in the 1 state. That's great. It's hanging out. It's having a good time. And then it decides, you know what? I actually want to go down to my lowest energy state because nature usually would prefer that I do that. So it's just like, all right, bye. I'm emitting a photon, and I'm going down to the 0 state. And it did that without your permission. You wanted it to stay in the 1 state, but it's not. It's in the 0 state. And there's really, you can't prevent it from doing this. Nature is just like, okay, see ya, I'm emitting my photon now. And this is called like the T1 relaxation time, and making this longer is a very important part of making these devices more usable because it reduces the error rate. Because you were counting on this guy being in the 1, but he's in the 0, completely, without asking you, which is very rude. And even worse, there's other errors that these little qubits can experience. For example, they can have their phase rotated without your permission. So we can have a qubit that starts out in the 1 state, and it doesn't have any particular rotation, or maybe a slight one in one direction. And then, without your permission, it has an interaction with another qubit and completely flips its phase. And this is a problem for us because many of the algorithms we want to use actually require these qubits to have certain relative phases to one another as we perform the algorithm. So if one of them gets rotated, again, completely without asking us and without our permission, it can affect the quality of our results pretty severely. And another common problem that we can encounter is, we have 2 qubits, let's say one in the 1 state and one in the 0 state, and we want to apply some gate to them like controlled not. So we want to control on the first qubit being in 1. If it is, we're going to bring the second qubit up into the 1 state too. We're not going to rotate anybody. And 99% of the time we do that, it works great. Awesome. Love that for us. But occasionally, when we apply the gate we intend to apply, we get a ride-along where we unintentionally apply some other gates, perhaps because the pulses we applied weren't very good. Or, some theorist walked into the room and they had a magnet in their pocket or something like that. Of course, I would never do this, but things like that can happen. And we ended up with multi-qubit errors where not only are these guys both in the wrong state, but they're also phase rotated. And we need some way to either prevent this from happening, notice it's happened, or at least be able to adjust our results to take into account that it's happened. And even worse, and you probably are going to get tired of hearing this refrain, different devices can have different noise profiles. So even if, let's say, you have a really great layout, like it's the world's most awesome layout to date, super good, and you fabricate it 5 times, then you'll still have 5 different noise profiles for that device, just based on very slight differences in the way it was fabricated and the conditions it's experiencing in the fridge. And so for each chip you have, you need to come up with an effective noise profile for it that, of course, is informed by your understanding of the device physics, and then correct for these kinds of errors as they're occurring in the device, which is a pretty hard problem. And just to kind of illustrate how important this is, we often characterize the circuits or algorithms we want to run in terms of the number of these 2-qubit controlled NOT gates we need. The reason for this is that if we have an error rate of 10 to the minus 4, so 99.99% of the time it's successful, we want to understand how many gates can we run before the results effectively become just a lot of noise. So having results that are effectively noise is great if you want to generate a lot of random numbers. Like generating random numbers is cool, but if you want something that's not a bunch of random noise, even a 10 to the minus 4 error rate can cause big problems very quickly. So I have drawn this histogram with a more exaggerated error rate, just to kind of show how this can accumulate even for one gate. So with no noise, you have the idealized result in blue, and then with a 10% error rate, if you run 1,000 shots, you have the results shown in orange, and with a 15% error rate in green. And so you can work out, if I accumulate errors at a 10 to the minus 4 rate, and my circuit needs 10 to the 6 of these controlled NOT gates, it's probably not going to be very good for my output, right? 10 to the minus 4 times 10 to the 6 is not a happy number if that's the total amount of error you've accumulated. And this is a big problem because the devices we have today, despite a huge amount of engineering effort that's been super successful by a number of very smart people, much smarter than me, this is still kind of one of the barriers we're encountering when we try and run these 2-qubit gates. So a lot of the algorithms we rely on really need a lot of these CNOTs, more than 10 to the 6. It can be up to like 10 to the 10 or 10 to the 13. So just running these on physical qubits, even ones that are pretty high fidelity rates, is going to quickly become very frustrating for us. And we need a way to deal with this. So of course, in the ideal world, what we would do is just say, it's illegal to experience errors, so you can't do it. Again, I didn't consent to this qubit flipping, so just don't. Unfortunately, again, if you just go up to the fridge and you yell at it, like, stop flipping, it's not going to listen. So we need a way to cope with a world with a lot of noise in it, which again, probably this week, many of us have a lot of experience doing. Although it seems that now the noise has been mitigated a little bit, which is good. So we have a bunch of different approaches we can take to dealing with the noise that the device experiences. We can try and mitigate the effect of the error. So we have lots of different algorithmic techniques we can use to handle these errors. We can try and infer a probability distribution, and then use that to adjust our results. We can suppress the error with a real-time adjustment of our pulses. This is, again, a super complicated problem that needs a lot of high-performance, low-latency classical compute. If only there were a language that were able to do that. And then kind of the ultimate goal for us is to be able to correct the errors so that we can run lots of circuits that have lots of gates for a long time without having to run a huge number of duplicates to effectively back out what the error was. And so the way we're interested in doing this is using what's called an error-correcting code. We construct a logical qubit that is an overlap of many physical qubits, and it allows us to detect and correct the errors. And this is something that needs a lot of low-latency classical control. And one very popular approach for superconducting devices is the surface code. So in the interest of time, I won't be able to go super in-depth into how this works, but I encourage you to check out this paper by Austin Fowler et al. It's a really great introduction for people with mathematical background, but not a lot of physics intuition necessarily. And our goal is to effectively create a bunch of tiles over the physical qubits that then create a logical qubit. And the number of qubits we need in each tile depends on both the physical qubit's error rate and the desired error rate of the logical qubit. So if the physical qubits we have are really noisy, we need a lot of them to get the logical error rate down, which is why it's still valuable to work on lowering the error rate of the physical qubits. And the implementation of these is, again, controlled completely classically, and this is something we can both implement at the microcontroller level when we talk to the device, and it's something we can simulate classically. So this is great. There's a lot of progress being made on implementing these, but unfortunately, it's still not enough. The problem is that these devices are still subject to not just errors, but defects. So what's the difference? Errors are relatively uniform, which means if we observe the error rate being like 0.1 now, and I go out for a coffee and I come back later, the error rate's probably going to still be about 0.1, and it's relatively evenly distributed through the device. They're relatively low magnitude, and the accumulation rate is quite low. And the whole point of an error-correcting code is to detect and correct errors. Awesome. But defects are not uniform, both in space and time. They're pretty rare, but when they occur, they're really bad. They're really difficult to detect, and they can't be corrected by existing sort of vanilla error correcting codes. So one variety of these is called static defects. That's what we already discussed with device or calibration manufacturing errors, or they can be dynamic. And these ones are pretty interesting because they are often caused by cosmic rays. So these are high energy particles coming at us from space. Luckily, we live on planet Earth that has both a very thick atmosphere and a magnetosphere. So we have like a nice blanket protecting us from quantum defects, which is great. The Earth is trying to make quantum computing happen, which is wonderful. Thank you, planet Earth. But these defects still affect the devices that we are building, to the point where if you actually take one of these quantum computers and put it in a deep salt mine, you'll notice that the accuracy of your computation actually goes up because it's no longer being bombarded by cosmic rays. So that's not really practical. Like, probably most of us working on these devices don't want to work in a salt mine 3 miles under the ground. So can we come up with a sort of improvement to our error correcting codes using classical software that allows us to heal these sort of point defects? And there's a lot of kind of cutting edge work happening in this field right now. I've included some QR codes for it. And here's a nice diagram from one of these papers about the entire sort of flow of these algorithms where you have defects on top of your existing errors, and you need to detect them, handle it in your error correcting code, and continue with your computation. We can't go into all the details right now, but as you can see, there's a lot of complex classical computation that has to happen very fast and low latency in here. So, of course, there's many options for how to do that. It's not guaranteed that Julia is the only one or the right one, but I think there are a lot of opportunities in this whole space for the Julia language and Julia users to contribute to kind of these developments. And then finally, this is sort of the area that I actually am most familiar with. We need to compare with something to understand whether our quantum computations are working. So we want to both simulate quantum algorithms themselves and then simulate the systems we want to study with those algorithms. When we say that quantum computers are useful, we have to compare with the classical state of the art. And the only way to find out what the classical state of the art is to do classical computing. So even if you don't know very much about quantum computing, there's a huge contribution to be made improving the performance of the classical algorithms that already exist. And so one of the big applications people are interested in, though of course not the only one, is doing quantum chemistry with quantum computers. A molecule, as we saw on Monday, is basically a big collection of interacting quantum objects. There's a lot of nuclei and electrons running around. These are quantum particles, and quantum mechanics governs their behavior. So you want to figure out what geometry is nature going to favor, and can you understand if or when reactions are going to occur. So there's a lot of sort of proposed applications for this, from doing carbon capture to studying things with aromatic rings. And one thing that's really great about doing quantum chemistry is that human beings have been doing classical computational chemistry for a really long time. We're really good at it, which is good. We have made a lot of progress in the world because we're good at doing classical computational chemistry. So it's pretty hard for quantum computers to beat, for a lot of systems, the classical state of the art, which is a good problem to have. But for some systems, the exponential blow-up we see is just so bad that classical computers find it really hard to make progress. So in the presence of strong interactions, these classical techniques break down. And we think, some kind of quantum computer to compensate. The way we do this, and I'm going to have to breeze through some of these in the interest of time, and I think there are drinks after this, so I'll try and be quick, is we need to translate a continuous system that represents the position of all the electrons into something digital that we can actually run on the quantum device. doing this translation is a really complicated classical computational problem. Again, this is probably a phrase you're tired of hearing me say. And this is also a really big opportunity for the Julia community. Many of the codes that do this now are great, but they're Python wrappers sitting on top of C++, a problem many of us got really sick of dealing with and wanted to avoid. And so there's a lot of low-hanging fruit in this space to implement both existing algorithms for doing these kind of translations and coming up with new ones. And then we also want to understand how we can take the existing quantum algorithms that we have come up with as guesswork for trying to use these and improve them. There's a lot of quantum algorithms out there for electronic structure or molecular geometry that we would like to run, but they have pretty bad scaling problems. So the naive version of the unitary coupled cluster ansatz, which is the one most of us use for quantum chemistry, has n to the 8 scaling. So n to the 8 is better than 2 to the n, but it's still really bad. And we haven't even talked about the prefactors. So what we would like to do is use a bunch of these algorithmic techniques, which many people are working on, to cut down that n to the 8. There's a lot of progress being made here, but it won't shock you to hear a huge amount of this relies on high-performance classical simulation of these systems. And this is something where we need a lot more of this simulation to understand how these algorithms compare with each other and how they compare with the quantum state-of-the-art. Or we need a lot of ways to efficiently generate these quantum circuits. And again, in the interest of time, I'll get to the part that probably many of you came to this talk to see. The question of integer factoring. This is the application of quantum computing that many people are very interested in, although a lot of physicists are tired of hearing about it because we don't care about integers. So I'll just say, here's a beautiful integer on the left, and here's 2 primes that I looked up earlier today that claim to be primes, so I believe them. So if you want to factor this object on the left, the claim is you can use a quantum computer to do it with some speed up. The good news is, to do this, you need on the order of 1,000 logical qubits, and today we have about 1. And the engineering task, as I've hopefully convinced you in this talk, of getting from 1 to 1,000 is pretty complex. So I wouldn't worry about it this year. And hopefully, by the time someone is giving another quantum computing talk, we'll have a better idea of how long this is going to take. But in the meantime, there's a lot of really interesting challenges that we want to tackle and that we can use Julia, I think, to make a huge amount of progress on. And we can have fun doing it, which is always a good problem to have. And I think there's lots of opportunities today to contribute at all levels, like even in completely classical computing, if you're like, oh man, this is awful, like this quantum computing stuff, you convinced me is terrible and I don't want to talk to these devices. That's great. You can use classical computing to prove that they still don't work for many problems, which is a good thing for people to be doing. And I also just want to emphasize that we can't assume quantum computing will evolve as classical computing did. Of course, in hindsight, it's obvious to say, like, yeah, the transistor came on the scene and that was it. And now classical computing is all based on these specific microarchitectures, and therefore quantum computing will be the same way. But we don't know that that's the case, so there's still a lot of growth in the field left, and we don't want to assume that everything is going to stay a trilobite. And finally, I just want to say that over the past 9 years, the Julia quantum community has really grown, and now we have all these amazing packages, including any I forgot. And hopefully, the next time I or someone else is giving a talk like this, we'll need a lot of slides to show all the packages we have. Many of these folks will be here during the hackathon. And finally, since I'm definitely over time, thanks everyone for your attention, and hopefully, we'll see more of you in the quantum community soon. Sorry.
Thank you very much for the great talk. Do we have questions from the audience?
Yeah, sorry. People in the balcony also can ask questions.
Oh, wow, they really came prepared.
There's one question on the second floor, here on the left. So if we can get the catch box on the second floor.
What's that? Nice.
Someone want to ask a question here?
See, that's a great example of a 2-qubit error. Right
Looks like we're actually doing sports in the stadium here. So my question was, considering that you need a lot of classical computing to even control these qubits, shaping your pose, etc., at what kind of problem size do you expect that the classical computing that we need to do in order to control these qubits is even viable to get some computing benefits out of the quantum qubits?
Yeah, it's an interesting question, partly because it's a moving target. So having to do these pulse optimizations repeatedly is partly an artifact of the fact that the devices we have, let's say they have room to grow. So as the device improves and as we better understand how to control it, you have to do fewer and fewer of these adjustments to control to kind of control what the device is doing. So, early devices are kind of like a waterbed, right? Like you jump on it and then it sinks where you are and it goes up everywhere else. And you're rolling around and it's sloshing and it's just very hard to control what it's doing. Again, this is like a very rough analogy. But the devices that we're working on building now are much more controlled, where you like press on it on one spot and it doesn't, floof up somewhere else. So we have a much better ability to keep the device in a relatively kind of static state, which then reduces the need for constant recomputation of both the pulses and then understanding of what the device specifically is doing.
Thank you for the very nice presentation. My next question is, can AWS bracket simulator do weak or strong simulation, and how many qubits is the max?
Sorry, could you just clarify for the audience what you mean by weak or strong?
If you have strong simulation, you get the complete state vector, and the weak one does not. So.
Yeah. For those who don't know, Bracket Simulator is a package we just launched that lets you do simulations of these systems on Amazon Bracket. It has support for both full state vector, so strong simulation without the presence of noise, and density matrix, which is a strong simulation in the presence of noise. And I think our maximum qubit count I've run just on my laptop is 31, but if on a system with higher memory, you can do higher. So there's a lot of also optimizations you can do in the classical simulation of these circuits, where you do a HPC kind of optimization or multi-GPU. It's a very interesting space. Oh.
I think we can take one last question, if there's more questions.
There are two questions, one this side and the other side. Which one?
You pick.
I mean, you can also chat afterward.
Yeah, well, I'll be around after. So. Okay, there it is.
So it's maybe a question that's a little bit more general, but what causes, and maybe it's just quantum effects, the performance of whatever chip to change over time? Is the state that's not visible that's changing over time, or is it the device itself that's deteriorating in some way?
Yeah, so it can be both. So when you initialize the device and you calibrate it, you set up your control wires and everything, and the entire chip has some quantum state, right? And you can experience what's called leakage, where when we came up with that idealization of the 0 and 1, there's other states that the system can access, there's two pairs or whatever. So as the system runs and as you put energy into it over the wires, you can start leaking these pairs into high energy states that, you said, no, there's only 2 states, and the device is like, oh, what? Well, I have lots of states. I don't care about your number 2. And then that's why, after running a bunch of circuits, you need to sit the device down, recalibrate it, lower it back down into its ground state. And then even worse, what can happen is, let's say your fridge breaks and now the device is hot and you cool it back down. You may never get it back with the initial set of calibrations you have. So it can be both an ongoing, a permanent defect, and then just the fact that when you're controlling the device, you're putting energy into it, right? You have to do that to talk to it. And this affects the state of the underlying chip. And I think in the interest of having our closing ceremony, Ray is on the staircase back there. If anybody would like to chat more after, I think we're having drinks after in the stadium. So thanks for your attention. And yeah, oh my goodness. Chateau Julia. Should I just...
Thank you for the very inspiring talk. And now I will hand the microphone to Ray for the closing remarks of the conference.
Thank you. Alrighty, can we swap screens here for me? Wrong screen. 1 second. Sorry, folks. All right, so the first thing I'd like to do is call, I believe, Alan and Curtis to the stage for us to have our annual Julia Community Prizes.
Hello, everyone. I should say hello, Phillips Stadium, but maybe hello, Dirtfield. But in spite of everything, I hope everyone had a great JuliaCon. Yeah, that's more like it. Thank you. So you've heard a lot of amazing talks over the last few days and hopefully learned a lot as well. But JuliaCon is nothing if not a celebration of our community. That's what we want to achieve through this, getting everyone together every year. So every year we celebrate a few members of our community, particularly by name, using the Julia Community Prizes. And this year is no different. We'll do that. Thank you, everyone who have nominated. We had, I think over almost 100 nominations this year. And thanks to our judges, Curtis, Alan, and Tim, who have the unenviable task of picking 3 winners from loads of deserving candidates. So without further ado, I'm so glad to announce the winners of the Julia Community Prize 2024. And in no particular order, the first is the Marquee team, which includes Simon Danish, Julia Scrumbigel, Frederick Fryer, and Anshul Singhvi. If any of you are here, would you please come down? The Marquee team have obviously, created Marquee and maintained it over the years. They have, according to the judges, improving the state of the data visualization in Julia is, is something that we should all be grateful to. Is anybody from the Marquee team here? Simon, come down, come down, come down. What are you doing? Come on, guys. Don't jump down, run. The prizes are secret, so, the envelope has just been opened, so therefore they didn't know. So that's part of the problem, but that's the Marquee team. So while we wait for the Marquee team to run down, oh, there he is. Anshul's first. So yeah, you can if you are nimble enough, I guess. Round of applause for Anshul for being first on stage. And Simon's in the stairs somewhere. So while Simon comes down, I think it's time to announce our second winner of the prize this year. But there is Simon. Simon and Julius. They are taking the long way, which is the proper way. At least they're getting some exercise through. So round of applause for Simon and Julius, please. Over there. Thanks again to everyone who's worked on Marquee, and particularly the 4 core developers. Thank you.
Thank you.
Our second prize for 2024 is the Jump team, including Oscar Dawson, Benoit Lagat, and Miles Lubin. I don't know if any of them are here, but let's give them an applause that they'll hear on the video. The Jump team have been at it for a long, long time, and their long-term commitment to Jump is something that particularly the judges wanted to call out. So thanks to the Jump, thanks to everyone who's worked on Jump. Last but not the least, our final prize for 2024 is Guillaume Dahl for their various contributions to the Julia ecosystem, including differentiation interface and the modern Julia workflows.
Sorry for this. I just want to ask if I can bring Adrian Hill to the stage because he has co-developed both differentiation interface and the modern Julia workflows. So this is for both of us, and there was a third member of modern Julia workflows who was sick today and couldn't make it, but hope you're watching. This is for you too. Martin.
Thank you. Thank you, Guillaume. Thanks again to all the winners and everybody else in the community who's made it such an exciting place to be. And with that, I'll hand over to Ray for our closing words.
Alrighty, thank you very much, Community Prize winners, and to Avik for running that for us. So first of all, thank you so much to the attendees of JuliaCon Eindhoven 2024. We really appreciate you being here, and obviously it wouldn't be a conference without you. So, give yourself a pat on the back for that. I'd also like to thank our sponsors, our diamond sponsor, Julia Hub, our platinum sponsor, ASML, our silver sponsors, Eston Automation, Cognibotics, Sioux Technologies, and Relational AI. Our bronze sponsors, Boeing and Jeffrey Sarnoff, and Pumas AI, as well as our copper sponsor, Better Hand Financial Technologies, and our amazing startup sponsors, EvoVest, G2I, Genie, Great Lakes Consulting, IENAI, and Unitary Fund, as well as Jolin and Jehan. In addition, we have a bunch of partners to thank, TUE, the Stadium, PSV, Lazy Dynamics, Version Bay, and Ferris Systems. So please give our sponsors and supporting partners a round of applause. I'm going to probably talk a little fast and rush through things because I know everybody wants to move on with the rest of their evening. So I just wanted to call out one more time that we have over 300 speakers at this event, over 700 attendees, especially on Thursday. It's our second ever JuliaCon Global in Europe and our 11th JuliaCon Global. And we had an amazing over 50 volunteers who have made this event possible this week. So please give a round of applause for our volunteers. I have some random brief announcements. The first is that we have some new merchandise stores that I wanted to announce here on the closing ceremony. And I'd like to announce the return of the REPL shirt to our merch stores. This is updated for LTS, so hopefully everybody will check those out. We also have a much requested new place to buy sticker packs. So I've received sticker pack requests from over a dozen people during this conference. Please no longer ask me for stickers. We have a website where you can purchase sticker packs, and we'll be updating it as we receive more logos and cool designs and stuff like that. So I'll be adding those to the website today, but you can find Sticker Mule for our sticker packs and then our new merch stores down here. We sold out of our hoodies today, so hopefully if you didn't manage to get a hoodie, please check out those stores at the bottom. And there's 25% off for the next 14 days since we just started those stores. I want to call out JuliaCon Proceedings. If you are here and you are a speaker, please give JuliaCon Proceedings your attention. They are a great place to publish a real paper with your talk. And our JuliaCon Proceedings team is an amazing group of people. So that process will go very smoothly for you, I am sure. In addition, we have a call for hosts. We do not yet have JuliaCon 2025 set in stone. So please email me or go to our website if you would like to host JuliaCon Global. In addition, I've had over a dozen people talk to me about hosting meetups and JuliaCon locals in their locations in the coming year. If you are interested in doing so, please do the same. Email me or go to our website. We'd love to continue to grow the communities across the world as Eindhoven has been so successful in doing here. Finally, excuse me. I'd like to thank our amazing organizing committee. We have a ton of amazing people Catherine, Luca, Mark, Skylar, Valentine, and our fantastic local chair, Gareth Thomas, without whom this conference would simply not be possible. Karsten, our proceedings chair, Pablo, Jorge, Max, Erwin, Dimitri, Long, Audra, our amazing sponsorship manager, Avik, Long, excuse me, I have Long there twice, my apologies, and Ranjan are my co-executive chair who is back in the US. So please give a huge round of applause to our organizers. I'd also like to thank a couple people who are not organizers, but without whom this conference would not be the way it is now. Cormulian, the person who I'm sure you all know designs many of our most beautiful graphics. Kuhn Vossen, there it is. Kuhn Vossen, who is not a member of our committee, but is a member of PyData. He did a great job with our AV, and so, you know, fantastic AV this year, in part because of him. And then real quick for the rest of the list, Jacob Zelko, Kim Oth, our DEI panelists, Guillaume, Julian Samaru, Cameron, Alan Edelman, and many, many more people have made this conference possible. Our hosts, TUE and PSV, have also been super amazing, especially you know, at TUE we have Erwin to thank for a large part of that part of the workshops. And at PSV we have to thank Anne, Robert, Dennis, Bram, the Mansfeld AV team, and the entire team running the conference center at PSV Stadium. I want to be sure everyone is aware we have a hackathon tomorrow. It starts at 10 a.m. at the Grand Café de Lictoren. It's attached to the West Court Hotel if you are unaware where it is. Please join us. We typically have great attendance. If you've never been to a hackathon, many of our organizers will be there to help you find a project and try to work with some of our amazing contributors in the ecosystem. So please join us tomorrow at 10 a.m. Not 9 a.m. like your brochure says. And then, yes, please charge your laptop. We do not know how many outlets there are. We do not know how easy it is to access them. Please charge your laptop. Thank you, whoever said that. And finally, we have an attendee survey. There are drinks and available for purchase and snacks after this. So while you're availing yourself of those amenities, please take our attendee survey so we can continue to improve the conference next year. And with that, I think we are ready to close this conference, and I hope you all have a great, safe travel home. Thank you.